Looks like we have a lot of folks joining in. I'll just give some introductory remarks here and give you a couple of tips and pointers for the day before we get started. For those of you who don't know me, my name is Christine Escobar. I'm vice president and co-founder of a company called Space Lab Technologies here in Boulder, Colorado. I often struggle with what to title myself as because I'm kind of a crossbreed between an engineer and a scientist, between a systems ecologist and space habitat systems engineer. So I'll call it an eco-astronautical systems engineer, but that's a lot of syllables. Basically, my background is in doing research and development for habitation systems for bioastronautics, and specifically for sustainable habitation systems is a passion of mine, and so that's why we're why I'm here today, joining all of you. What we are really here together for is that we all, I think, share a vision. And that's for the idea of using life to support life in space, a vision of being able to sustainably live and work in space so that we can explore farther for longer periods of time. We believe that there's a need to promote and organize closed ecological life support research internationally and try to reignite interest in the ecological systems approach for space habitation, given that there's this big current momentum really for deep space exploration. And we think that closed ecological systems will be the capability to enable indefinite, sustainable human exploration of space, as well as sustainable living on Earth. Many prior needs assessments that we'll go back over with you some of the results from when we met last time, but they all point out similar gaps in knowledge and technologies, and a lot of the obstacles, there are a lot of obstacles remaining in realizing this vision. So we think that advances will be made when we start coordinating our efforts and socializing these concepts globally. So we hope that this workshop can provide you with some inspiration today and some momentum to that end. And we hope that this will be one of many. And again, we're really glad that you have joined us. Oh. So a couple of the primary goals of this workshop: we want to review where we've been, what are the research needs, what's the knowledge gained to date. But we also want to get to know one another, know who's who and the active professionals in the field, and get to know each other's research, and be able to start talking and coordinating together to plan next steps for closing gaps in knowledge and technology. This year, we are going to focus on number 2 a bit more. We're going to be hearing a lot of presentations from this professional community to get to know who's working on what great research. Just wanted to introduce and thank our co-organizers. They're shown there on the screen for you. Actually, is Stephen on today, Patrick?
I don't see him in the list.
Okay, I was gonna.
Steven's here.
Okay. So wanted to specifically welcome Stephen as a new co-organizer from last year, but we have Frida Taub from University of Washington, myself, Jane Shetzoff from, she's a co-founder of the Propagule Space Ecology Institute, as well as a instructor at UCLA. Patrick Grubbs, our IT champion of the day, bringing all of this Zoom webinar, all this technology together for us. And Sherry Damlow, who's a space taphonomist, and tomorrow we get to hear what that means from Sherry when she does her presentation, and Stephen Lanton from the University of Florida. So, seeing how I'm doing on time here. Today, what we hope is that closed ecological systems for space life support won't just be a footnote or a small session in a larger conference, some bygone obscure field. Today, we really hope to immerse ourselves in this topic and really define space ecology as a field of study and establish some unity of vision and purpose. So for all of you who are a little less familiar with what we mean by space ecology, artificial closed loop ecosystems, they also known as closed ecological systems, exploit a combination of biological and ecological and physical chemical processes to support human life. And so by closing this material loop with food production and waste recycling systems, the idea is that a closed ecological system would reduce reliance on Earth resupply and enable indefinite, I hope indefinite, sustainable exploration of space and living on Earth. So really, you can think of a space habitat as an artificial ecosystem in which there's human beings and they're exchanging energy and material with other components in their extraterrestrial environment. So we're defining space ecology here as the study of the relationships of organisms to one another and to their physical surroundings in the space environment. It's basically the science and technology of space ecosystems. Last year, just to review a little bit, we spent some time discussing and identifying knowledge and technology gaps. I won't review all that for you here this morning, but we did some great brainstorming activities that actually ended up contributing to a paper that was presented at the International Conference on Environmental Systems to review the outcomes and proceedings of that workshop. So later on, I'll put a link in the chat to this paper, which I forgot to do on my slides here. But you also have a copy of this in your program, so it kind of gives you a review of the proceedings from last year. And also, if you're interested, if you missed it, last year's workshop is also still available to view on YouTube at the link there, and we can put that link into the chat. So today's agenda, again, we're going to be changing things a bit from last year. We're going to have a lot of speakers, but for the next 2 days, for today through tomorrow. This morning, very excited to have here with us Dr. Cesare Labascio from Thales Alenia Space, who's going to be talking to us about bioregenerative life support and the space exploration revolution. We're going to have 20-minute presentations following that talk. And then have a break. We're going to try out some networking tools today on Zoom. We'll see how this goes. And Patrick will give us instructions for some virtual networking. And then we'll come back for some more presentations, take a lunch break, and then have in the afternoon our featured speaker. We're very excited also to have Dr. Mark Nelson with us from the Institute of Ecotechnics to talk about Biosphere 2. Which happens to be the background behind me for those of you that don't recognize where this picture is from. And then again, we'll continue presentations throughout the afternoon. Tomorrow, we're going to do much the same. We have our featured speaker tomorrow morning is Dr. Carl Aspelan, who is here with us today as well. Followed by more presentations where you all get to tell us all the great work you're doing and all the ideas that you have for this field of study, and get to know everyone a little better. I've already somewhat introduced our speakers for the day, and just a couple of administrative logistical tips for the day. Your all mics are muted. Really, I would love to be able to have us all talk more interactively, but when we have about 100 people online, that kind of might get a little difficult. So that's why we have all of the mics muted. But instead, there's going to be many different ways that you all can communicate with us and with each other throughout the day. In your Zoom, you will have... I have now lost my own buttons. There they are. You will have a Q&A button. During our presentations, if you would like to ask the speaker a question, go ahead and put that into the Q&A and we'll deliver that question to the speaker for you. There's a chat box where you can chat about anything you like. Whatever feedback or comments you would like to give, please use that chat box. And the presenters if you would like to ask a question of a speaker, please use the chat box as well. You might not have this Q&A capability. If you all have questions, please message Patrick, who will try to keep us all running smoothly throughout the day. We are recording this workshop, and Patrick will send out a link to the audio recording after the 2 days. Let's see, anything else? One more thing to point out for all of you who are new to Mural. We love this brainstorming tool that Patrick's going to give a link to in the chat. It's another way that you can communicate your feedback and ideas and questions throughout the day. Feel free to go to this Mural board link and brainstorm and communicate with one another in writing at will. I think you'll enjoy that tool. It's more interactive than a chat room. And we'll give some more instructions on that, I think, perhaps during one of the breaks. And
I just dropped the instructions for joining the mural in the chat. So hopefully you can all click on that link and select join as a visitor, and then you can participate. Yeah, I see some of you are already on there. Great. So again, for those of you clicking on the mural link, join as a visitor. You don't need to log in, just click join as a visitor. So with that, I'm going to hand over control here. And again, welcome everyone. We are so glad to have you joining us today, and we hope you'll enjoy yourself and have an inspiring 2 days with us. So I'd like to introduce Cesare Labasquio, who is going to be giving us our first talk today.
Thank you, Chris. Do you hear me well?
We can.
Great. And do you see my screen as well?
Now we do.
Yes, there we go.
Okay. Okay, great. Thanks for the intros. This is a great workshop, I think, and I hope I can make a great start and provide some ideas, some thoughts, some energy here. First, I'd like to say a word about my company. I work at a large space integrator, a company called Thales Alenia Space, which works basically in every field of space, maybe except launchers, not yet, at least, but satellites in general. But in particular, and I am in Torino, so my greetings from Italy, where it's 5:15. So work in Torino is devoted entirely to space exploration, which have been my career, my entire, let's say, life devoted to that, and I have to say, still my passion. So I'm trying to provide some thoughts, some ideas about bioregenerative life support for the exploration revolution. That's how I called it. And it's, as I said, the perspective of a space integrator. So I am an engineer by background, not a scientist. I am also, let's say, in the company, I've been recognized as senior expert in life support and habitability. Now, I think after so many years that being expert in life support and habitability means like knowing nothing about a bit of everything, because it's like a huge field. You know, I tend to say it's like from A to A, so from agriculture to astrodynamics, astrophysics. It's just too much to be expert there. But given that caveat, I've spent a lot of my career on different projects. And what I have observed in the last 10, 15 years is what I call here a revolution. you see it here. If you were like looking at the panorama of space exploration just 15 years ago, maybe you would see, of course, the International Space Station, but there was, let's say, a blurred view about our future in beyond LEO. Are we going to the moon? Are we going to Mars? Where are we going first? Are we going to asteroids? I think now we have a much clearer vision. And besides that, everything, many things happened in the low Earth orbit developments. And now we are facing a revolution there as well because of the, let's say, entrance of new actors, new privates, commercial actors, which will definitely change the way we go to low Earth orbit, and we exploit it, and we live there. So we at Thales Alenia are quite careful and quite attentive to all these fields, to these trends, and we have a tradition in the ISS, which I will say in a minute, and we are looking at the developments with great attention. So we're trying to be at the forefront in this new low Earth orbit panorama, in the Artemis mission, of course, in the Artemis program, with different projects on which we are working, and of course we still see the closest future, let's say, not so close, but at least after the moon, we see Mars as the next exploration step. So some background on what we have done, and I must say I'm quite proud of what we did in the past decades for the International Space Station. I'm proud to say that we have basically put together, from design to integration, manufacturing, and operations of about the 40% of the habitable volume of the ISS, coming from here, Turin, with any kind of element. Permanent elements like Columbus, the nodes, the cupola, logistics elements like the ATV, the multi-purpose logistics module, which now retired after the shuttle retired, and the airlock. So I think we are really incredibly proud of what has been done, and we can say that everything works fairly well. We had no major failure, and now, counting numbers, we are above 500,000 total hours of flight there. So it's quite much. It's quite impressive. We've also been involved, and this was also one of my personal projects, in transporting potable water to the ISS in 5 different flights of the automated transfer vehicle. So that was quite great. It was quite challenging. I'll talk later again about storage and how we should look carefully about storage. What did we learn? Well, we can all say that we master environmental control. That's definite. For when I say we, I mean both sides of the ocean and more. We know how to control pressure, humidity, temperature. I mean, we can do that. Now we have decades of experience on that. I'm putting here the most iconic module that we built, the cupola, and our Italian astronaut Samantha in there observing outside, taking pictures, great pictures taken by the cupola, and astronauts still very, very grateful of having the cupola up there. But perhaps if the cupola has been the most iconic, the most difficult have been the nodes. Here, node 3, Tranquility. Well, nodes are really complex structures with openings, 6 openings, so that makes them a bit weaker in terms of structure per se, connecting 6 modules, and in specific, node 3 had regenerative life support racks for regeneration of air and water. the toilet, gravity countermeasures, quite challenging indeed, and quite a nightmare for a configuration engineer and life support engineer to put everything together. More than 400 equipment, several kilometers of lines, electrical, fluid lines. You know, if you move something and you decide to do a mod, then you know, everything gets screwed up. It's just quite a feat to put everything together. We did that. It's great. We accommodated the NASA government furnished equipment for life support. So it was not our development, but it was an accommodation there. And now to jump a bit into some thoughts on food, I'd like to share with you this quote which we got from Samantha in 2015. There was like well, that is actually it's a song festival. The good thing is that there's millions of people seeing that on TV, and there was a connection to the ISS, and the guy asked Samantha, "Is there anything you really miss?" And to my surprise, the first thing she said is a nice salad, maybe fresh veggies, some tomato. It's impossible to have it at the moment. So I was really surprised to hear that, and you know, that gave us some let's say some food for thoughts and some, let's say, some energy to go further into food production, which is one of the key elements for us for bioregenerative life support. Despite that, of course, we are mostly resupplying station with the commercial resupply. Cygnus is built here, the pressurized cargo module. We build 2 a year, so we have set up a sort of mini series production of those modules. We know quite well how to make them, you know, affordably and fairly quickly to you know, to meet this challenging schedule. What do we have in future low Earth orbit in terms of ISS and commercially? Well, already on ISS we have a commercial airlock which we built for Nanorex. We have and we are building now the new modules, the 2 ones for Axiom, that will then become, you know, an independent station. So we're going to see really an evolution of low Earth orbits, and the fact that we already see commercial activities there was interesting for me to show you one example, which may be considered just a small example, but of how privates can get interested into using the ISS in a different way than just you know, doing experiments, or a different way to fund them actually, because this was a customer, Space Cargo Unlimited, which had the idea to fly, you know, 12 bottles of wine, and not just a regular, you know, whatever wine. That was Bordeaux Petrus 2000. So it's just an incredible wine. And the idea was, okay, we want to put it in microgravity for a year and see when it comes back how fermentation was affected, how, you know, how it tastes, and so on. And it was done just with private money, so there was no public money except the launch, of course, that was given. But the interesting thing was that all this research was paid by selling one of those bottles just when it was back. So I know it may be considered just, you know, not so pure in terms of science, but it was, to me, a nice way to show how you know, privates can get into the picture, and probably this will be even more happening in the next few years with the commercial LEO destinations in development. You know about Orbital Reef and Starlab. Now, actually, last week, I think there was the announcement that Northrop Grumman, our customer for the Cygnus, is going to join Voyager for the Starlab. So those human platforms will be avenue to many developments and will host life support systems, be them classical, regenerative, bioregenerative. That remains to be seen. On top of that, we have some automatic platforms in development in Europe. What you see here is called Space Rider, hosting about 1 cubic meter of cargo bay payloads on for like 2 months in orbit and re-entry, giving the possibility to do research, development, manufacturing in different verticals. And how to talk about revolution without mentioning Starship. This is probably the most important revolutions going to take place in the next decade and more. And this will mean a much higher capacity to LEO, capacity to the moon, 10 times more capacity basically, and perhaps 10, if not more, times less cost per kilo, even 100 times maybe less cost per kilo. So that is going to really drive a revolution. We still need to understand what that means in terms of space ecology and regeneration. I'll come back to that in minutes. But the great next step beyond LEO is, of course, Artemis. Is of course the moon. We are going to the moon to stay, to learn, and it's going to be an international endeavor. And we believe we are doing good there as well. We have actually a major role in the Lunar Orbital Platform Gateway, in which this time we are basically realizing all the pressurized parts. So be it as prime within the so-called IHAB, the International Habitat, in which the life support system, which is partly regenerative, is made by JAXA, a Japanese agency, but also in the HALO, which is the Habitation Logistic Outpost. Prime is Northrop Grumman, again, our key partner in Cygnus, and Esprit, in which there is also pressurized element. Not to forget that we are as well working hard and for the Orion service module, which is the European contribution, and we are doing consumable storage subsystems. So we are doing, for example, water storage and gas storage there. We are not just going to the moon to orbit around it. We are, as you all know, we are going to put boots on the moon, and in that framework, at the moment, we are mostly active on the European Large Logistic Lander, the EL3, which is a cargo lander, and we are working in a bilateral between the Italian Space Agency and NASA on what we call the multi-purpose habitat for surface, which may be the first permanent small habitat on the surface of the moon. Perhaps it may have some wheels, which are not shown here, to move a bit around. This is still to be decided, but we are quite excited to use our expertise that we built for orbital systems on surface ends. What may look like in the future? This is a pictorial by the European Space Agency. Is of course a much larger outpost. You see in the picture some green stuff here. Okay, maybe it's not going to really look like that. A greenhouse may be buried or look quite differently, but it's interesting to see that let's say the agencies are considering that feature for permanent long-term habitation. So back to numbers and life support. The numbers you know quite well, better than me. Life support for space exploration. What can we expect? Well, if today on a station we regenerate air and water quite nicely, and we are just starting to do demonstrations for, let's say, food complement in terms of growing crops there, simple crops. Most of the activity is still research in microgravity, on plants, on food, with great benefits on Earth. But most of the, or a large majority of food is resupplied by Earth with the Cygnus, with the Dragon. Are we going to see a green transition when we go to the moon and when we go to Mars? I put a question mark because I believe it's still to be. I'm personally not certain this will happen or when this will happen. Let's consider that of course the moon has resources. The Mars as well has resources, in particular water, which we can extract, and that could be already a great advantage for life support systems. But what about the green transition? And I usually put up this slide in my talks, and also when I do lectures, and I'm typically saying, okay, International Space Station, low Earth orbit, 400 kilometers. We are going to the moon. Yes, way more distance. We are going to Mars, tens of millions of kilometers. Resupply mass, cost, and time is increasing. So we will have a transition. Less or storage to physical-chemical regeneration, air and water, to bioregeneration and food production. But then at the same time, when I say that, and I put up the picture, I have millions of questions. And actually, I ask the students the questions: are you really convinced on that? First, when we talk about mass, cost, time, is it the same thing? How do we measure it? We typically talked about mass for a long time, and equivalent system mass. We have tons of papers on that. When it was the time when the cost of launch was really, really high, and therefore it really was let's say proportional to cost. But what about now? If the cost of launch is going to decrease dramatically, is it still a good equation? What about the cost of development of technologies? It takes time. It takes so it's a schedule impact if you want to put a regen technology on board. So all these kind of decisions need tools. We are developing new tools. We are studying new ways to do this kind of evaluations. Life cycle cost analysis, for example, is probably more accurate than ESM, for example, in taking this kind of decisions. What do we want to develop? Where we want to invest? And another, let's say, area in which I think we need to have some more thoughts, or we should be careful, is about we shouldn't see this as a sequence like storage, regeneration, bioregeneration, but rather we're going to have storage. I mean, even a bioregenerative system will have storage. Our ecosystems have huge buffers. We need those. And do we know how much storage we need? I think we are really unclear yet on this kind of simple questions. How much storage is necessary to have a sufficient degree of safety, reliability in our missions? Which are the best first technologies to put in place for regeneration? Probably water. Yes, for us, a must is to work on water regeneration. From water, you can relatively easily get air as well. When is it good to transition to food production? What is the length of the mission? How many crew members? Isn't there the risk that we never get here? It's not convenient, so we put it back and back in the future. This kind of questions we ask ourselves, and I don't really know. I'm also asking you if you have ideas, if you have your own answers to that. given those open points, we're basically working on two main pillars or two main fields in regenerative life support. Water, I'm not going to mention here much of it, but I'm going to say a few words about food production and crops production in space, in which we like to see what we call a stepwise approach. We believe there's, and this may be valid for other bioreg life support technologies, by the way, we believe there's demonstration and there's industrialization. Demonstration is demonstrating feasibility. We may say easily today that with G and other planned facilities which flew in space since decades, we know it's feasible. That's not a question anymore. But is it reliable? I mean, to be food production, this is not research. We want to feed people, and we have to do it reliably. And if we want to put, let's say, less storage and more food production, we have to be sure that this is reliable. So not a trivial step here. And yes, several projects ongoing for that. In Europe, we have what we call PFPU, which is in the Melissa program. And but this is not the last step. We are going to be asked to be affordable, to be convenient, so to optimize our system. Once we know it's reliable, we will have to make sure that we can afford it, which is good for a given mission. It's costing less than stored food, for example, whenever this is possible, because you may submit that for Mars, the storage time for food is so long that we may have to have fresh food anyway. And finally, to make it sustainable in time, to make it sustainable in the whole mission, in the whole picture of the different systems, integrated with the water loop, with the air loop, with the substrates regeneration, and to make it really sustainable in the long term. Just a few examples on how we're doing for some demonstrations. First, and I think maybe one of the most interesting projects in the last few years, the Eden ISS, in which we demonstrated technology for food production space analog in Antarctica, which is a psychological analog for sure, isolation. It is a logistic analog. Again, for isolation, difficulty to reach the place, similarly to maybe the moon. In some cases, maybe even seem more difficult, as well as a microbiological analog, fairly pristine place where there is almost basically not much external contamination, similarly to the moon, perhaps. So the project is now finished. It was at Neumayer Station in Antarctica. Great place. The teams produced several hundreds kilos of fresh veggies for those who were staying there in winter. There was one of our racks in the Eden ISS facility, which is now back in our labs in Torino. So, building on the experience of the Eden ISS rack, we are now building the precursor food production unit, PFPU, within the Melissa program for the European Space Agency. You see here some developments in our lab, and here this is very recent, still data being collected and let's say under evaluation. Growing potatoes, so we're growing probably the most difficult crop possible. So we'll be sure that we'll be able to grow other stuff more easily, but we are doing parallel projects as well, for example, on microgreens. So much easier stuff to grow than tubers. What do we see in terms of scenario and vision in the next few years? We believe the ISS will continue to be used for space demonstration of key subsystems, science, and some complementary food production. We we really see with interest the commercial LEO stations with different customers and user needs, and that may host already some work. We're actually working with some startups as well there, like Space V, which is led by an Italian astronaut, by the way. So we're helping them to develop an adaptive salad machine. About the Gateway, well, Gateway unfortunately is not doesn't have a lot of room to do experiments and to do even less to do food production. We can be glad if we can have some demonstration in preparation to exploration, like exposing some samples to the radiation environment. While of course it's going to be the interface, the first real place in which we believe there could be not just a dietary complement perhaps, but more life support related crops being produced. Finally, looking at Mars. The Mars Transit Vehicle could be indeed a program in which some supplements, micronutrient supplements by a food complement unit may become really, really interesting in the long term. I'd like now to wrap up and finish. And before thanking you for your attention, I've put on this chart some suggestions. What we called a SWOT, a strengths, weaknesses, opportunities, and threats, looking at space ecology, looking at bioregenerative life support, which is what we all love. But it's good to try to list not only where we are strong, but also where we are weak, and opportunities, and as well as some threats. Now, of course, this is just to open a discussion. It is not a complete analysis. It is just a fruit of some discussions in the company here. Just those back of the envelope things you do when around the lunchtime with some colleagues. So totally open to discuss. I'm going to mention some points. I believe that the strengths are, for example, given to the purpose. The purpose of all this is quite noble, it's quite holistic, it's natural. At least that's my view. I think it's great. It sells also great. However, it's hard to demonstrate convenience. And when you talk to the technical people, to the mission planners, okay, this kind of vision starts to be more blurred when you run into the practical problems. I believe there is a great and competent scientific community. You guys, we all of us. However, we are still small. I think sometimes behaving a bit as a club. May agree, may disagree. In terms of Europe, I think we have a strong program, Melissa, but we are not flying enough demonstrators. And that's a shortcoming, I believe. In US, there is much more flight experience. I mentioned Veggie, APH, and other experience and demonstrators. Reliability, still weak. And maybe it's more perceived reliability than real reliability. That is, when looking at biological systems, people are, I believe, a bit biased in negative. Another strength is the possibility to use analogs, the use of analogs. I think it's great, at least in our experience. Weaknesses. How much storage do we need? I don't think we can still be clear on that. I was talking to astronauts this week. One of them said, okay, we're on ISS. We still have to eat food which is becoming a bit old because we have so much stock. Because to be sure we still have food. The stock is bigger than the consumption. So I mean, these kind of things. How much storage do we need to be safe, but also to use resources carefully and well. Psychological impact. There is a positive side. For example, some elements like plants seem really to have a positive impact. Some, okay, bugs, okay. Does it really, have? I believe, I perceive it as negative. At least this is what I hear. Another strength, it may seem a weakness, but there are gaps. Okay, that is a weakness, but the gaps are well identified, I believe. And what is less well identified, this is my view again, are the priorities on filling those gaps. At least this is what I feel when talking with scientists about gaps. It's hard to relate them to the mission. What is more urgent to be done? What are the priorities? Opportunities and threats. I mentioned Starship. We may mention New Glenn. Future of large launchers, 8 meters diameter, 100 tons more in LEO, lower cost of access to space. That's an enabler. It's a big enabler. So it's a great opportunity. Yes, but there is an equivalent threat. This is, again, my view. Is it becoming a dumping enabler? Is it becoming something that will enable, okay, more storage and more dumping just because, it's costing less and because there is no such thing as a waste tax? Maybe, I don't know. Up to your judgment as well. Other opportunities, commercial LEO programs, I think we should really see them as opportunities. More opportunities to fly, maybe fly fresh food. Europe, again, there is an opportunity related to huge programs that have been launched on sustainability, green economy actions. However, in Europe, we still have a big lack. We are lacking a human launcher, which is a major lack for Europe. And that's something that may drain a lot of resources in the next decades because we're still lacking that one. Another opportunity, I believe, is the emergence of emerging startups. There's a few which are starting to work actively. On the other hand, I put here incumbents work in business as usual. It's the opposite of innovation, And I think we can do better. I believe. Non-space companies, I believe, can be a great asset. We are talking to some of them, for example, some in the food industry, getting interested in space. On the other hand, when talking to non-space companies, I do still see a lot of ignorance on space benefits, on space in general. What is space? What can give me? What are the benefits? They all think it's a huge cost. So I think we have a great deal of education to do there. New expected discoveries, products, yes. This is a belief. Okay, of course, when something is new and unexpected, you cannot really predict it, so you cannot really defend it. I'd like to finish just comparing two things which struck me in the last month. One is, I call it an opportunity, one a threat. And the opportunity is depicted in this article, which is Thriving in Space, Decadal Survey, published in September 23. Great things about bioregenerative life support, the importance of it, what should be done. On the other hand, another article, Scientific American, October, very fresh, Why We Will Never Live in Space. Well, don't stick to the title. The title itself would deserve, I think, a PhD dissertation for, and I'm talking about a communication PhD, not a scientific PhD. When using the word never, you're trying to manipulate your audience. This is well known. Who is we, is just us, is the whole humanity. When today, in 3 centuries from now, in space where? I mean, we're already living in space. Are we referring to traveling? Okay, these things get, I should say, a bit more clear when you read the article, which is actually a great article. So I invite you to read it. It's and all most of what is there makes a lot of sense. However, I think the title was not well devised. I'm done. I really thank you for your attention. I just want to finish with some add-on which I put to the per aspera ad astra motto, which is per aspera et per legumina. So with some vegetables as well, we'll get to the stars. Thank you very, very much for your attention.
Thank you. Wonderful talk, Cesare. Thanks. We have a few minutes for some questions. Patrick, I'll go ahead and jump in, and then maybe you want to do a couple questions as well. Well, actually, I'll handle the ones for now. First one I'll go to is a question from Priya, which was in the chat, not in the Q&A. She says that she sees green veggies and now potatoes, vertical growth possibly for wheat, rice, and other grains. They're the basis really of our current food, but you need horizontal space for potentially other crops. Priya, maybe I'm misstating your question, but I know you wanted Cesare to share thoughts on horizontal versus vertical growth space. As someone that cooks a lot, she says she would need a lot of herbs and spices and salt. So thoughts on horizontal versus vertical and what kind of crops?
Yes, that's a great question. I believe I was discussing this actually with Franco Malerba, this astronaut, just yesterday about volume versus surface, how volume is important, how surface is important. Actually, these guys are doing really an interesting work because they are working. I mean, it's not really new, but what they're doing is automatically adjusting the height of the trays, or the height of where you grow plants. Again, it's not new, but there's a lot of challenges there, like the closeness between the LEDs and the plants, creates some harm to the leaves in some case. The conditioning of the airspace, the volume on top of the canopy is another challenge. So yeah, perhaps we should think of completely different ways to grow crops. My thinking is that we are really doing, I believe, most of the food production, crops production will be for surface applications. And in that case, something more traditional can really work as well. My thinking. I don't know if I answered the question, actually.
I guess what I was saying was that the wheat and rice and such things need a lot of space. You need to grow laterally. So when you're enclosing it, you need a lot of energy. So the plants that you're showing, I see it are totally viable in that space. The things that we eat bulks of, unless we change our diet, which we could, there's the gluten-free diets and such, where maybe there isn't so much necessity, but people like me like my wheat. So
well,
we may have to make some choices at some point to restrict ourselves to crops that are more fit to the constraints of growing in space. And there's ways you can make it work for certain ones, but certain might not be really well suited just because there's perhaps a lot of inedible biomass that you're dealing with that's not very efficient to grow. So yeah, you might need to start looking at changes in dietary plans that fits those constraints. So sorry.
Yeah, that's absolutely true. I think again, I have to submit, we have a more, let's say, industrial perspective. So we are maybe looking at shorter rather than very longer term. We are not much looking into cereals, for example. We are looking first at simple things, fresh, leafy crops, for the psychological value, for the nutritional value, for the micronutrients. we are not really seeing like a whole vegetarian or vegan diet, which, of course, needs carbohydrates and much more, being really close in time. So that's why we are focusing on microgreens. But you have seen the potatoes, so you may say, okay, but that's that's carbohydrates. That's yes, actually. I think the choice of potato, and this is made by the European Space Agency, is because it is possibly the most difficult one to grow. Here we have much better specialists in this, or me on that. But we are experiencing ourselves how difficult it is to grow potatoes. But at least when we know how to do that, we know how to control microbial contaminants in the root zone, and all the rest, we are going to be fairly sure that we can grow radish, for example, and we can grow many other crops. So yeah, maybe it's a shorter term focus that we are putting together at the moment.
Okay, question from Ray Wheeler. How important is it?
Hi, Ray.
How important is it for us as a bioregenerative community to show how we will integrate with existing ECOS technologies as missions evolve? How important is it to show how we will integrate with existing systems?
Well, that's tough. I think we really have a poor level of integration at the moment of bioregenerative life support. We have really few examples. We have some which are open. Are you asking me something more?
Oh, nope.
Sorry. Okay, no, sorry, because there's just a delay. So I believe that this step is a crucial step. It's something that I believe will come a bit later as well. I mean, we tend to believe that feasibility first, reliability second as a building block, and then there is like the next steps into getting this all integrated into the cycle with other systems, like the water regeneration, for example, like condensate recovery. I think we are a bit far from that. I don't know if I got the essence of the question, actually, Ray. Maybe you can comment as well what you think. You are the guru there.
Yeah, I don't think we can have Ray comment audibly at the moment, but maybe we can continue that in the chat.
Okay.
I have 1 more minute before we start with Dr. Porterfield's talk. However, one more question that I think is important from Craig. How do we convince for those of us, I would say, working in technology development companies or commercial space, convince our program managers that they should take a budget or schedule hit in the beginning of a program to implement closed ecological life support systems? How do you convince your program managers that this is important?
You can't.
You can.
Well,
and with that, hello, Marshall.
Because they don't have the money.
Then ciao.
They don't have any money. They can't.
Okay.
No, it's true. I think we have to take from the startup world. We have to take an approach which is to start small, to think big but start small. We have to start with simple things, and we have to put them in at the first with as demonstrators, proof of concept, simple things. I think in that veggie is a great example. Something that has been there now for a bit of time, and is demonstrated that we can grow, it's feasible, and then you do the next step. So be very, very cost efficient and cost savvy. I can say I could say much more on that, but our time is gone.
Well, thank you. If you have a few minutes, Cesare, in the question and the Q&A, you might be able to answer some of these questions directly. Some
I'll
are pretty
try. Yeah, sure.
challenging questions, and I may take a stab as well as in the chat. And our next speaker, I'm very happy to welcome Dr. Marshall Porterfield, who's going to talk to us about bioregenerative habitation and omics infrastructure requirements for deep space bioastronautics. Welcome, Marshall.
Thank you, and hopefully my presentation will kick in here.
Looks like we can see your screen.
Nice. Should be slideshow. There we go. So I'll start off.
We can see your presenter view. Maybe swap. Swap presenter view.
I don't know how to do that.
Okay.
I'll just do it this way. How about this? Is this okay?
Sure.
Okay. First, let me just start off and tell you a little bit about myself, since I don't know everybody in the audience here today. I started off working in the cells program and space biology as a graduate student about 30 years ago. I was working on hydroponics and hydroponics for controlled ecological life support, and also was working on space flight results and plant responses in space flight in the CHROMEX series of experiments. And I worked out of Kennedy Space Center in the cells program in the summers. After my PhD, I started focusing more on sensor work, focusing on biophysical sensors to be able to study indirect effects of microgravity and biophysical parameters of the space flight environment, how that affects space ecological systems. And then also I spent 5 years at NASA headquarters from 2011 to 16. And during that time, I established NASA Gene Lab and the Twins Initiative. So I've been thinking about humans in space, humans in space life support, bioregenerative life support, from really kind of an ecological, practical perspective for about 30 years now. So when we start looking at controlled ecological life support and kind of the history behind that and the different elements of consideration, really these are the issues that are becoming more prevalent now as we're starting to change the direction of our space program from really ISS and low Earth orbit towards greater destinations. Let's put it that way. The moon is probably our next target for a lot of reasons. And the work that we've done in the controlled ecological life support program over the last 30 years, the work that was done at Kennedy Space Center, is going to be much, much more relevant as we start to move into this era. And I have this picture here. This is an artist's rendering of an idea of what a lunar habitat might look like in the future. And I think our ideas about what that habitat, this next phase of Artemis, probably this is pretty accurate, of a habitat with some kind of add-on with plant production in it. Maybe not a complete ecological system yet, but maybe that's really the direction we're going in, because you start thinking about these greater destinations, we've got greater challenges that we're going to require bioregenerative capabilities and really a merging of interdisciplinary life sciences across human health, agriculture, and ecological systems. And that's really the omics foundation for these systems. But before I get into that, let's just kind of review again what our human ecosystem, each of us is an ecosystem in our own right. We contain multitudes, right? We contain a microbiome. Microbiome sciences is only like 10 years old, right? We only did the first microbiome project on a human being in space 10 years ago in space. Before then, we didn't have the capability to do any of this type of work. But when you really start thinking about the logistics challenges of human beings in a spaceflight environment and what that means in terms of daily needs, it starts to become relevant and evident what the challenges are. And I think it's important to keep this in mind, because what we're trying to achieve in space in terms of bioregenerative systems is exactly what we need to achieve in our ecosystems here on Earth, and that's bioregenerative balance between our human systems, and the global ecosystem. So I talk about bioregenerative life support sometimes as a challenge where we have to replicate the functions of the planet without all the buffers. So let's kind of think about this challenge of the impact of these technologies back on Earth. That's actually relevant when you think about the argument about why are we even going to space. I'm sure we've all heard this argument about why do we go to space? Why are we even doing this when we should solve the Earth's problems before we go to space? And my answer recently has become, well, we don't have a choice. We've already messed up the Earth. We're probably going to have to re-engineer the ecosystem of the planet now from where we're at. And this is and I cite literature, right? Here's a paper, a PNAS paper recently in the last 2 years have been published, a global biomass of wild animals. This is an inventory of all the animals on the surface of the planet. This is humans, and this is our food. There's not much left of mammals on the planet. So if we're going to wait, if we're waiting to solve all the problems on the planet before we go to space, tough luck. It's too late. Another example, global human-made mass compared to global biomass. There's more human-made mass on the planet now than there is natural biomass. So we do face a global ecosystem challenge here already. And we're going to have to develop ecosystem-based technologies in order to solve our global ecosystem challenge by leaving the planet, by developing bioregenerative life support so we can leave the planet and save it. That's another way to look at it, I think. And especially now that we're so metal hungry with our new electric cars, we're going to need lots of metals and resources for this new economy that we need in order to save the planet. Well, maybe we need to go to space for that. Mining in space would represent a real outlet for human civilization, and maybe that's what we need from a ecosystems perspective. So when I think back of what we did in the last 30 years at Kennedy Space Center and the work that was done, it's really amazing. It's also amazing in the fact that NASA just cut everything in 2004, wiped out these programs. But we do have a commercial vertical farming industry that's emerged that really represents kind of a foundation of technology. This is the greatest spinoff of NASA's history, actually. The greatest spinoff that the NASA never claims is that spinoff of vertical farming. And this is going to have massive impact now. Economically, it's already being seen, but in the future, people kind of discounted some of the problems with the vertical farming industry recently with financial issues in the industry, but those are going to be buffered out, and in the future, this will all move forward. So where are we at now? We've got basically the foundations to do some of these kinds of capabilities, and we've established and started emerging omics capabilities. GeneLab was really the omics investment that NASA made. That's a platform for our life sciences and human research program now. And so based on this platform and really all the lessons learned of the past in terms of NASA research from the cells program and how that's being applied to the CEA industry, it's just had really a tremendous impact in terms of a foundation for future engineering of these more advanced habitats. Really the challenge in these habitats is in working in the spaceflight environment is really the challenges of dealing with space, and that is radiation and microgravity. Depending on whether we go to Moon and Mars, we're facing deep space radiation for the first time in 50 years. And also we have to deal with microgravity and deal with all the other instrumentation and indirect effects of microgravity and how that impacts our hardware systems, fluidics, pumps. That's really the main area of research I think that we really kind of overlooked over the last 20 years is really looking at indirect effects of microgravity. That's important for distinguishing from radiation effects, which we still don't control for in our experiments because we don't readily fly centrifuge controls in our spaceflight experiments. But really these, the indirect effects of microgravity from a ecosystems perspective, and that how that affects living systems really needs to be considered. And that's, I think, an area where a lot of the young scientists in the audience really ought to think about biophysics and biophysical systems and buoyancy-driven convection and how that affects ecosystems and the functionality of ecosystems. Really, it's a biophysical issue associated with microgravity. You have to deal with these issues of diffusion, thermal regulation, and things like that on top of the radiation issues. So you really need to be able to create the framework for the biophysics to separate these stresses so that we can study and understand them better. So really, what we're, in terms of next generation spaceflight systems, and when you think about a spaceflight system as being an ecosystem, and that's really the approach I'm taking mentally and conceptually in terms of the way that we approach this in terms of bioastronautics. Humans in a system, in a habitation system that's being delivered to a location for exploration, bioregenerative capabilities, the human in the system, you have a human health, precision medicine, personalized medicine, then we have the agricultural component in the system, and the ability to do precision agriculture now and using omics in precision agriculture. And what unifies the human with the crop system is the microbiome ecology of the human microbiome and of the soil microbiome. Really, that's a unified science. We just haven't connected them together in the right way ecologically so that we can use that as a foundation for bioregenerative life support. That's really the next one of the major frontiers for ecological engineering in these systems is that level of work. Microbiome engineering the microbiome of the human soil crop system as a living entity, as an engineered system. That's really the challenge there. And it encompasses human medicine, crop and soil systems. We're learning so much about that connection between the soil microbiome and the crops and the medicinal value of some of the foods that we eat. Actually, the compounds that have medicinal value are made by the microbes in the soil and are given to the plants, and the plants absorb them. And then we harvest the plants and use those as our medicines. And it actually comes from the soil in the beginning. And we're just starting to learn these things. We're just barely starting to understand some of these basic concepts. We're going to not learn them and then try to leave the planet, without that vital information. We're just at this critical junction now where we're just on the verge of being able to learn and understand these things now that we have these new omics capabilities and these new omics research capabilities. And that's really what we need. These are frontier areas for science. These are frontier areas for engineering and technology development. So again, omics is an integrator, is a controller for bioregenerative and ecological engineered systems. That's really a primary area of focus in terms of enabling these technologies in the future. So with that, I'll stop here and I leave plenty of time for questions. I know we have a busy session today, and I'm looking forward to questions and hearing from the other speakers in this workshop. So thank you so much for this opportunity and your attention.
Great talk, Marshall. Thank you. There was a question actually from the prior talk that I thought maybe you might like to comment on. George is asking, do we have a prediction for where we think closed ecosystem technology will be in 5, 10, 20 years? What's our prediction of the technology's timeline? And I'm curious what your response to that might be, Marshall.
That depends on what kind of research infrastructure we have moving out into the future. Really critical piece is actually to have a closed system that we can put humans in. We do not have that kind of research infrastructure where we can actually have a fully closed with gases and really close in and with the infrastructure and capabilities to study the microbial ecology in those systems. So that would, to me, it really, we can make progress if we have the capabilities, we have the investments. So how do we going back to the one of the other previous questions, how do we get the government to invest in these areas of importance and the agency to invest in these areas? Don't go to your program manager because they can't help you. We have to go up further upstream. We have to go to Congress.
Dr. Taub asked a pretty loaded question in the chat a few minutes back. Rather than read the entire question, Frida, if you don't mind, I'll paraphrase for you. But I'm wondering, Marshall, if you can provide your thoughts on the role of international collaboration versus international competition, and are we in a new space race?
Yeah, we're in a new space race. The only reason that's we're getting any attention on this is because the Chinese have been advancing it.
Well, that's something from the brand level that's being looked at. Yeah, and I could go all the way up, higher up.
I don't know, someone's talking, we can't really hear you.
Oscar, can't hear you very well. I don't know if
All right, he was talking to someone else. That's all right.
Oh, okay.
Cubicle.
Anyway, continue, Marshall. Sorry about that. I don't know if you wanted to say anything else about the competition.
This is something I deal with and think about a lot too, because in my role when I was at headquarters, I was actually seeing the earliest examples of the Chinese program moving into this area, and I was trying to make the agency aware of that. And at the time, I was a division director. I was head of space, life, and physical sciences, and no one cared. So it's not enough competition. Once they have a moon base up there, then they have to do something. It's kind of like Sputnik. Once the little sphere flies over your head, and you can hear it turn on your FM radio, and you can see it flying across the sky, and you can hear it beeping. It scares the crap out of you. Then you have to do something. Then that's when we'll do something.
Does anyone else have a last question for Marshall? I apologize if I've missed anything. Okay. Oh wait, we might have another question. Oh, wow. We have 1 minute, so this is a tough one to answer in 1 minute, Marshall, but if you're still there
I'm
you
here.
are. Okay. What's your opinion on the impact of microgravity on the evolution of virome and viral disease dynamics? That's a long question to answer, but
On what?
Evolution of viruses, disease dynamics, and the impact of microgravity on that. But that could be a whole day to talk about. But
Well, we're actually doing some biophysical modeling now of human respiration, and based on that, I could make some comments about virus dispersal in microgravity and gravity, but maybe not any like long-term predictions. But yes, in terms of indirect effects of microgravity and understanding the fundamental biophysics of the indirect effects of microgravity, there are a lot of aspects of respiration, fundamental respiration, photosynthesis, fundamental biochemistry of organisms that are not understood. It's not understood the connection between those processes and gravity. It's not completely well understood. And we're going to see those features challenged as we move these ecosystems out into space. These will be features that will be studied and understood better, yes.
Confounded much by changes in fluidic flow, convection, and gas exchange, and all of those.
Those are the most confounding issues in space because yeah.
Okay, I think that's all the questions we have time for. I'll go ahead and bring in our next speaker, Davy Souza is going to be presenting on advancing space ecosystems with bridges.
Hi, everyone.
Davy.
Thank you
Hello.
for having me.
Nice to see you.
Same. Can you see my screen? Hi.
Yes, yes, we can see your screen.
Okay. Thank you, Christine. Well, hi, everyone. Good afternoon, directly from Brazil. It's a great pleasure for me to be here with this amazing community and to present the work that we have been conducting on this Space Ecology Workshop. The work is entitled Advancing Space Ecosystems with Bridges. This is a result of my collaboration together with my colleague, Tarun Bandemegala. Since now, I hope you appreciate the topic. This is the agenda and the topics that I'll be covering in the next couple of minutes. And giving you the scope of this work, as most of us already know, we are dealing with this increasing enthusiasm for long-duration crewed missions. Together with that, we are also looking to establish some self-sustainable bases or habitats on the Moon and Martian surface. But once we start talking about these habitats, we also need to provide a self-reliant environment. This will be within a complex architecture that will allow us to sustain life in the celestial bodies. But what we have so far, as Cesar mentioned, and also Dr. Porterfield, we have a lot of current environmental control and life support systems capabilities that are operating, for example, right now at the International Space Station. And they are mainly based on physical-chemical process. But once we start talking about self-sustainability, well, we also need to think about food and food production, especially. Because if we are considering the dependence of the terrestrial resources, this will become impractical. And no matter if we are decreasing the launch costs, if we still need to send food to space, this will increase the payload mass and consequently the costs. Considering all of this scenario, we are also taking into account the historically evolution and the collaborative problem solving on the control of the environment agriculture, the CEA sector, and the application of this sector in space, which we are relating here as Space CEA. And this has resulted in some notable technological breakthroughs, such as the LED lighting systems and the vertical farms that was well presented in the last presentation. Now, introducing you about bridges, this is just the acronym for what we are considering our biologically reliable integration and design for growth environments in space. This is a project that emerged as a methodology, and we are aiming to understand the synergies between the biological and the physical-chemical process within a space ecosystem. And as you can see in the figure provided here, to build this methodology, we are considering the base of this pyramid as the biological environment and the architectural environment. And once we integrate all of this with the ecosystem, we can build and we can deploy an atmosphere that will be adequate for humans to live and plants to thrive. But to make all of this possible and to operate in the most efficient way, we all know that environmental control is more than necessary. That's why we came up with this objective to deploy a reliable and scalable system that will allow us to produce food in a variety of environments, no matter if we are talking about space analogs, extreme environments on Earth, and also space stations, Moon, and Mars. But what we have achieved so far, Bridges has become a both simulation tool and a control system too, because we are using some simulation data to train the computer of our control system to handle the changes of flux on Mars and on mass and energy during our experimental process. It will also rely on available technologies and its capabilities that will be integrated with some software controls to ensure us to meet the desired operational settings. Some of examples of these settings are the adjustment of the environmental parameters to the adequate levels, both for humans, and for plants, in order to meet the required set points. And also, we are considering the precise control of the growth factors to provide an accurate management of growth conditions. And to make this feasible, we also need to ensure a continuous or optimally a real-time monitoring of our environment. And considering what we have achieved so far, we started looking for some gaps that we could address with some of these capabilities that we are envisioning for bridges. And that's why I want to present here some of the gaps categories that was highlighted in the gaps list by NASA Spacecraft Production Project. They have highlighted the 3 main domains of gap categories, which are the ecosystem domain, the crops domain, and hardware system domain. Specifically for this work, we are considering three categories of the ecosystem domain. And with that, we want to address the multi-crop interaction, the human-plant interaction, and the stability. And it's important to mention that this was a list made it until the year of 2021. We might have some new projects that are happening now. And by that year, we only had the total number of 6 projects in these 3 specific categories. But we needed to narrow down. If we want to make this feasible, as Cesare said, we need to start with small steps. That's why we have highlighted some subcategories in each one of these categories. And I want to present you here. The first one is the lack of knowledge on specific crop type interactions in the spaceflight environment, both beneficial and harmful. Also, we have the lack of automation and crew time strategy to maintain the plant environments. Finally, we have the lack of knowledge of ecosystem stability during planet mission durations. And what we are doing with bridges to address these gaps. The first one, we started to characterize the systems in their interdependencies with the cultivation environment. And as you can see, the top figure, we have delineated what are the interactions between our main system, our central system, which is the plant growth unit or PGU, and the subsystems, which are the illumination system, the atmosphere management, and the nutrient delivery system. On the physical domain, specifically on physical capabilities, we are establishing a comparison of hardware systems performance in specific growing scenarios and structures. And we are envisioning, as you can see in the second figure. And with all of that, we can start conducting some evaluations on the impact of different species on the microclimate. Now, talking about the human-plant interaction, we are studying which is the best strategy to define the levels of automation, considering not only the plant's response to the environmental manipulations, which we know that is very important, but also we must take into account the necessary tasks, what is desired by the astronauts, and then the system capabilities. And this is briefly highlighted in this diagram provided below, because we can have the automation level, which is a feature that will be our main goal, that we are looking for semi-automated or fully automated capabilities, but we also need to look on the tasks, which can be auxiliary, cultivation tasks, and monitoring tasks. Finally, we can consider the features on the hardware, such as the automation type and the mode of control, and with all of these integrated, we can ensure that our system will be operating in a smart manner. Now, on the stability domain, we are developing a model to monitor and efficiently control the air mass fluxes based on 16 hypothetical plants. So as you can see in the graphic here, we have the baseline in orange, which is the amount of oxygen produced by one of these hypothetical plants. And imagine that we are putting not only one plant, but 16 of these plants in our hypothetical system our ecosystem that can ensure the best interactions between the plant and environment, that we can have our optimal capabilities on our hardware systems, and together with this, we can ensure the best levels of automation. With all of this, we can guarantee that the 16 plants will produce the necessary oxygen to meet the demand for 1 human per day, as is shown in the gray line. In the same perspective, we are evaluating this for the CO2 removal. With the same 16 plants, we can meet the necessary amount of CO2 to be removed in this environment, because we have the line in yellow that is the amount of CO2 produced by 1 human per day. And considering this approach, we are also evaluating how these plants can interact with the environment once incorporated in a life support systems, which means that we should conduct a better analysis on the time domain. As you can see, we started looking on phased cultivation with some delays between each phase of cultivation that will allow us to ensure this desired stability on the long term. Finally, to conclude this presentation, we know that to achieve that, we should start prototyping standardized plant growth systems with different technologies, scale, and maturity levels. Then we should start deploying these reproducible structures that will overlap both CEA sector and space CEA sector and this facility and its facilities, together with the adaptability to the context of space analog research, which means that we should also conduct the analysis not only in the space analog research, but also in the CEA facilities, commercial facilities, that will allow us to have more data and more outcomes from what we are expecting in this data. Then we should look on to provide the operational and the technical models for implementing a phased CEA to transform the physical chemical process into regenerative ones. And what are the cost implications of all of this? We are being able to have a breakdown of costs during the life cycle of a life support system to make possible the transition to a more sustainable system in space. Then our next steps is to test the operational model that I showed you to evaluate the failure modes and predict the mass and energy requirements in real scale applications. And this will lead us to to deploy and to develop an economic model to reduce the mission costs and also the need for resources while we are building large scale crop growth systems. Finally, I want to mention that with bridges, we are looking to advance the current life support systems capabilities that will allow us to reach the threshold of the future bioregenerative systems in space. That's why I want to invite you all to let's build these bridges together. Thank you very much for your time. These are the references of the study, of the work, and we are open for questions. And if you might be interested to know more about bridges and even to collaborate with us, feel free to reach us out. Thank you.
Thank you, Davey. This is very exciting work.
Thank you very much.
A couple of questions for you. Stephen is asking what the modeling basis is for the hypothetical plants. And if I might paraphrase, how is a hypothetical plant modeled?
Okay. Stephen, ask it.
Oh, sorry?
Who
Stephen.
Stephen, thank you very much for a question. Just to mention to you that we collected some data from the papers that we have in the literature, but these hypothetical plants is most to see how our model is working. We are not conducting some specific the evaluations with some specific plants exactly, but what we are looking for is to see like, okay, if we set the number of plants, a specific number of plants that can ensure this amount of oxygen, how much plants do we need and what is necessary for us to build as an architecture, to build as a environment, as a closed, controlled ecological system that will allow us to meet these numbers that we are envisioning for like oxygen production and CO2 removal. I'm also with my colleague Tarun if he wants to complement something.
Hello, everyone. Davi actually covered the entire basis for how we wanted to get that done. So the underlying basis that Davi and I used for getting this graphs and getting the data handled is to use the growth rate of different plants and the time it takes for the growth to happen and what's the mass increase that happens. So we've used all of these different parameters for each of these plants to that a plant undergoes during a growth cycle and correlated that with the amount of oxygen produced. And again, mind you that these are hypothetical plants, so these are not real. We are only doing this to test the system that we're building right now. And once we have reliable data that makes a lot of sense, we're gonna use that with the plants that we intend on using on the experimental systems, firstly on a small scale, as Davi was mentioning earlier, and then in an analog setting to see how well our built system works in regards to the actual experiments that we're conducting.
It's important to mention that, like me and Tarun, I'm the hardware guy, Tarun's the software guy. So on the hardware perspective, we are considering that if we establish some specific systems requirement with specific capabilities, what we can achieve on that numbers, on that values that we are building our model. So I'm looking on how we can implement some specific hardware. And once we have this data like of the plant inside of this system, we can specifically, we can like really establish the real values and to start doing this module in a real scale scenario, in a real scenario.
We have a question from Greg. He asks if this is an MEC model, which I know is modified energy cascade model, or are you all using other kinds of plant growth and gas exchange models other than modified energy cascade?
Can you repeat, Christine? I didn't get this question, if Tarun got it.
Mm-hmm.
Yes. So
go ahead, Tarun.
Currently, no, we're not. We are not using the energy cascade model, and we are yet to introduce anything energy related at this point because we're slowly trying to build it based on. Firstly, we're only looking into the air exchange, and then we're moving on to the water exchange, and the energy will be considered at a later point of time. I need to look into exactly what the energy cascade is as well. I'm sorry.
It's very empirical, higher like polynomial fit of basically carbon. Biomass production as a function of light, and I forgot the other parameters. Forgive me, Greg. You sent the link there in the questions, though. But yeah, there are a lot of different modeling techniques and ways that we can go
so to begin with, I did use the ratios between the plant mass with oxygen, carbon dioxide, and other stuff empirically, but I'm not aware of the official terms being used for that same thing, but it's at a very basic level at this point of time.
I had one other question for you all. If I can find my question, I wrote it down. There it is. So I see that we're modeling flow of mass through the system, carbon dioxide, oxygen, CO2 consumption. How would you go about maybe starting to incorporate nutritional quality and biomass quality or calories in that mass flow? It looks like it's not in the model yet. Is that true? Okay.
No, I can take this one.
Model.
Yeah, like exactly. We are doing, Christine, like some few steps. We are evaluating first this mass. This air mass exchange on our system. Then our next steps will be on energy requirements. Like once we establish the desired hardware that we want and the desired capabilities, we will look for the specifically for like energy requirements. And then we will be adding some other parameters like temperature, like relative humidity, VPD. We can start looking from the amount of nutritional resources that we need to put into the irrigation system and so on. Like we are considering that for now, we should basically to see what is the best approach that we can use to make this feasible in a long term and to start adding like with more certainty, let's say like that. We should not committing some mistakes. We are analyzing one step with like our first step, considering one human in the loop, one specific hypothetical plant, and then we can start looking for like 2 types of plants, accrue in this loop, and so on. Like we want to establish step by step to see what are like the needs in this first step, and then we can start addressing the next ones. But thank you for your question. It's a very relevant point.
Thank you, Christine, and thank you, Davi. Just to add on what Davi just said, as Dr. Ray Wheeler was asking quite a bit ago when Cesare was giving his talk. We are currently trying to use the existing ecosystems and integrate that into the next steps that will lead us to a more bioregenerative systems, rather than completely chucking the physicochemical systems out of the way and just relying on bioregenerative systems. So we're planning on integrating both of these things together by the end of this project that we're thinking of.
Yep. That makes a lot of sense. Much safer way to go about it.
Thank you.
Thank you
All
very
right.
much.
I think it's time for a coffee / networking and mural board break. Hi, everyone. Before we get started, there's been a question in the chat about the Coffee Breaks Zoom breakout rooms. We're having some technical difficulties on the breakout rooms right now. Patrick, our fearless technology organizer, is trying to get on Zoom tech support to figure out why they are not working. So we will try to have the networking rooms open over the course of the next couple of days, but they're not quite available yet. So to the person who asked that question. Okay, Patrick, are we back, and are you ready to go?
Yes, I haven't resolved the breakout room, but I think I'm ready to hear from Borja and everyone else.
Okay, so let's keep this train rolling. Our next talk this morning is Borja Barbero talking about adapting at the ends. I love this topic: exploring plant telomeres in the extraterrestrial environment of space and lunar regolith.
Awesome. Thank you very much for that kind introduction. Can you see my slides?
Yes, we can.
Awesome. So hello, everyone. My name is Dr. Borja Barbero Barcenilla, and today I will be talking about plant telomeres in space and in lunar regolith. So I don't think I need to remind you what is the importance of plants in space to this group, but as you all know, plants are going to be critical in the next colonization attempts to Moon and Mars. We're going to need them as a food source because, we cannot keep eating ramen noodles forever when we go to Mars. As well, we're going to need them for oxygen generation, carbon dioxide removal, and one other issue that is often not reminded of, which is mental health. When you talk with astronauts on the International Space Station, they say their favorite experiments to do, they're always plants, and it's probably because it reminds them of home. And this is going to be something very important for next colonization events because there's going to be mental health issues, especially in close encounters as we're going to be. However, we have a huge problem. We don't actually really know if plants are going to be long-lasting in space. So our solution is going to be to check their telomeres, because telomeres are the most known marker of organism and cell prosperity. But before I go any deeper, I need to give you a brief background of what are telomeres. So telomeres are DNA repeats at the end of the chromosomes, TTTA-GGG, that they do not code for protein, and their function is the protection of the whole genetic material at the rest of the chromosome. You can actually think of telomeres as the aglet or the very tip of your shoelace, where you have the tip of your shoelace or the aglet protecting the rest of your shoelace. When we lose this little part, the rest of your shoelace is often broken, right? So telomeres do a similar job in the sense that they protect the rest of the integrity of the chromosome, similarly as to the aglet protects the shoelace. And of special importance is an enzyme called telomerase, which is in charge of adding these telomere repeats at the end of the chromosomes. Telomerase, besides being very important for telomere length maintenance, it has also been found to have roles in oxidative stress as well as mitochondrial stability. So every organism has a different telomere length set point, which maintains the rest of the genome protected. In Arabidopsis thaliana, in Columbia ecotype, which is our organisms, is between 2 to 5 kb. In mice, is between 20 and 100 kb. And in humans, is between 5 and 15 kb. So mutations in telomere-associated proteins, as well as telomerase, can lead to changes in telomere length. There can be telomere shortening and telomere lengthening. When we mean telomere shortening or lengthening, it means below the range. For example, in Arabidopsis, telomere shortening will be considered below 2 kb, or telomere lengthening will be considered above 5 kb. So telomere shortening can lead to premature senescence, and telomere lengthening is one of the major hallmarks of cancer cells. So organisms with very short telomeres have actually lower chances of species prosperity. And in addition to mutations in telomerase and telomere-associated proteins, environmental and oxidative stress can have an impact on telomere length and telomerase activity. My work during my PhD was to test the fact that plant telomeres are actually quite resistant to environmental stressors, especially if we compare with other organisms such as humans or even C. elegans. Telomere dynamics are actually influenced by a very host of physiological and environmental factors. So things such as smoking, diet, inflammation, infection can lead to an increase in reactive oxygen species, and telomeres are actually a hotspot for ROS lesions. I actually, we tested during my PhD work that telomeres actually accumulate 100 times more amount of ROS in plant telomeres than the rest of the genome. Depending on the severity of this ROS will be different changes in telomere length. If we have an increase above the basal level of ROS, this can lead to telomere lengthening. However, if we keep increasing the levels of ROS to the maximum, will lead to telomere shortening and eventually cell death. We also are aware that there's different antioxidant mechanisms that can lower the levels of ROS and eventually will have an effect in the telomere lengthening, just because antioxidants will lower the levels of ROS, as I will be talking in a little bit. So to study the effect of space flight on telomeres, there has been two major studies. The famous twin study experiment that Dr. Marsha Porterfield talked about, and there has been another 6-month astronaut mission. So in both experiments, they were revealed that there was a telomere lengthening happening in the International Space Station to astronauts. And this telomere lengthening was actually independent of the duration of the flight. This was observed early on, as well as when it was later on in the mission. The telomere lengthening was prevalent over the duration of time. So, as you may hypothesize, telomerase activity, an increase in telomerase activity, could potentially account for these telomere length changes. However, in the twin study experiment, as well as the 6-month astronaut mission, there was no telomerase activity assay able to be performed due to the degradation of the protein itself. Accompanying these phenotypes, we also observed that astronauts experience increase in ROS, genome instability, as well as mitochondrial dysfunction. So the question that we had, it is, what is this effect in plants? Because we need plants for different purposes in space colonization effects. So very quickly, I'm just going to go over the experimental setup. Plants were launched aboard the SpaceX CRS-22 on MS plates, where Arabidopsis thaliana was grown for 12 days in the veggie hardware that you can see over here. 12 days after, astronaut Mark Van de Heydt collected the samples and froze them, and part of them were shipped back to Texas A&M, where we will perform the telomere length studies, and to other groups across NC State as well as Ohio University. So first, we tested the effect of telomere length in both shoots and roots of our Arabidopsis thaliana, because we knew that shoots and roots, they do experience a different response in spaceflight. So as you can see, the plants roll in the ISS, the roots go all over the place, and this is due to the microgravity, because the roots do not have any gravity vector to follow. And we tested telomere length using our TRF-based assay. If you remember from my intro a couple of minutes ago, I mentioned that Arabidopsis thaliana Columbia ecotype telomere length is between 2 and 5 kb, and that's exactly what we saw in the control for shoots and for roots. And surprisingly, we saw that the telomere length for our flight shoots and roots tissue, you can see that there are no changes compared with the control samples. We quantify this over here. So this is pretty remarkable, because this is the first organism that in a space flight doesn't suffer from any telomere length changes. This was tested in humans as well as in C. elegans back in the 80s. Then we tested for telomerase activity assay. First of all, because, well, it was very interesting to be the first experiments to test for direct telomerase activity assay of space-flown tissue. And as well because we wanted to see if telomerase activity could have a role away from chromosome M maintenance in spaceflight. As you can see here in shoots and in roots, we tested for telomerase activity assay with a assay called TRAP and then Q-TRAP. So these are independent experiments. And you can see in both TRAP and Q-TRAP that there is an increase in the telomerase activity of our shoot samples, up to 4-fold change measured by Q-TRAP, as well as in roots. And in roots, dramatically, the increase was up to 150-fold change in telomerase activity. This is a vast increase in telomerase activity. And remember, this massive increase in telomerase activity did not lead to changes in telomere length in Arabidopsis thaliana. So obviously, we hypothesized that this could be due to the increase in oxidative stress that plants experience above the International Space Station. And indeed, we detected an increase in genome oxidation space from samples, data that I'm not going to show here for the sake of time. And why is this happening? Why do you see a huge difference in roots versus shoots in terms of telomerase activity? Because this is a vast change. So roots, unlike shoots, are actually not adapted to deal with the damaging effects of radiation that they might experience in the International Space Station. And I just want to point out that other Earth environmental stressors that lead to oxidative stress lead to a change in telomerase activity upregulation in plants without changes in telomere length. So we hypothesize that this increase in telomerase activity that we see in spaceflight is not leading to changes in telomere length. Telomerase is doing something else involved in perhaps in oxidative stress response. So there's many things that happen in many different stressors that can happen in space. There's microgravity, there's radiation. So we tested the effect of microgravity first on Arabidopsis thaliana telomeres and telomerase activity. So for that, we went to Kennedy and using their fantastic facilities, we tested for, we kept the plants for 12 days in an RPM machine that will mimic microgravity. As you can see, samples that were grown on RPM, the roots did not follow a gravitational vector. And then we went and measured telomere length and telomerase activity. As expected, we did not see either change in telomere length in our samples that were kept in the RPM versus the 1G control. And this is similar to what we saw in space. So this was to no surprise. However, and very interestingly, we saw that telomerase activity did not quite really change in microgravity conditions versus the control. We see here in shoots, there's no statistical significance change between the RPM telomerase activity and the ground control. A small tiny increase to 2.5-fold in the RPM roots telomerase activity compared with the ground control. But remember, this was 150-fold change in telomerase activity in space flight. So taking all of this into consideration, we hypothesize that probably radiation may have an effect in the massive increase in telomerase activity that we are observing in space from samples. So for future directions, we are going to go back and perform experiments with telomere-associated protein and telomerase mutants in the International Space Station, as well as plants that overexpress telomeres to see if actually telomerase overexpression is necessary for plants to perform and do well in a space flight, as well as we will test this in Brookhaven. So part one, I just told you about what we saw in low Earth orbit. There was a change in oxidative stress that plants suffer, telomere length remained unchanged, and telomerase activity was increased. What happens beyond low Earth orbit? What is going to be the outcome of our plants that are going to be grown on our future colonization missions? And we are all aware of the fantastic science that was done by Dr. Annalisa Paul and Dr. Robert J. Farrell, in which they grow Arabidopsis thaliana on genuine lunar regolith. And the plants were able to germinate, which is shocking and amazing for many people. However, these plants, as seen by their transcriptome data, they did suffer from oxidative stress. So the question that we have is, can plants live on the moon? So we are going to be looking at the physiological and molecular markers of fitness in these plants for multiple generations, because we're going to need plants to be able to grow in regolith, if that is the way that we're going to grow them, for multiple generations, because otherwise it's going to be a very short trip to the moon and Mars. So I'm just going to show data from G2 antioxidant lunar plants. We had to grow plants in antioxidant simulant regolith, because otherwise untreated led to no plant growth. And we knew that this could be the case, especially from the data from Annalisa Paul. So we grew our plants on a regolith simulant that had antioxidants added into them. As you can see by the pictures, this is our earth control plants that are grown for one generation on the lunar regolith that is slightly smaller, as you can see as well from the rosette area and biomass comparison. G2 starts seeing a tiny bit more of this stunted growth and delayed development compared with the G1 and the earth control. So there is a progressive loss of plant size and, well, different markers. The question that we have is, like, why is this happening? What could be the molecular phenotypes happening here that can lead to this continuous decrease in overall plant size, biomass, and as well things that we're going to need for create food? So we tested for telomere length changes in our earth compared to our G1 and G2 regolith grown plants. Compared with our earth grown plants, we can see that G1 telomere length started to shorten around 500 base pairs, and the G2 suffered an even farther shortening compared with the earth and G1 control. So you can see a further loss of around 500 base pairs loss in telomere length, which this eventually will lead to plants to be non-viable in lunar regolith. I just want to remind you that this is just wild-type Columbia ecotype. These are not genetically enhanced plants. So this shows potentially that genetically enhancement of plants is going to be a requirement for plants to grow in regolith. And then the question was as well, besides, why is the plant getting smaller and losing overall size? That could be potentially explained by further loss of telomere shortening. But why are telomeres shortening in these plants? Well, as you remember, telomere length can be changed depending on the amount of oxidative stress. So we tested for the amount of 8-oxoguanine, which is a common marker of genome oxidation. So if you have oxidative stress, you will have your guanine being oxidized into 8-oxoguanine, and it's a marker of genome oxidation. So both G1 and G2 saw an increase in genome oxidation, meaning that the plants are suffering from oxidative stress, but there was not a much difference between G2 and G1 lunar amount of oxidative stress. It keeps to be high, but it seems to be at the same levels. However, and very interestingly, we saw that the amount of telomerase activity in G1 lunar plants was decreased to around half of the earth control. So our hypothesis of why you see the shortening of telomeres in plants grown on lunar regolith, it is due to an increase in oxidative stress combined with a decrease in telomerase activity. And this is very puzzling because this is the opposite of what we would expect from plants that are actually being oxidized. But obviously, more to study on this matter for sure. So putting everything into perspective, I just want to discuss that I was able to convince you that telomeres are markers of prosperity, and that's why we set out to do in these missions. We saw that telomere length on plants aboard the ISS remain unchanged compared with the ground controls, and this change it is unique to plants, as any other organism that has been tested for telomere length suffered a telomere length increase independent of the duration. And this was followed by an enigmatically increase in telomerase activity that we hypothesize is due to an increase of oxidative stress of plants aboard the International Space Station. And sadly and interestingly, we saw that telomere length of Arabidopsis plants was shortened within every generation as well, and this could be due this telomere lengthening decrease due to an decrease in telomerase activity as an increase in oxidative stress. So putting everything in, to conclude with everything, and I know there was very heavy data presentation, I just hope I was able to convey that telomeres are markers of cell and organism prosperity, and we're going to need to understand the telomeres of every organism that we bring in every colonization, and space travel. The effect of low Earth orbit was lessened in plant genome and telomeres compared to other organisms. Plant grown on lunar regolith displayed physiological and molecular stress, with sorting of telomeres very apparent in second generation. Obviously, I don't have time to talk about this, but we observed similar phenotypes on Martian regolith, but even more dramatic. And then antioxidant and telomeric genetic enhancement of plants, I didn't show this either, shows promise on lunar growth. So thank you, first of all, to the CPEN lab, where I'm the postdoc currently right now, as well as our fantastic collaborators from Ohio University, Dr. Wyatt, from NC State, Dr. Pereira, as well as Dr. Aquilano from Universidad Nacional de Plata, Dr. Susan Bailey. And then thank you very much for the NASA Plant Analysis Working Group. I know there's a bunch of you attending the presentation today, as well as Dr. Meyer and Jeffrey Richards for their amazing support and help with the experiments. And thanks for funding for NASA and the NIH. Thank you very much.
Thank you. We have time for maybe one question, and then after that, perhaps if you don't mind, Borja, going on to the Q&A or into the chat to answer some questions.
Yeah, absolutely.
Yep. I'll just choose one here. Constanza asked what you think about the use of synthetic microbes edited to reduce oxidative regolith, where you don't need to edit the plants, but bioengineer the regolith.
So that is a very interesting question. That's something that we're pursuing. After you start reusing the regolith, there's some more microorganisms appearing because you are starting to convert adding organic matter into the regolith. And now we're actually seeing that the reuse of the regolith, and we hypothesize due to the increased amount of microorganism, is actually leading to the plants performing better. So I agree that could be an interesting avenue to study and work on for sure to enhance plant growth in this regolith, which is a very terrible material to grow plants on.
Thank you very much. And again, check out the chat. I think there's some other questions for you there, if you don't mind maybe responding to a couple of those. Our next speaker, we're going to hear from Donald Kuhn, who's going to talk to us about, the modified energy cascade model for bioregenerative life support. Welcome, Donald.
Thank you. I do this. All right. There we go. So, yes, my name is Don Kuhn. I'm with the University of Florida Agriculture and Biological Engineering Department. And today we're going to be taking a trip through the modified energy cascade, some of its past iterations, and some of my current work on how to build this up for a useful bioregenerative life support system tool. So in order to fully get the understanding of what's going on, we got to go back to the 90s when myself and this model were originally developed. It contains four main components: photon capture, canopy quantum yield, carbon use efficiency, and a harvest index. With those four simple components, you're able to make a pretty easily understandable model, which can be applied to all the crops, provided you can parameterize those four components. However, in the wonderful world of modeling, there's mainly two options. You either add more stuff to a model, or you make it simpler. So naturally, a few years later, modifications began, with the first one being the Cavazzoni Modified Energy Cascade Model. And if you ever cracked open the NASA Baseline Values and Assumptions document, this is what you're going to find in there. It's a pretty useful model, and it still contains the original energy cascade in these three equations here: canopy quantum yield, your photon capture, carbon use efficiency, and your harvest index. What he did is he added this entire transpiration cascade, so you can predict, how much the plant is photosynthesizing or how much water is being consumed through transpiration. And he also parameterized the model for 9 of the most basic crops that you can get, including lettuce, which is what I'm going to be focusing on because I'm a PhD student. I don't got time to grow wheat or potatoes, so I got to go something quick. But the next one was Bashiri, who actually took out the yield component and added in water, gas, and nutrient flows. So much more detailed information for a very closed environment that he was testing this model in. And then our final one was Amatranos, who actually went the opposite direction and made it simpler by taking these 3 equations and changing them to 2 variables and simplifying some of those resulting calculations and reduce the amount of parameterizing and calculations that are needed, while also introducing a way to calculate cultivar specific coefficients. That way you can get your genotypic representations in there. But she didn't stop there. She also found that the MEC has some overestimations under off-nominal conditions, specifically under high vapor pressure deficits and daily transpiration rates. And you can see that here where, under ideal VPDs of 0.56 kPa, it predicts pretty good with a R value of 0.95. Meanwhile, as soon as that VPD goes outside the nominal range, you lose about 20% of your predictive ability, which is, a little bit concerning, especially when you think about the fact that this is the most recent model version to be developed. So the question is, did any of the others also have this issue? Or, is it specific to the changes that Amatrano made to the model? Which is something that none of the previous authors necessarily did. They didn't necessarily go back and look, did we do better or worse than the person before us? Which brings me to my purpose. That's my goal. Pick apart these models and learn how they work, what makes them tick, where they function really well, where they don't. That way we can improve upon them, because at the end of the day, we want a nice, smooth cascade that's predicting yield and resources. That way we can better utilize these models in spaceflight environments. We do not want to continue building upon something that may burst into flames and give us really bad prediction results. And so all of this actually started with a very simple direct comparison. Dr. Amatrano was kind enough to bribe me with some of her experimental data, which I naturally just shoved into the other 2 model versions to see if I give them all the same inputs, do I get the same outputs? No. That would be way too easy, wouldn't it? And so here you can see daily transpiration rate. There's her observed data. That's what her model output predicted. There's the Bashiri model version and Cavazzoni. So Amatrano's was the lowest, Bashiri's was the highest, and Cavazzoni's came in right around the middle. And this trend is very visible throughout a lot of the results, even with total edible biomass. And you can actually see some of the consequences of the simplifications she made. You can see some of the consequences of the modifications she made with those variables, leading to a very linear representation compared to Cavazzoni's much more exponential and realistic model predictions. But interestingly enough, they both came to the same conclusion on the day of harvest. So the question is that good or not? But this is only just one simulation, one set of inputs. We're not going to learn too much unless we do this many, many more times. And the framework for that is global sensitivity and uncertainty analysis. It sounds big and complicated, but it's not too bad. It starts with very simple. You got to define your parameters and take samples of them. I picked a triangular distribution for this current iteration of this analysis, going from the minimum value to the maximum stated operational ranges of the MEC, with an average value in the ideal environmental conditions for lettuce production. Then from there, instead of doing random sampling, which renders a lot of spaces and cluster points because random is not always necessarily truly random or useful, I used Sobel sampling, which smooths out those gaps and clusters. That gave me about 768 different simulations to run per model, which I did. So they all had the same exact set of data that they were simulating, but we already know they're going to get different results. And ironically, look at that. For net photosynthesis, Amatrano averages lowest, Bashiri averages the highest, and Cavazzoni averages right in the middle. And this holds true across the entire range of inputs for a given output. And now that we've looked at the data a little bit, for net photosynthesis, you think about, okay, well, this is a cascading model, so each one of these things fits into the next one. And net photosynthesis is used to calculate your stomatoconductance, which calculates canopy conductance, and lastly, calculates your daily transpiration rates. Ooh, okay, now that's weird. The variation that you see upstream of daily transpiration rate is almost erased entirely by the time you get to calculating daily transpiration rates. So does upstream calculations have any influence on the downstream calculations? Well, this is where we actually get to the analysis portion of GSUA. Two main methods. We have our Morris method, which is a qualitative screening to find out which factors or inputs are important or interactive, and then a quantitative analysis through the Sobel method, not Sobel sampling, same guy, different thing. A Sobel method analysis detailing how much of the output can be explained by the inputs. And so here we have our elementary effects, the outputs of the Morris analysis. Once again, you can see some trends with Amatrano's models performing relatively the lowest, Bashiri's performing the highest, and Cavazzoni's predicting right around in the middle. And then interesting enough, fortunately, they are very similar models, and you can see trends in the importance and interactions of these inputs being consistent across model versions. So like temperature all being lined up here and PPFD being lined up as the most interactive and important factor for each model. Now, granted, there are about 24 different outputs because there's 3 different models with all their own different things. So not all of them have this trend, but for the most part, they do. They do. And using this, we can then go on to the Sobel analysis to look at how much influence these inputs actually have on the outputs. And so, net photosynthesis, surprise, surprise, largely and mostly only driven by PPFD. Almost 100% of the variation you see in net photosynthesis can be explained by that. But something like stomatoconductance has a lot more of the entire environment influencing it. And then by the time you get to daily transpiration rate, your PPFD values barely influence the outputs at all, and it's mostly temperature and photo period. But these are just single inputs, and single inputs do interact with each other. Temperature, humidity, CO2, light, all those things do have interactions, and individually they are quite small, representing maybe 10 to 20% of the explanation of the output's variance. But collectively, they do have a much larger effect, especially for something like daily transpiration rate. And so in order to fully understand this, you do look at the total order effects, which combine your first and second order. And in most cases, the interactions sort of reduce the amount of variability. And in the upstream calculations of daily transpiration rate, well, for daily transpiration rate, they actually increase the variability and the importance of certain factors like temperature and photoperiod. Okay, we made it. Almost done, folks. And so in conclusion, wrapping things up, the first order variations are generally reduced by the interactions. I just went over that. Bashiri's model and Cavazzoni's tend to be equally sensitive in most cases, while Amatrano's is usually less than and quite different from those two. Bashiri's and Cavazzoni's are very much more directly related, while Amatrano's made the most modifications, diverting away from the original MEC. And this trend of Amatrano lowest, Bashiri highest, and Cavazzoni right in the middle holds true across many different of the outputs and even deep into the GSUA results. And for BLIS and controlled environment agriculture, it's quite important to make sure we focus on not just yield, but also the resource use efficiency and plant performance indicators that are possible through this transpiration pathway. We do not want to neglect it as we continue to develop and use this model to predict resources and yield within spaceflight environments. And because, you know, like they said, we want lettuce, we want salads, we got to make sure there is enough lettuce to go around for everybody. Real quick, just some acknowledgements for people who have helped me out and some of the funding I've gotten, references if you need them, and that's everything. You got any questions?
Yeah, we do have a couple of questions here for you, Donald. Let's see. Oscar is asking, which model in general do you think predicts the data better, is the most predictive?
Yeah, so I haven't actually, other than Amatrano's data, which is her experimental data she used to develop her version of the model, I haven't compared them to ground truth data, which is my plan for the spring. This GSUA is the first step to do a model evaluation.
Mm-hmm. Yeah, I think Jane was also asking a similar question about whether we've tested the original model, and I guess we're interested in the performance between the different
Give
methods.
me about 5-6 months.
Okay. Yep, Oscar says these models need validation. Absolutely. Another question for you, Donald, is how many plants are in a growth cycle and how many growth cycles are needed to give you data points that you need? Like, how much data do we need for validating a model like this?
Okay, so I can just share my current plan. I'm going to get a growth chamber. I'm going to have 3 different varieties of lettuce, 1 heat tolerant, 1 heat sensitive, and 1 somewhere in the middle. Maybe about 14 to 15 plants for each variety at different age groups, because I want to be able to capture that. So I'm going to need like 50, 60 plants per variety growing at once. That's my plan. I'm going to have like 16 plants on scales. I'm going to be pulling weekly samples for destructive samples and various other measurements to hopefully capture as much of that cascade as I can.
Yeah, I've always been curious myself about the power, statistical power with the model, with this model, that I know the number of parameters has decreased with the different versions. But yeah, whether it's overfit and how many data points do you really need?
Yeah.
Oh, also I may have missed this in your talk, so I apologize if I did. The input variables and looking at sensitivity analysis, what kind of ranges and where are we using for the sensitivity analysis for those inputs, and how do those ranges of those input variables compare to actual operating conditions you think that you might see?
Well, for this sensitivity analysis, the range of input variables I used would not, I hope, not represent true production, because it has anywhere from, the absolute minimum possible,
Okay,
0
so
light to 1,000 micromoles of light. That's crazy. And so this one is just a quick look at, the entire range of possibilities. That way we can elucidate, where it might fall apart, where it performs best. And then later, I'm going to do another one with more production realistic distributions, where it's highly in optimal environments, and it might, vary out every once in a while. And then we can hone in on what's most important most often versus when things go wrong.
Okay. You mentioned vapor pressure deficit, and again, I apologize if you answered this, but I didn't see pressure in the input parameters, and I can't remember if it was in one of the older models. Should pressure be there?
It is considered a constant in most of the literature, but it, spaceflight environments, it wouldn't be. So it is something you can change, and the model will respond to, though.
Okay. Any other questions for Donald? Oh, so Melanie says we need pressure, but we need funding to do that. That's always our answer. We need funding.
Well, and she's always trying to get me to do that, being on my committee.
Great. Let's see. Any other questions? Anyone that I've missed? For Donald? Well, this is, oh, I did see, I knew there was one more, sorry. Lori, who asked about the number of data points, she is also asking whether they can provide you data points. Is there a way? Have you all talked about collecting data from different organizations? I think it's a great question for this group as a whole, actually, is data sharing.
Yeah, that would be interesting. I'm certainly open. Usually I have found that any data points somebody has are rather incomplete because I'm trying to do the entire model, make sure it works from beginning to end, and they might have, photosynthesis and yield and no transpiration data or conductance data. And I need to do an entire pathway, that way I can validate that. But I might be able to, mush things together if environmental conditions are close enough to. But if you got data you're willing to share, I'd be willing to take a look.
Actually, it might be helpful. Yeah, really useful to get a list of basically what those conditions are that you would need to have monitored and in order for that data to be useful. And let's see. I guess also we can connect. Lori, maybe you can message Donald in the chat and see if you want to discuss data sharing further.
Yeah.
Okay, great. Thank you so much, Donald. Great talk.
Thanks.
Our next speaker is going to be Ben. Hello, Ben Smith, who's going to be talking to us about biofiltering for human-produced atmospheric volatile organic compounds. Welcome, Ben.
Oh, thanks, Christine. All right. Okay. So I'm Ben Smith, lunar settlement scientist and founder of Lunar Homestead. Lunar Homestead is researching the frontier-enabling technology and techniques needed for permanent, sustainable lunar settlements. Today, I'm going to talk about the airborne volatile organic compounds humans naturally produce, why they are a problem, and how we can deal with them using biological solutions. Okay, so what are volatile organic compounds, also known as VOCs? VOCs are compounds with a high vapor pressure and low water solubility. This makes it possible for them to evaporate under normal pressure and temperature conditions. They're considered organic because they all contain carbon. Many VOCs are human-made chemicals used in a wide variety of processes and materials. Some examples are petroleum fuels, paints, building materials, cleaning supplies. Actually, it's an enormous list. The first step in dealing with VOCs in off-Earth habitats would be to make sure none of these materials are allowed to enter the settlement in the first place. But that's a huge challenge in itself and outside the scope of this presentation. Unfortunately, humans are also on the list of VOC emitters. A healthy individual will emit acetone, methanol, ethanol, isoprene, hydrocarbons, alcohols, ketones, and potentially hundreds, if not thousands, of other VOCs from their skin and breath. Each human doesn't produce a lot. The numbers are measured in parts per billion and micrograms per hour. Interestingly, one study indicated that keeping your skin clean can limit the generation of skin VOCs. So just another reason why subtler personal hygiene is going to be very important. While an individual human doesn't produce much VOCs, put a bunch of them in an enclosed space and the concentrations will build up if not dealt with. I've listed the sources used in my research at the end of this presentation. Source number 3 has a table that shows calculated VOC concentrations for some situations. For our purposes, let's look at what happens in an airplane, which is kind of like a sealed habitat. Note that this was a very limited study that only looked at 5 types of VOCs, not the thousands that humans emit. So you put 85 people in a 56.7 cubic meter space with no air exchange. You end up with 950 micrograms per cubic meter total, or about 11.18 micrograms per cubic meter per person, of just these 5 VOCs. However, this calculation also assumes a steady state and not a gradual accumulation, which I'm not sure is a realistic assumption. The body will absorb some VOCs and metabolize others. Neither of these are good, but I doubt that this would prevent VOCs from gradually accumulating in the habitat. The numbers are actually kind of all over the place. Apparently, there hasn't been a lot of research done on this issue. You would think this data would be readily available from NASA. However, if it exists, I couldn't find it. Source number 4 included a lot of VOC types from both breath and body. That study showed a total body emission rate of over 1,500 micrograms per hour per person of VOCs. All right, so why do VOCs matter? Well, because they're toxic, even in low dosage. I couldn't find anything about the toxicity of human-produced VOCs, but there have been studies on industrial exposures. One study on acetone found that workers exposed to 890 parts per million over 14 years experienced a wide range of problems, ranging from eye irritation to memory loss to significant neurological issues. And remember, we're talking about permanent settlement here. 14 years isn't that long measured against a lifetime in a settlement. Another study showed that women exposed to even 14 parts per million can experience significant issues in incidences of pregnancy complications. This definitely isn't good for settlers. And VOCs in general are known to cause a bunch of other health problems as well. I listed just a few of them here. The point is that even the minor stuff, like eye and skin irritations, are not all that minor if a settler is going to have to deal with it the rest of their life. Memory and coordination loss represents a hazard to everyone in the habitat. Increased pregnancy and cancer risks are just unacceptable, period. So let's look at what NASA considers acceptable concentrations for 4 of the VOCs humans produce. Keep in mind that NASA wasn't thinking about settlers when they made these decisions. These numbers are for astronauts that are going to do a mission and then go home. So let's put it all together. It looks like human-produced VOCs, at least these 4, are below the NASA allowable limits. This is good, right? Nothing to worry about. Unfortunately, it doesn't take into account several factors. The human production number is per person. More people equals more VOC production. Do 15 people push acetone production over the NASA limits? Sure looks like it. And what about accumulation? If the VOCs aren't absorbed, metabolized, or removed, then they have to accumulate in the habitat. NASA's timescale isn't long enough for settlers, especially settlers born into that environment. Which brings us to pregnant women and children, both of which are much more susceptible to VOCs, and both are necessary for any true settlement. And the NASA document covers a lot of contaminants, but not all of the major human VOCs. And finally, all the research I found has focused exclusively on humans. Large-scale, long-term settlement of the solar system must include a lot of different species, not just human. We have to protect all of them from VOCs as well. This is a long way of getting to the conclusion that no concentration of VOCs is acceptable for long-term settlement. Okay, so if we have to continually remove all the VOCs produced by humans, how do we do it? Let's look at how we're doing it now. On the International Space Station, the Trace Contaminant Control Subassembly, or TCCS, deals with contaminants that are not carbon dioxide or water. The TCCS is part of the Environmental Control and Life Support System, also known as ECLSS, and resides in the US part of the station. The Russian segment is serviced by the BMP. I didn't take the time to hunt down what that stands for. The TCCS uses physical adsorption, thermal catalytic oxidation, and chemical adsorption processes to remove contaminants, including VOCs, from the cabin atmosphere. The cabin atmosphere enters the charcoal bed assembly, which is activated charcoal treated with phosphoric acid. It's primarily designed to remove ammonia and dichloromethane, but it's also good at removing a lot of the VOCs as well. The air is then moved to the thermal catalytic oxidizer assembly, where it is heated to remove methane, carbon monoxide, and the VOCs that the CBA didn't remove. And then finally, the air flows through the post-sorbent bed assembly, containing granular anhydrous lithium hydroxide. the SBA absorbs hazardous oxidation products from the COA. The air is then pushed back into the cabin. Unfortunately, none of this equipment is sustainable. The charcoal and post-sorbent beds can't be regenerated. They are bagged and jettisoned to burn up in the atmosphere when they reach the end of their projected life. The oxidizer has a lifetime limit due to catalyst poisoning. Any settlement using a similar system would be completely dependent on Earth for its survival, and they wouldn't be able to expand their settlement without buying more equipment from Earth. The Orion spaceship and the Gateway station will also require an ECLSS, which includes VOC removal. However, I couldn't find any specifics on the trace contaminant removal equipment. What I did find showed the same setup as the ISS, which makes sense because Orion and Gateway will have similar volume, mass, and power restrictions to the ISS, and they are designed to be completely reliant on Earth. We need something better for actual lunar, Martian, and space settlements. Our current space tech isn't designed for settlement. We're going to need a whole new toolbox if we want humanity and life in general to spread throughout the solar system. So how about using plants to scrub VOCs out of the habitat atmosphere? Plants have a lot of potential advantages over chemical systems. They are relatively low maintenance. Settlers are going to need air, light, and water anyway. And we know how to easily turn food and other waste into fertilizer. Plants are self-replicating. Once our settlement establishes their first batch of plants, they can grow as many as they need without needing to import more from Earth. And plants provide other benefits as well. A charcoal bed assembly isn't known for raising people's spirits. Plants can. The NASA 1989 report Interior Landscape Plants for Indoor Air Pollution Abatement, also called the Clean Air Study, is often cited as proof that plants are capable of significantly cleaning household air. The report even states, if man is to move into closed environments on Earth or in space, he must take along nature's life support system. The report also states that low light requiring houseplants, along with activated carbon plant filters, have demonstrated the potential for improving indoor air quality by removing trace organic pollutants from the air in energy efficient buildings. Sounds great. Unfortunately, the study only looked at benzene trichloroethylene and formaldehyde, which doesn't really help us since humans don't produce these. But as you can see, the plants did reduce atmospheric VOC concentrations inside their very small sealed containers, about 1 cubic meters. A single type of VOC was introduced at pretty high concentrations. The plant was then left alone for 24 hours to do its thing. The amount of VOC left in the chamber was then measured. While this is a good initial experiment, it doesn't come close to replicating the conditions inside an occupied habitat. And we don't really understand how VOCs were removed. There are at least 4 ways that we know of. The above ground part of the plant could do it, most likely through the leaves. Microorganisms in the soil could be responsible. Well, one paper stated that they are partly responsible. The plant's roots could be involved, or the growing media itself could remove VOC through some chemical reaction. Or it could be a combination of all 4, and it probably is. One thing to consider is if microorganisms and soil interactions turn out to be significant contributors, then hydro and aeroponics may not be the best solutions for growing plants. That's going to make some people sad. And we'll have to figure out how to make soil using locally available materials. This shouldn't be too difficult to figure out, but right now there are no detailed instructions on how to actually do it. The fact is that there are not a lot of studies looking into VOC removal using plants. There is also no information regarding human-produced VOCs in plants. There is a lot of opportunity for non-professional scientists to do some research and move our knowledge forward. Finally, if you start researching this topic, you'll find a lot of pages, articles, and posts debunking the clean air study, which is baloney because the study is sound. I read an article claiming that based on the paper's results, you would need 1,000 plants per square meter to equal the same VOC removal rate that the average indoor to outdoor air exchange already provides, which is absurd because that's not at all what the study was about. And completely irrelevant when it comes to space habitats because the last thing we want is an air exchange with the outdoors. So, what can we conclude from all of this? Humans produce volatile organic compounds in high enough concentrations that we need to deal with them if we want to settle the moon, Mars, or anywhere else. And since settlement requires children, we'd better be able to remove all the VOCs all the time. It's going to be a hard sell if we can't prove to people that their children won't be born with birth defects or develop cancer because we can't clean the air. The current tech, which works, isn't suitable for long-term settlement. It requires constant resupply from Earth. Not only is this expensive, it's a huge vulnerability. Any disruption in the supply chain could endanger the settlement. It also uses materials that will be difficult to find on Luna and Mars. This limits our settlers' ability to repair the equipment or build more if they want to expand their settlement. And there may be an issue with scaling up the system. It works okay in a small space like the ISS. I don't know if anybody has looked into how it works with larger pressurized volumes. If it doesn't scale well, then points 1 and 2 become more of a problem because settlements will need more units. Can we use plants? Maybe. Certain plants can remove significant amounts of certain VOCs under controlled conditions. However, the few experiments that have been conducted haven't tried to replicate the conditions in a settlement habitat. And they haven't tried to remove the VOCs that humans produce. So for now, the answer is just maybe. And maybe a better mechanical chemical system is needed instead of biological. The activated carbon bed can be designed to be regenerated, and maybe a different catalyst can be used, or maybe something completely different. It might make more sense to run the air through a supercritical water oxidizer and simply reduce the VOCs to their basic elements. I don't know. And it seems like nobody else does either right now. Whatever route we take, one thing is clear. A lot more research is needed, which brings us to, I actually had more to say about the slide, but the presentation was running long. So these are just some of the things that we need to figure out moving forward. And here are some of the sources. This is being recorded, so I'll just move on. And more sources. And that's it. Thanks, everyone. Any questions?
Thank you, Ben. Great talk. We have
Thanks.
a lot of chatter in the chat room. I'm looking to see if there's any specific questions. AC in the Q&A says he's surprised that butyric and propanoic, if I pronounce that correctly, propanoic acid VOCs are not observed from humans. I'm not familiar with those, but I'm wondering if this list of VOCs that humans produce is necessarily comprehensive.
My list? No, that was just
anybody's.
Yeah. I found a couple of studies. There's interest in using VOCs as health indicators, right? So if you measure certain VOC outputs, you can maybe find pre-cancer, pre-diabetes, whatever. So there's some studies measuring human VOCs, but the number keeps growing. Like initially, the oldest papers I found, it was dozens, and now it's into thousands. And not everybody produces all VOCs all the time. It just depends on your certain biochemical reactions that day. But yeah, I did not find a comprehensive list of everything.
So it's fascinating to me because I haven't often thought about personal hygiene as actually affecting mass exchange.
Yeah, well, it's interesting.
Yeah, we think about human effect on the environment in terms of big scale things like carbon dioxide, but yeah, it's fascinating. There's a lot of chatter on the chat box about whether it's soil microbes that are doing most of the work, or whether it's plants. And I think actually Mark Nelson, where's his comment, says he will be touching on that during his talk after lunch, as far as potentials for space and indoor air pollution and sick building syndrome. And I know there was a lot of interesting data there from Biosphere 2 on soil filtration. Jane,
yeah, the thing is that you know, in the ISS, they're filtering for macro amounts of VOCs, basically off-gassing of the equipment and everything. And so all the human-produced VOCs are just overwhelmed by that, and they get treated anyway. But like I said, if we're smart building settlements, we won't introduce those materials in the first place, in which case we're going to have to deal with the VOCs that humans and other animals and the plants or whatever produce, instead of the massive amounts from materials.
Melanie also suggests biochar is something to look at, but I think what you're saying here is we need something regenerative. I guess biochar could be. Oh, Donald has. Nope, those are different questions. Another one I wanted to ask, and maybe if you're not sure, Ben, I also might ask this question of Oscar Manje. VOC monitoring, my recollection is it's not great right now. I know there's still a need for even being able to detect, like we can detect certain things, but I don't know if you wanted to comment on that, because if it's that much of a potential health impact, we probably need to do a better job of being able to measure it.
I have no idea. I have no idea what equipment is used to actually monitor it. One of the papers talked about, having a full mask on their test subjects and collecting the gas, but I don't know how they analyzed it.
Oscar's saying FTIR, Anita, there's a new technology there. But yeah, that's an active area of work where we NASA's been looking to improve, and until we know, can't really define and deal with the problem until you've really measured it.
Right. I mean,
what problem it is.
The best case scenario might be just to over-engineer the whole system. So, it's removing all of the VOCs, but you don't necessarily know how much.
But it sounds like some very interesting experiments you're suggesting of really trying to dive into the different effects of whether there's plant filtration versus soil microfiltration going on, and starting to tease experimentally prove that out.
And on another level, we have to figure out what happens with the VOCs. If the plants are absorbing them but not metabolizing them, then we have to treat those plants as contaminated. You would just want to throw it back into your agriculture. Whereas if it's metabolized, then what is it metabolized into? And is that something that we would want to reintroduce? I mean, we'd have to destroy these plants completely because they're contaminated.
Great. Thank you.
Thank you.
There was, again, a lot of interest in your talk on the chat box. You see some of the chatter, and continue answering questions if you don't mind.
Yep, no problem. Thanks, everyone.
Thanks, Ben. Our next speaker is Dr. Oscar Manje, who's going to be talking to us about producing air revitalization waste biomass. Welcome, Oscar.
Can you hear me? And I don't know if you can see me. Okay.
I can hear you. And, can't see you yet.
Okay.
There you are.
That's
Hello.
fine. Okay. I can't see myself, so I don't know what I look like, but I'm going to try to share my screen. And I'm going to share this one, and it says share, so. Is it there? You got it?
Yep, we can see it.
All right, great. So I guess I'll get started. I'm going to talk to you. Well, Ben, thanks for the great introduction. You've, pretty much explained all the problem in its gory details. So what I'm going to talk about is how to produce air revitalization sorbents from spacecraft waste biomass. And, I got my name here, but I got to recognize a lot of people at KSC, Riley Finn, and other colleagues like Orlando Melendez as well. Okay. So this is a recycle presentation, and, I was going to make a whole thing about new topics and bioregenerative life support. But the main point I wanted to make is that bioregenerative life support is going to be a hybrid endeavor. And by that, I mean, it's going to be physical chemical systems and biological technologies mixed together. And so, a perfect example is what Ben proposed is, we have the trace contaminant control system right here, TCCS, and this diagram over here on the bottom right corner in blue. And then, the sorbents that it uses, you'd have to bring them all the way from Earth because there's no other way to do it. So, expensive, et cetera, et cetera. So one of the things I want to say is about the TCCS, it's TRL 9999. You know, it's been tested, it's reliable. It's just not sustainable. You know, and then it works at a certain scale, and in scaling, sure, that would be have to be looked at, but you know, essentially it would work for a crew of 6, and that would cover most of the first crew missions to the moon or Mars. So we don't really need to reinvent that technology. We just got to make it sustainable. So what I want to talk about is, okay, how would it go about making things sustainable, having all these plants and physical chemical systems? Well, we have food systems, crop production systems. They produce crops. They supplement the crew diet. You know, we've heard all these topics. You know, bioregenerative life support, BLSS. The plants recycle water via transpiration. They produce oxygen and remove the CO2. Everything's good. Now, but if we look at the plants themselves, you know, only 30 to 80% of all the crops is edible. You know, harvest index for potatoes 80%. So, you know, but not every crop is like that. So the remainder inedible biomass is waste. And, you know, we can store it, we can burn it, we can throw it away. Or what I'm proposing is, and actually not proposing, we've been doing these experiments. You know, we turn it into biochar. We have to turn it into activated carbon, and then we can use it for air revitalization. So in this chart over here, we have, you know, the plants remove CO2, they produce oxygen for the little stick man over here. The little man produces VOCs. When he runs, he sweats and produces acetone and ethanol and ammonia. Okay, so ammonia is missing in Ben's chart. That's a big one. And then they produce tons of CO2. So the plants, if you give them a little bit of light, they produce the edible biomass and a bunch of inedible biomass. So what do we do with that? Well, we can turn it into biochar. We can turn it into activated carbon. The activated carbon can be used to swap out the used beds in the trace contaminant control system. And then the used activated carbon can be used to, you know, amend our soil regoliths and continue this carbon cycle. So this is a way of doing this. I'm going to try to explain how this is feasible. So another aspect is, you know, that we can use algae as well. You know, here you have the little stick man. They produce urine and gray water. The gray water can go to the plants. The urine can go to algae. The algae, well, it can make proteins, fuel, nitrogen. You know, maybe people don't want to eat it, so I didn't put that arrow there, but some people think you want to eat algae. You know, I've eaten a smoothie, it's great, but it's not everybody likes that. But there's a lot of inedible algal cake waste, and you can turn that into biochar as well. And here we go, we're back in this system. One of the things about photobiological membrane bioreactors, they convert ammonia-rich waste like urine into ammonia nitrate fertilizer, and then the algal biomass can be converted to biochar again. You know, so this is being done at KSC, producing the algae and doing this, converting the ammonia-rich waste into ammonia nitrate fertilizer. And I'm going to talk about the algal biomass. So, you know, we've looked at on Earth, biochar helps closing the carbon loop. I mean, this has been done by ancient peoples that are no longer around, the Terra Preta, you know. But in space, you know, we can use biochar to add it to lunar or Martian regolith to improve their fertility, to, you know, we can maybe make it more usable so the plants won't be dying. They can host microbes, and it's your organic matter, you know, that's what's missing on the regoliths. So one of the topics that Ben mentioned was as duration and crew size increases, the logistics of resupply and disposal of ecoless consumables like activated carbon is limiting. And so for the TCCS, you know, uses 50 pounds of impregnated activated carbon. You know, you use it for 5 to 6 years, but then after that, what do you do with it? Where do you resupply it? So one of the things about those spent carbon beds, they're loaded with VOCs and ammonia salts. And if you put that into compost or regolith with bacteria, hey, those bugs can use that, and the plants can use it as well. So there's some work to be done there. So some of the objectives of this work is produce impregnated activated carbon sorbents for trace contaminant control from carbon wastes, and compare the VOC removal capacities. You know, you can make the waste, but if you don't have the removal capacities, then you're nowhere. You know, so okay, so that's what I was saying over here. So is the approach feasible? First of all, we must accommodate the mass, power, and volume limitations of spacecraft. So one way to do it is you get rid of the waste, you turn it into
Oscar, are you still there? Can you all hear me?
Yeah, I can hear you just fine, Chris.
Okay,
I
did we
think
just
that
lose
Oscar has
Oscar?
a network connection issue.
We'll give him another moment to come on back in.
Mm-hmm.
We'll just take a moment here. Again, there's some interesting chatter going on about this topic. So keep going, guys. This is great. Now, I wonder if Oscar knows that he disappeared.
Well, if he's here, he should be able to hear us talking about him. So,
huh. Strange. Oh, he's connecting. Hey, you're back.
Yeah, did I drop out?
Yeah, you did.
Yeah.
Maybe about a minute ago.
Yeah, no, I saw all snap, and I'm like, uh-oh. Okay, sorry guys.
It's all right.
So anyway, what I wanted to say was, you know, to summarize the current slide. Can you see the slide still?
Gonna have to share it again, I think.
Okay, I have to share again. Okay, good. Sorry, guys.
There we go.
Okay, so the point I want to make is if the approach is going to be feasible, you got to accommodate the mass, power, and volume limitations. And then the activated carbon that you're producing has to be equal or better than the activated carbon you're replacing, right? And then the processes for forming the biochar and the activated carbon can't be energy intensive or require, you know, sophisticated chemicals or additional hardware. So, you know, those are the kind of things you got to keep in mind. So 3 sources of carbon waste I looked at were tomato, wheat, and algae. And tomato was produced using slow pyrolysis. Inedible wheat biomass, I got it from a farm and dried it at 60 C. And then algal cake was dried at 80 C and broken into pieces. So here's the sorbent. Here's the, you know, some tomato turned into biochar, some dry wheat. And then if you drain the algae and turn it into algal cake, that's what it looks like. And so what I looked at was just the tomato char, and then we impregnated it with phosphoric acid, algae, dry algal cake, and impregnated. And the wheat we didn't impregnate it. But essentially, these are the 5 sorbents that we looked at. And what we did is we compared them to 2 commercial acid-treated sorbents for ammonia removal. You know, these are Ammonosorb 2 and Chemsorb 1425. And then these absorb ammonia and other amines. These are replacements for the Barnaby Sutcliffe 3032 that is no longer made. So, we have to look for substitutes for these sorbents anyway for the trace contaminant control because of commercial obsolescence. So instead of looking for commercial sorbents, in this study, we were making our own basically. So when you impregnate sorbents with phosphoric acid, then this reacts with ammonia through chemisorption, and you can you have an absorption capacity for ammonia. So we studied the absorptive capacity of the commercial off-the-shelf sorbents and the carbon waste sorbents by passing 40% ammonia, 50 to 60 ppm, through about 50 to 60 milligrams of sorbent in an open loop using an FTIR, to measure the VOCs. So for comparison, I'm gonna say that the commercial off-the-shelf sorbents, the ChemSor 1425, if you look at ammonia concentration on the x-axis and then removal capacity, this brown diamond is at 26 milligram per gram. That's where the ChemSor 1425, and then the Ammonosorb 2 is the other diamond, is around 48 milligrams per gram. So if we're going to have a sorbent that's going to be a good replacement, then we want to be in between those two ranges. And so those are our benchmarks. And then we looked at the tomato char and the tomato impregnated char. The tomato char was below, that's it, this little blue circle here, 8.6. But the impregnated one is, right there. So that's a good one. We looked at the algae and then impregnated algae. The algae was right at our borderline, but the impregnated algae was not. So there's differences in chemistry, of how these sorbents are going to behave. And the wheat straw impregnated worked fine. So we have made some sorbents that we can use, and we can generate them from carbon waste. So in conclusion, we demonstrated that we can make impregnated activated carbon from carbon waste biomass, inedible plant biomass and algae. The capacities are comparable to capacities of commercial sorbents. And, this proof of concept study shows that spacecraft carbon waste can be repurposed for ECLS air valorization architectures. And so the bottom line is that, this waste carbon recycling is going to enable sustainable exploration, in a hybrid bioregenerative life support system. But it also will help us here on Earth, generating circular economies and maybe even reducing the cost of vertical farming, instead of just selling the product. Okay, you got lettuce where, your harvest index is high. When harvest indexes are lower, you're going to have a lot of inedible biomass. And, if you can recover some of the nutrients or filter some of and they can help out vertical farming. So with that, I'll entertain any questions.
Thank you, Oscar. If anyone has questions for Oscar, please go ahead and put them into the Q&A box or into the chat. One question from Aurora is how would basically other VOCs or carbon monoxide or other pollutants that are produced during pyrolysis then be removed? Or what? Yeah.
Okay, well, you can have catalysts for carbon monoxide. So there are catalysts, and I have some papers, we've looked at those. But essentially the trace contaminant control system, the carbon monoxide would go right through the charcoal beds, but it ends up in the catalytic oxidizer and forms some sort of acid, and then so these are single pass systems that are just getting rid of all the VOCs that come through. A thing to mention is ammonia and dichloromethane dichloromethane is the smallest molecule, and ammonia is something that's not captured by activated carbon. That's why you have impregnated activated carbon. So those two compounds, they're the key performance parameters for ECLS architectures for VOC control. And if you can remove those, then all the other ones follow.
We did have a suggestion from AC about vacuum pyrolysis of organic matter using, well, solar concentrated energy. I guess you could use any other energy sources as well. But yeah, how about vacuum pyrolysis?
Well, there's many technologies, but what is their TRL, and how do you mature those technologies, and how do you benchmark them to existing technologies? So you got to have a down select process, and mass power volume, life cycle assessments, all these things have to be done. But eventually, the simplest, most integrated, most robust, sustainable, reliable technology should end up in where making the cut.
Trying to see if there's any other questions I might have missed. I don't think so. I did have one question, last question for you, Oscar. Where did you get that picture on that slide? It's beautiful.
Which one?
On your
that one
slide.
Okay,
yeah.
that was, well, I had worked on the people with the Mir space station, and so that is a droplet in microgravity that was put on a plant, and then a cosmonaut injected a little air bubble into it.
That's an amazing picture. There's so much going on there. We did have another technical question here, basically about what you said about TRL. The systems to create biochar, are they even high enough TRL? What would you suggest for advancing them?
Well, they're you can use plasma pyrolysis, and right now they're very small, but they do. So we're proof of concept, probably TRL 4 right now. So those are the kind of things. Yeah, we're getting there. And if you like pretty pictures, here's my acknowledgments. These are some zinnias I grew in my lab, so
Wonderful. Okay, thank you very much, Oscar. If you all want to keep asking Oscar questions in the chat, feel free. I think it is lunchtime. Patrick, any announcements before we break?
Yes. Well, I figured out the breakout room thing. The short version is, I think I've corrected it, but it would require us to restart the webinar, which is not a super great user experience. I'm afraid we might lose people if we do that.
Yeah, I think that's probably maybe for tomorrow.
Yeah, I think so.
Okay.
So sorry about that, guys. It should be sorted out by tomorrow. In the meanwhile, we're having these really excellent conversations in the chat, and that's kind of what Mural is for. Comments have a little bit more staying power on a whiteboard than in a chat thread. So I'll drop the link again into the chat if you guys want to interact on Mural over lunch. But I guess other than that, I'll see you all in like an hour and a half, just about.
We will be coming back at 12:45 p.m. Pacific time.
Yes.
Okay.
All right,
Thanks,
here's
everyone.
the link. Thanks, everybody. See you soon.
So it looks like we have 45 that are back with us now. Not as many as this morning, but I imagine that some of our international and European, especially counterparts, are beginning to drop off and go to sleep. So welcome back, everyone. I hope you had a nice break. Patrick tells me that tomorrow we should be able to do networking breakout rooms to chat live with each other. Unfortunately, couldn't do that today, but thank you to Zoom for changing their software since last year. So we will have that fixed tomorrow. I'm very excited to have with us Mark Nelson from the Institute of Ecotechnics, who's going to talk to us today about Biosphere 2's radical experiment in global ecology. Welcome, Mark. So glad you can.
It's such a pleasure to be here, and obviously a group that signs up to a Space Ecology group is going to be people that I share a great affinity to. So I want to give an overview of Biosphere 2 because I think it's still hardly fully comprehended, and its significance and relevance both for our continued happy, regenerative, sustainable existence on this planet and certainly in space. But I think the focus of my talk is really going to be on Earth and environmental applications. So a lot of people think, I'm not able to move a slide. Oh, here we go. Yeah, a lot of people don't understand that the group that I'm connected with, the Institute of Ecotechnics, we've been working for 20 years before the closure of Biosphere 2. And it gave us the background because we had demonstration projects in very challenging ecological areas around the world. We'd worked in many of the biomes that became part of Biosphere 2. And we hosted small international meetings for 20 odd years where we met the leading both engineers, ecologists, and thinkers involved in both biomic and biospheric work. And Biosphere 2 then was designed as a pretty radical, although we downplayed how revolutionary it was. One, we didn't expect that it would gain worldwide interest until we worked out the bugs in Oracle, Arizona, and then sold some systems to recoup the capital costs, to Los Angeles, Tokyo, places where tens of millions of people come. But Biosphere 2 somehow touched the global nerve at a time that I have to remind you that even the word biosphere was a foreign object to most people. Although I do have to say now everyone knows how to spell it now that we've endangered its continued functioning. But I think we still don't really understand as a species that we are totally and utterly dependent on our biosphere for literally our every breath of life, every drop of water. And of course, in space, the lovely thing about space is that reality will be so much more present. And just a shout out to two people that if you're not familiar with, you should be. The bearded gentleman is Vladimir Vernadsky, and he, in his work from the turn of the 20th century till his death in 1945, really understood the science, the modern science of what the biosphere has accomplished in its close to 4 billion year life, how it's transformed the planet. If you're familiar with Gaia, Jim Lovelock and Lynn Margulis, they were unfamiliar with Vernadsky, but when they were apprised of that, they both acknowledged that Vernadsky was the kind of a forerunner. And the guy on the other side is Claire Folsom, who is actually on our project review committee at Biosphere 2. And he's holding up, he was the original pioneer. Frida and some other people continued his work, but he demonstrated laboratory-sized small biospheres or ecospheres that as long as they were species rich, i.e. taken from nature and not overheated, they can continuously work. So it's kind of the origins of closed ecological systems as a scientific study. And at the time of Biosphere 2, the most advanced work was BIOS 3. And we were really lucky when we made outreach to the leading scientists and then the Soviet Union, both in Moscow and in Siberia, that they could understand. One is we came with a translation of excerpts from Vernadsky's Biosphere book. They understood that we were taking the field of closed ecological system to a Vernadskyan level. Obviously, for short-term and near-term application, something as robust as Biosphere 2 is inconceivable. It's so much it will have to happen. But our thought about space was we needed to start experimenting with mini biospheres and understanding how they function, what we don't know about how they could be put together. And we need to have many iterations of that before we'll be confident eventually to make biospheres in space. And two of the other groundings behind Biosphere 2, and I was missing part of this meeting because there's a 50th anniversary of the H.T. Odom Center for Wetlands at the University of Florida, where I worked with H.T. and got my PhD. But ecological microcosms and mesocosms are really fundamental. And in some ways, Biosphere 2 put together a number of ecological mesocosms, i.e. the mangrove was a mesocosm, but we put them together in a unified metabolic thing. And the other discipline is ecological engineering. And that's why I could see from the participants and the presentations that space ecology intrinsically is going to be an ecologically engineered collaboration. And HT is considered the father of that. So Biosphere 2 can be considered to be a biomic experiment. And there was a great deal of wonder especially from NASA scientists that I was speaking with. Why would you put a desert, a rainforest, a tropical savanna, an ocean, my God, with a living coral reef inside a life support system? Well, we wanted to have, it's certainly not a model of Biosphere 1, our global environment, but we wanted to have a laboratory where we could look at the major components and be able to study it both holistically and in detail to see the interactions between wilderness systems and the two anthropogenic ones, our intensive agriculture and human habitat. When our Russian friends came to Biosphere 2, Joseph Gittleson, who's then the director of the Institute for Biophysics that did the BIOS 3 experiment, said, you gave it the wrong name. This isn't Biosphere 2, it's Noosphere 1. And for those of you unfamiliar with Vernadsky, he could see the crisis that humanity is now much more along, that we have become a geologic force, and the interplay between the ethnosphere, especially the technosphere, and the biosphere are two elements that are seriously out of harmony. And what he optimistically thought that humanity was approaching or would approach out of necessity a noosphere. Nous comes from the Greek word meaning intelligence, that we would have to intelligently regulate our human activities with the idea of fostering and not damaging the natural systems, the biosphere. So Noosphere 1 was kind of an inspiration. And I should say, the idea of biospherics, of the science of making mini biospheres, they can be done in many ways. And we decided with Biosphere 2 to make it as pristine and non-polluting an environment as possible. The Russians wanted, and before the Soviet Union collapsed and they sort of ran out of the ruble collapsed in value, they wanted to make Biosphere 3 in the Soviet Union. And they said, we'll make it extremely polluted and use it as a laboratory for studying how to clean up air, water. So we took a different approach. And of course, a Russian biosphere would not have tropical rainforest. It might have boreal forest, taiga, and other types of biomes. I only caught a bit of a presentation earlier that was talking about the power of plants and soils to clean up indoor air, but among the environmental technologies or ecological engineered systems that we were forced to implement to make Biosphere 2 successful was air purification using, and a better term than soil bed reactors, which I think was in that talk, and how we called it. It's really soil biofiltration. And I didn't catch that talk, but I think the plants are not the major drivers of that cleanup. I think it is the soil and especially the microbial richness. So soil biofiltration is a technology that really got originated in modern times in Europe for bad factories, and they began pumping the exhaust through soil outside of the factories. And now when they make them, they either enrich the soils or they pump the air through compost beds. What we did in Biosphere 2, which innovated, is we couldn't afford to have a space without growing plants because Biosphere 2 was really so tiny as an Earth laboratory. So we experimented with and verified that the function of the soil biofiltration is enhanced and certainly not contradicted by having green plants. And we actually engineered Biosphere 2 where the entire farm could function that way, and we could pump the entire internal atmosphere through the soil in about 24 hours if needed. This was a visualization of a commercial product that we were developing. It looks like a ordinary house plant, but there's a little pump underneath the indoor plant and its soil that will pump the air. And just like other ecological engineered systems, like the constructed wetlands I'll talk about in a bit, the beauty of these systems is that depending on the pollutants in the environment, the appropriate corresponding group of microbes will increase. So we used our test module to demonstrate that ability. And the beautiful thing about Biosphere 2 was it was a great example of ecologists and engineers working together. And some of the great drama of Biosphere 2 was way before we put people inside, was getting ecologists to learn engineering talk and getting engineers to understand ecology so that they could work together. I mean, literally, they were in two different universes. And the engineers freaked out because Biosphere 2, when they saw the designs, was not going to be a simple, big box store. It was going to be a very elaborate architectural kind of homage to world architecture. And they also freaked out when they realized that they were being asked to do really, really difficult engineering tasks. But all the engineering of Biosphere 2 was not going to make it habitable. So the technology, the engineering was really to provide favorable conditions for the life systems in Biosphere 2 to thrive. Just a shout out because it was I had been an organic farmer for 15 years, both in the United States and Australia before getting involved with Biosphere 2. And the intensive agricultural system was really quite a marvel. We originally started with hydroponics and we decided to go to soil, one, because the results from Biosphere 2 would be more applicable to world agriculture. And also soil makes it kind of easy. You can do composting. It really facilitates the recycling. And because we were really concerned about microbial diversity at every level, having soils meant that we had a much more ecologically diverse black box of life to deal with. Just some images of this intensive agriculture. One of our consultants, Dick Harwood, was a professor at Michigan State University and an expert on Chinese agriculture. And he calculated, although we had our struggles and we lost 50% of our light because of the shading and passing through glass, that Biosphere 2 was probably the most productive half-acre, 1/5 of a hectare, if you work metrically, farms in ever. And we couldn't use or even organically approved chemicals. Biosphere 2, it's useful to remember, was not a 2-year experiment. It was designed to be a 100-year experiment. And, perhaps you could even see what's happening with it now as part of, what that 100-year experiment has entailed. So in terms of science, both in terms of the exciting aspect of it, and also a management real conundrum is that when you make a small closed system, and I know you guys looking at space are looking at systems and thinking, oh my God, Biosphere 2 is so fast and so leisurely. But you look at a concentrated amount of life in a small space, and the consequence is that most of the biogeochemical cycling gets really accelerated. So, kind of the punchline of this slide is that the 3-year or so residence time of CO2 in the Earth's atmosphere gets truncated to 1 to 4 days in a facility even as large as Biosphere 2. That means that you have 90 to or 100 to 200 cycles of carbon movement per year. So in some sense, Biosphere 2 is a time machine. And John Allen, its inventor, coined this phrase that I find very useful for thinking about both Biosphere 2 and any small closed system. They're cyclotrons because things happen so much rapidly. And I've published papers on the water cycle as well. Oxygen was the great surprise of the 2 years. And it's really interesting. We had scientific advisory committee, and at the end of each of the sessions, it was formed a couple of years before Biosphere 2 is closed, and it succeeded a project review committee. Everyone was asked in the room, what are your 5 or 10 biggest nightmares? And many scenarios were put out there, but nobody predicted that oxygen might somewhat mysteriously disappear. And those of you who remember the media at the time, this was the great thing that's still cited as the failure of Biosphere 2. For me, it was the great success in that something totally unexpected ecologically happened. And Biosphere 2 was small enough. This is when Columbia University first got involved, that with very sophisticated isotope injections and tracing carbon cycles, we could really delineate where that oxygen went. And there are papers that I'm not going to go into that. Some of the other interesting studies were we were on a reduced calorie, nutrient dense, caloric restricted diet, which happened to be that the fellow who's watching me on a exercise bike is Roy Walford. Just happened that our resident doctor, that had been his forte at UCLA, was life extension with this kind of a diet. So he might have been happy. The rest of us, worked at growing, and we grew an extra ton of food as we got to be better farmers and understood the system inside that. And then we also were able to really study the impacts of that lowered oxygen. And in fact, I think one of the funniest papers that came out in a peer-reviewed journal was Roy and some of his colleagues put out the hypothesis that we biospherians were actually starting to hibernate because 2 of our major sources of energy, food and oxygen, were restricted. But it was a pretty definitive look at that. It's when mountain climbers go to altitude, it is not the decrease in oxygen that triggers the usual responses. Because in Biosphere 2, we were at 3,900 feet elevation. That didn't change. It's just that the oxygen declined, and we didn't show the usual adaptations. So, some of the results from the 2 years, the biomes really self-organized quite rapidly and grew. We started with really a bonsai biosphere with the tallest, trees maybe being 6 and 8 feet. By the end of 2 years, we had 30 and 40 foot species, both in the savanna and the rainforest. The predictions that all the biomes would homogenize, which some ecologists thought, and I think they underestimated, and this is, 30-year-old technology, the sophistication of the environmental technologies that we were able to employ so we could really have different temperature regimes, rainfall regimes in all of the biomes. And there was a great ecological surprise that our fog desert started to move towards a dominance by shrubs and grasses. The Biosphere 2 coral reef, which was probably the most difficult biome we had to manage, actually became a landmark after Columbia University assumed control and started experimenting with this unique facility. They started manipulating CO2 and demonstrated kind of 20 years before the fact the crisis that global warming, increased CO2 is producing in coral reefs around the world. And I do want to shout out the personal impact of being involved in this project and having the great luck and good fortune of being selected to go in for 2 years. And I had been pretty committed ecologically for 20 years before Biosphere 2. And to me, when I got a chance to spend 24 hours in the Biosphere 2 test module, which has now been converted to SAM, the simulated analog space environment, the reality of actually living in such a small closed system, it's kind of like the size of your living room, but with 35-foot ceilings and packed with plants from all of the biomes that we were going to be including in Biosphere 2. The impact was really remarkable. It was very profound. And at that point, I went from being a director of the project to starting to do biospherian training, hoping that I would have the experience. And then this is the great group of 8 that went inside Biosphere 2. And we tried to live as complete a human life as possible. Unlike the right stuff, we were encouraged to put our feelings into music and art. And we hosted several inter-biospheric music and arts festivals, through, this is kind of pitiful technology by modern standards. There was no internet, but we were able to video link with artists and musicians and poets outside. And I think one of the things that we wanted to demonstrate, and it was so great that we had this unexpected world stage, the world turned onto the system, I think because Biosphere 2 kind of answered a question that every human has, is why are we here and what's our relationship to this living world? I think Biosphere 2 was small enough that relationship could be quite seen and visualized. And we wanted to demonstrate that being ecological was not a deprivation, quite the contrary. So it was a really rich life we had inside, although we were working our butts off doing the farming and doing all the research that we could. And Biosphere 2 is also a great example of the intimate interplay of ecology and technology. I love that slide. It's just a plant, starting to invade one of our air handlers that kind of functioned like a car radiator and produced the gentle breezes. We tried to have as diverse a carrying capacity as we could. The largest of our animals in the wilderness areas was the galago, kind of a prosimian African species. We partied, we made home brew. I think like most cultures that live frugally on what they can derive, we decided early on to put aside some food so we could have feasts and parties. And we fermented everything that we could. The best of our products was banana wine. We also did a kind of a Tibetan beer, a rice chung, which was all right. And the really bad stuff was the red beet whiskey. I love this one slide. This is the Biospherian handshake, which I only learned later is what prisoners do with their visitors. We thought we invented this. And John Allen, the inventor of Biosphere 2, is on one side, and my dear now departed friend Oleg Gazenko, who is kind of the the father figure. He ran the largest space institute in Moscow and was considered kind of the shrink and confidant of the cosmonauts. And he became a great friend and supporter of Biosphere. And then at re-entry, I mean, I'm told that hundreds of millions of people watched this live, you know, and this is before internet, with satellite communications being what they were in 1993. And I have to say also, it was so amazing to step out of Biosphere 2 and really experience that we had created a different biosphere. You know, the smells, the taste, everything inside was so different than coming outside. And since we did 5 months of research before putting a second crew in there, I watched as my organism, which was really adapted to Biosphere 2 after some initial struggles, you know, where the center of gravity finally switched to where I was comfortable being back in Biosphere 1, as we call it. And just a shout out that even though, and I encourage you to see that film Spaceship Earth, although they didn't do much on the science of Biosphere 2, but it gives a little bit of the backstory of my institute and, you know, the fun that we had before Biosphere 2, during it. But we hosted, at the encouragement of our Russian friends, a series of international workshops on biospherics and closed systems. The first one in '87 at the Royal Society. Then we actually went, and we were the first Westerners allowed to visit BIOS 3 in 1989. It was quite wonderful. In '92, we had one at Biosphere 2. And then we had one at the Linnean Society with representatives from Europe, Japan, our Russian friends, NASA, etc., to share the results. And somebody was asking before I started to speak something about, and I love these constructed wetlands. These are images of, this is our sewage treatment system. So if you don't know constructed wetlands, contrast this with, you know, if you're in a town and you haven't visited your sewage treatment system, wear some nose plugs and go over and take a look at it. But I totally fell in love with this, and we worked with Billy Wolverton, who is a pioneer both on the indoor plants and in constructed wetlands. This was a system that treated all of our, not only human waste, but also the waste from our laboratories and workshops. And it was a beautiful system. It had 14 flowering plants, and I harvested, you know, feeding our domestic animals with it. And it was a beautiful part of our water system, because the nutrients and the water from the system, now highly purified, went back into our agriculture. And it inspired me to go back and do a PhD with Odom at the University of Florida, and to make these systems around the world. Because one of the things that I really appreciated in Biosphere 2 was that connection I felt with the world of life. And I know when I was coming out, I was thinking, how do we get people, you know, more reality based, you know, where they, you know, begin to wonder, where's the water that comes out of my taps? Where do my wastes go? Well, if your wastes, you know, from your flush toilet or whatever, go into a constructed wetland, you're connected. And then, you know, since we don't love, you know, we're not programmed to love bacteria and waste products, but we are programmed through biophilia. You know, you start to think about what you are flushing down your sinks if you have a beautiful garden, you know, either for your personal house or business or hotel. And it's been great fun. I've loved taking these systems into places and countries where it's unknown. And you learn so much, because the climate dictates what plants you can work with. So we've now put these systems into 14 countries, and we have a big project just about to get funded and implemented in southern Iraq. I wrote a book about it called The Wastewater Gardener. And I heard somebody talking about, it's such a pity that we don't have closed systems to work with. So a little bit of a shout out. After Biosphere 2, we built this very modest laboratory biosphere. That's the one with those windows. The thing in the back is our little variable volume, the equivalent to the lungs in Biosphere 2. And we did about 5 or 6 years of research. My God, this was even before LEDs took over the field. We had, old-fashioned sodium halide bulbs, and we played with a lot of space crops, and also, continued our study of the beautiful interplay that you can study in a closed system. This facility now it houses currently our worm beds, but we are 20 miles from Santa Fe. It would need some refitting with LED lights and sensors, but if there are researchers out there that could think of a brilliant use for this, I put in the chat earlier little link because we've published papers that'll give you all the technical specifications of this facility. And then I continue to, plumb the relevance of Biosphere 2 and also to share with people. I mean, even though a lot of the data was, let us call, missing rather than destroyed, a lot of scientific work came out of it. So Pushing Our Limits, which I was happy to publish with the University of Arizona Press, really pulls together a lot of the published work and data of Biosphere 2, but I'm incapable of writing terse academic unreadable prose. So it's a pretty readable personal account as well. And we did a new edition of the original book that 3 of the Biospherians wrote, Life Under Glass. We've updated it, etc. And so why was Biosphere 2 so controversial? No cutting edge, no controversy. Well, we were very cutting edge. And I have to say, it's really sad, and I saw this more when I worked with H.T. Odom, who's, one of the most prominent holistic scientists, that there is a guerrilla war in science, limited funding, academic jealousy between specialists and holistic science. And of course, Biosphere 2, to be successful, we did work happily with both. And we were perceived as outsiders. I think it's one of the reasons I went and got a PhD, so my enemies could say, Dr. Nelson, we think your work is shit. And then there was the media. The great thing is we had this platform for getting our message about the importance of biospherics and biospheres and ecology, but we became a media play ball, and so 2 years somehow had to be perfect, or an experiment was a failure. And they've made a lot. I mean, I keep on reading about, the interpersonal dynamics in Biosphere 2. And I don't mean to downplay it. It was probably the most difficult, but I've worked in the outback of Australia, and I have stitches in my face of actual fights between, not between rowdies at the pub, between me and my colleagues there. I think, we have to accept that we're very volatile, and learning, especially in isolated groups, those tensions are not to be underestimated. On the other hand, we never sabotaged each other's work or the biosphere. One is we understood it was our life support system. And the surprises that happened, experiments, it would have been a failure if that thing worked perfectly, because we wouldn't have learned as much, so key insights. We're entering the age of the Anthropocene. So that dialogue between ecologists and engineers, I think people told us, by the way, that we were 50 years ahead of our time. And I think that's largely true, because if we built Biosphere 2 and we said, look, one of the big things that we want to study is how humans and their technology can live happily, sustainably, regeneratively with a biosphere, would not be considered as outre as it was. There were academic scientists who said that having people inside taking care of the biosphere was a violation of objective science. Well, I think the science question and the human question of our century is going to be, can we humans and our technology learn to live with the Earth's biosphere? We must participate in the management of our atmosphere. I mean, it was amazing to be in a world where we read CO2 data every morning and then oxygen when that began to decline. And it was like an ever-present factor in our minds is, how do we affect the atmosphere? How do we control the rise of CO2? How do we counter the decline in oxygen? The technosphere can be redesigned to support life. I mean, we're starting to hear that about energy, renewable energy, but I think that that conversation needs to go way further. We need to rethink how we do everything, how we, graze animals, how we grow food, how we produce products. The amount of chemical pollution is absolutely terrifying. And I think the good news is that we've largely created a technosphere, not understanding that where we are, Earth is as closed or more closed an ecological system than Biosphere 2. And we all share this lifeboat. And I hate, the gloom and doom and throw our hands up and these problems, the opposition of established industry is too great. Optimism is a yoga. And we have to change our biospheric paradigm. The thing that I guess I realized, it was such a wonderful experience to have that opportunity to be a biospherian, but think about that word that we chose, and we chose it, thinking a lot, is that I became a biospherian of Biosphere 1 again when I came out. That paradigm, that experience is available to all of us. And it's actually the reality. I don't really like this word, the environment. We have to find a different term because it reinforces this fiction that we have, is that we're in this kind of human, our individual existence, our cities, our friends, our circles, our urban existence. And we kind of think that, the environment makes us think that we're separate. We're not separate from the biosphere. I mean, the wonderful thing why we have to have ecology in space is every astronaut who lives in some kind of a bioregenerative life support system is going to have such insights. And since we look up to these people, our explorers of space, for them to become ecological, which will be second nature. I don't care if the person, can't grow a blade of grass on Earth. In space, if he has a living system that is his life support, he will become a #1 ecologist. And so just a final, ecotechnics and biospherics can help us learn to live sustainably. I love that now the term is regeneratively. We don't want to just sustain the world. There's so many problems that are, currently baked into it. And even more, when we go to space, everything that I've said is going to be so obvious to the space ecologists and the space engineers who will work to make these systems. So thank you for your time.
Thank you, Mark. That was a very, very, very inspiring talk. I've seen a lot of great chatter in the chat room. So glad you were able to share your experiences with us today.
Do we have any time for Q&A?
We have a few minutes, and I have a lot of questions we probably won't get through. Let me see if I can start here at the top. Priya was wondering about saline environments. There was an ocean and coral reef. Was there any other environments that were saltier than ocean?
Oh, yeah. Yeah. No, I mean, one of the great systems that I fell in love with, we had a mini mangrove wetland. and we replicated in about 200 feet. I think it was 6 salinity gradients from freshwater wetland through slightly saline, finally to red mangroves. So that was, that was a brilliant ecological engineering. And in fact, working with the Smithsonian Institution, we built a mesocosm of a Everglades system in a greenhouse in Washington, D.C. before we did the one for Biosphere 2. So yeah, that gradient, and I should just say, when they say that Biosphere 2 is a model of the Earth, that's just ridiculous. There's so many things, there's so many important biomes that were not in Biosphere 2, but we wanted to have kind of a cross section. I always think of Biosphere 2 as being a semi-tropical world. So we had a spectrum of terrestrial biomes from very wet, the rainforest, through the moderately wet, the tropical savanna, grassland, trees, to the fog desert. Here we are in a system that's so small and sharing an ocean and rainforest. A fog desert can handle high humidity. But then the two aquatic systems were really important. That spectrum that we replicated was an estuarine system in like the Everglades, where you would start with fresh water, and as you approach the coast, salinity would go up, and all along that gradient, there's a change of vegetation. So manipulating and trying to prevent salinity, we had RO devices for freshening our water. But, living in a world that both had systems very intolerant of salinity and ones that thrived on them, was part of the ecological management challenge.
Priya was also wondering whether the system was closed to the ground. And my understanding is complete mass closure minus whatever gas leakage you had, right?
Oh, yeah, but
like plants couldn't grow into the ground.
Yeah, among the things I would do differently is, most people who visited Biosphere 2, of course, now it's different. You actually go through the whole system. We kind of refer to the basements of Biosphere 2 as our technosphere, although we had technology elsewhere. And Roy Walford he likened Biosphere 2 to the Garden of Eden above ground and a nuclear submarine below ground. So underneath those systems were a maze of piping and machinery to keep the system functioning. And metaphysically, it was really interesting. And I should say, we were aiming at material closure, which meant that, and originally we had no idea. We thought we would do it with plastic. We went to glass because plastic is too permeable for gases. But underneath the earth, we had stainless steel, welded stainless steel that we then tested for leakage and a whole. I think Bill Dempster, for those of you who are at the workshop last year, he gave a talk. He became a master of the lungs, the variable volume structures, and leak detection. And it was quite extraordinary. I got congratulatory calls from some NASA colleagues when the oxygen decline happened, because they said, my God, you bastards have actually sealed that thing that tight. If it was more porous, we wouldn't have seen. That was one of the graphs I didn't have time to show you. But if we had the kind of leakage that they were proud of at Breadboard or BIOS 3, that would have washed out. We were declining in oxygen 0.25% per month. And that's because the air exchange, the air leakage, was under 10% per year, which is quite extraordinary. So yeah, so underground there was stainless steel liners, but in our definition of a biosphere and the Earth, we're essentially materially closed. I should. It's so lovely. I learned this actually after Biosphere 2. We get a small amount, 100 tons, I think, but by Earth scale, a small amount of cosmic debris comes into our atmosphere, and we're losing some of the light gases way up in the stratosphere. But essentially, compared to the volume and the biotic circulation, the Earth is a materially closed system, but energetically open, obviously, and informationally open. So that's what, why we developed a very strong pre-internet but computer system to where data, could be freely shared between consulting scientists and our people in mission control and inside Biosphere 2. And of course, energetically open, Biosphere 2 is largely sunlight driven, but then we had supplemental power sources through natural gas. We wish we could have done it renewably, and I'm really happy University of Arizona keeps increasing the amount of renewable energy that's needed to run Biosphere 2. Too expensive at the time. It would have added, $20 or $30 million to the cost.
Added methanogens, they would make the gas for you. Microbes.
Microbes that do what?
Methanogens. They're archaea that produce methane gas. So you could actually you can use that for lighting Bunsen burners. I don't know how large scale you would want to go.
Yeah, but inside Biosphere 2, we couldn't even light birthday candles. So, no, I know that technology, and I because I'm working in constructed wetlands, and we usually have a septic tank or equivalent as the primary treatment. I'm hoping eventually, I'm sure people have been doing that you make that into a biogas generator, and then you have the constructed wetland deal with the liquid part of the waste. But that's how sensitive Biosphere 2 was.
Right.
Even a tiny fire would have probably driven us out of the facility. That's why partly the architecture. Are you, Christine? Looks like you're actually inside Biosphere 2, but I know it's a backdrop. But that's one reason that the architects made it fairly spacious. I think it's like 35 feet in the savanna, which is the backdrop of Christine, and actually up to 75 feet, 80 feet in the rainforest.
Trying to move out of the way. There we go.
But still with such a concentration of life that, that those slides I just quickly showed you, things were really moving rapidly, and pollution, really minor pollution would have been a problem.
Dragos also is in Biosphere 2 right now. He's at night. I don't know if you can see him.
Yeah.
No, I know. I realize that. Are you actually in it now?
No, I worked there for 5 years, so I connect to what you're saying pretty tightly.
Oh, cool.
I'll talk about that.
That's a beautiful image, by the way.
Yeah.
I hate to interrupt this, guys, but we're really cutting into Priya's presentation here. So
yeah, we can cut into the coffee or into my talk a little bit, so it's okay. But yes, let's continue on. And Mark, there's actually a lot of questions and comments in the chat, so if you don't mind sticking around and just kind of responding to anything you're able to respond to there, that'd be much appreciated. And thank you again so much for a great talk.
Oh, it's been a joy being here. I will get on the chat.
Okay, Priya, we have we have Priya Desarma, who is going to talk to us about Halobacterium, NRC1, and other Haloarchaea for true candidates for space ecosystems. Welcome, Priya.
Thank you so much. It's very hard to speak after such an inspiring talk, and it's got my mind going into the biosphere. I need to learn more. I want to learn more. So thank you so much for that incredibly inspiring talk, and for the whole meeting, for being invited to this. I'm coming at this meeting from a very, very small perspective. I am a microbiologist, and I'll be talking to you about Halobacterium species NRC1 and its friends. Halobacterium is a misnomer. I have a slide where I tell you why, but it's Haloarchaea is what they are. They're considered to be amongst the most ancient of life forms, so therefore archaea, and halo is referring to salt in Greek. And so that's the background on this for those of you who are not familiar with our organism. So this is an image under the microscope of some of the colonies, and they look like space candidates to me. Anyways, so let's see if I can get this moving. And All right. So I'm coming at this, as I said, as a microbiologist, but also as an earthling. And I know that we call it the planet Earth. It's really water covered. And the saline oceans make up about 96.5% of this. So maybe the term fragile blue dot or blue marble may be the more appropriate name rather than Earth, because it's covered. I realize volume-wise, it's not the most dominant part of our planet, but on the surface, that's what it looks like. So you can look at the blue planet and the wonderful green life on it, and the plants that the talks this morning were very inspiring. But there are also other areas. And if you look at some of these areas here, these are some places that we've isolated microbes from much more saline environments than the ones in the Everglades or the oceans. These are hypersaline, extremely saline environments, including, this is Salar de Uyuni, the world's largest salt flat. This is Deep Lake Antarctica, etc. I'd be happy to talk about the different places later. So our Haloarchaea, like I said, are from this extremely salty environment. Our microbes, and specifically NRC1, I'll be talking mostly about that organism from South San Francisco Bay. Its optimal salinity for growing is 4.3 molar sodium chloride. It will die in seawater. It's too dilute for it. So it needs a minimum of about 2 molar salt in order to have the osmotic balance that it needs for its survival. And it's an archaeon, which is distinct from the bacteria. It's something that Carl Woese worked on, the 3 domains of life. In fact, one of his last papers was with us on the Deep Lake Antarctica genome. As I said, we work on these microbes from these incredibly colorful, incredibly highly salty environments. I'm not kidding you, they're beautiful. You can see these are some of my favorite microbes. And one of the things that we're trying to look at is seeing how do these microbes survive in these extreme environments? And this may help us not only to survive here on this planet as things change with climate change, but also elsewhere should we choose or be able to do so. So we've been driving genomics in our laboratory since its inception. Our genome of NRC1 was one of the first genomes ever done, and it was led by our laboratory, and it was the first haloarchaeal genome. And what did we discover from this? These are organisms that live in extremely high salt, have extremely high salt concentrations inside of them, and yet they're able to survive. Most other organisms and most other proteins are unable to survive high salt. In fact, proteins aggregate and precipitate out as part of molecular biology and biochemical processes. I'm a microbiologist, so this is a little bit different than what I do normally. But the major thing that came out of our genome when we did that was that these microbes have an extremely acidic proteome. So their proteins, their pI is about pI of 4.2, whereas most other organisms have a bimodal distribution of their proteins, and on average they're neutral. And this is something that is absolutely a characteristic of these high salt surviving haloarchaea. And this is something that's held true. This, by the way, I have QR codes for those of you interested in learning more about it, including what I had mentioned about the archaea terminology. I know it's called Halobacterium. It's a long-standing feud, maybe an exaggeration given with what we're dealing with in this world these days, but it's an issue. So we talk about open science, open data. We have had a public website since 2000 when we published the genome of this organism. It's called Halo Web, Halo meaning salt, web. It's in the early days of the web, and we have been providing this to the community, and they've been used for many, many years. They're the genomes and proteomes of many, many organisms from the haloarchaeal field. Funding would be welcome if any funding agencies or any funding sources are available. Currently, this is being funded by us personally. My husband and I have been working together for over 30 years. So our laboratory then had the whole genome. We knew that the proteins were acidic, but we also knew that these organisms not only handle the high salt, but they also handle a lot of other extremes. In fact, they're called polyextremophiles, many extremes that they deal with. And if you think about living on a planet like Mars, where it is cold, there's high radiation, including UVC, which we don't see thanks to the ozone layer protecting us. There is desiccation, it's very dry. There are a lot of toxic ions, including perchlorate. There's low oxygen levels. All of these extremes can be tolerated. And in fact, our organisms are actually more able to tolerate than most other organisms in some cases. So these are some of the aspects that we've studied in many, many years. I could talk about any of them for hours, but I will try to keep this short. So these are our microbes inside of salt crystals. You can see this red. These are inside of the salt crystals, and they survive there potentially for millions of years. In fact, we have isolated some that are supposed to be about 250 million years old. And they don't form spores, by the way. When I said they're beautiful, these are our microbes. The pink is due to the presence of nanoparticles that refract light. On occasion, one of the 13 genes involved in this process that we discovered is mutated, and therefore they don't produce the nanoparticles, and then the light is able to go through, and so they're translucent and red. But they're all of the same type of organism. We spent some time looking at the radiation resistance of these organisms, and here's Deinococcus radiodurans, the survival fraction, and you can see here's NRC1. This is our wild-type NRC1 from South San Francisco Bay. When we went through multiple rounds of radiation using a synchrotron with our colleagues at that time in Idaho, we were able to produce organisms basically new strains we called LH5 and LH7A, and we ended up with 7 independently isolated organisms that were more radiation resistant than Deinococcus radiodurans. And because people used to think that the nanoparticles gave protection, in fact, one of them was red and one of them was pink, so it wasn't the nanoparticles that was providing them with the radiation resistance. So they're kind of out of this world type organisms. I didn't mention, and I can talk about this later, that we actually identified which 3 genes were upregulated in these organisms, and in fact those are found in humans as well. They're single-stranded DNA binding proteins, and we were able to both knock out the genes as well as overexpress these genes to actually prove that these 3 genes were involved in radiation resistance. So we think they're kind of out of this world, unbelievably strong and resilient. So can they actually live off of our planet? Can they exist in a place elsewhere? So the stratosphere sort of is a mock or a model region that has it's close enough for us to get our microbes to, that are kind of Martian-like conditions. And we were able to send them up there with a crew in California, some students, and we actually were able to culture these organisms. We sent up both the San Francisco Bay strain NRC1 and HLA from Antarctica that happened to be slightly more radiation resistant. Was able to survive slightly better because of the fact that it can handle the cold a little bit better. But they were able to go up there, and if you think about it, these organisms were in brine because of the high salt concentrations. It didn't actually freeze until, way up there. So we were able to take them live in their liquid form, which is something that nobody else can do with any of the other organisms because the water freezes in most other organisms' media. So stratosphere, sort of Martian-like conditions. Can we take it beyond Earth? Well, yes, possibly. These are actually lakes in the middle. There was a fellow called Wally who sent me these from Cheatham Salt, and he asked me what I thought was going on, and I told him what was going on with the exchange that with the stipulation that he would give me the image. This is actually seasonal lakes. These are our microbes blooming there. They come in many different hues. We have a purple version of the organism. You can see this is here a flask from the laboratory. If you do a membrane extraction, you can see that the membrane is here. In fact, the organism is really kind of amazing because it can grow aerobically, anaerobically, and phototrophically, meaning it uses sunlight energy to produce its own energy. Not likely plants, but it does produce its own energy. And you can see that if you there's a code here, or if you want to look at PBS Eons, does a nice job describing this. So this is where we came up with a purple Earth hypothesis. And just to give you just a slight detail here, this is chlorophyll here, left and right. It's using the sunlight energy on these extremes of the spectrum. At that peak of the solar spectrum, right here, are the retinal pigments that Bacteriopsin, that our organism is using for making its energy. And it's believed that possibly this simpler form of life, this less complex form of life, may have existed prior to the more complex chlorophyll-based organisms, and was therefore, the other organisms had to sort of use the sides of the spectrum to be able to survive. The other thing to remember is that these organisms actually can float, our organisms, and so possibly there was a stratification of the light coming through the brine. So that's way out there. But then if we go back deep and delve back in time, 250-million-year-old salt, this is a location in New Mexico that we were able to go down to. There are organisms there too. These ones that I'm showing you here these are salt samples from Bolivian salt mines that are also 250 million years old. And what was going on then? Well, if we go back then, you were looking at CO2 levels starting at where we are almost, if you think about it. We're over 419 ppm. CO2, that was starting at 412. Temperature right now, on average, over the whole planet is 15 degrees. At that time, it was 32 degrees. Oceans were acidifying. We were just discussing this in the previous talk. There's a lot of similarities. We're kind of headed in that direction, hopefully extremely slowly. But that is at the Permian-Triassic era is when there was the largest mass extinction of life. So we really need to keep in mind that if we don't want to go that way, if we don't want to become a barren planet, we need to do something about this. I mean, just to give you a graphic of what's going on in 2023, this is our planet, the heat map. And it's predicted that by the year 2050, 25% of all plant and animal species on Earth will be threatened with extinction. Sea level rises and salinization, which, as we heard earlier, is an issue, is already having an impact here in the United States in New Orleans, where the drinking water is now salty. So that's a lot of, yes, worry, but if we can understand how these organisms can survive, how they can adapt, maybe we can use something for us here as well as potentially on other planets. If we wait long enough, there's supposed to be a supercontinent in 250 million years. And then all bets are off. So we do need to be sort of elsewhere. So we're here on this spaceship Earth. We're all crew, as Al Gore said. So there are no passengers. We all need to pitch in. And NASA is saying that there are distant exoplanets that may have rare water, ocean, and possibly a hint of life. We have sort of areas which we thought were sterile, like salty environments. This is actually the South San Francisco Bay cover that we published a few years ago. You can see that it's talking about climate change. This is way back in the 2000s. So moving forward, and hopefully we're going to move and cooperate and collaborate together and make, improve the world. So if we wanted, and the reason I was so interested in coming to this meeting was I was thinking, if you do want to move to another planet and you want to do a food chain or a food web, you could actually use these haloarchaea, which are basically, they are able to handle just using sunlight to produce their own energy. They can live anaerobically as well. You could use these because they are actually found in places like in the Great Salt Lake. Brine shrimp eat them and actually are used for the basis of our fish industry, which people, not me, I'm a vegetarian, eat. If we put in a couple of degraders or fungi or whatnot, we can degrade ourselves, and then this whole loop could be formed. It's not a biosphere image. Obviously, I have a lot to learn, and we all do. I mean, this planet is pretty complex, and even if we think we've understood everything, there's always something that we can learn. But for a very simple graphic, I just thought this would be interesting to put our haloarchaea into the loop and to keep that in the thought process, because people usually think plants, which of course we need, but there's also this. If you had Thai food you've eaten was involved in fermented sauces. So the other use that our microbes could have is if you're traveling long distance and you don't want to be taking something that's stored at -80, our microbes can survive potentially then for millions of years inside of these salt crystals. You could actually take these organisms and bring them with you. We have what we call a vaccine in the salt shaker, or beyond that. These are these nanoparticles that are made only of protein, and we have an ability to actually attach or genetically cause them to produce antigens or drugs or whatnot on the outside of the surface of these little nanoparticles that are inside of the cells. Now the cells are inside of your brain. Your brain is inside of a salt crystal. You could potentially, without a food cold chain, actually bring these with you. So you could have it for particular diseases that may possibly arise. We have a couple of patents on this, and we've been working on this on malaria vaccines and salmonella and whatnot. And it's really promising to hear more about that. You can go to this link down here. It's my husband. So this novel design platform. Okay, so if you want to learn more about what we do in the haloarchaeal field, feel free to come and visit our website. There's a lot there, including a molecular genetics tutorial for those of you curious about molecular genetics. So in summary, Haloarchaea can survive above the atmosphere, deep underground, maybe ancient, possibly on Mars. Maybe we could bring it there. Maybe it's already there and beyond. And the big question remains, can we? And so I'd like to conclude my talk offering you that we have these superbugs, as the Washington Post touted it in the national news a few years back. Maybe they'd be useful for some of you for your research and for your thoughts. And we welcome collaborations. My email is down below, and I'd be happy to take questions.
I'm afraid, Priya, that we don't have time for questions. Okay. We're just over. But there were several in the chat, if you wouldn't mind going through and answering them. Thank you so much for that talk. That was really cool. I really like archaea. Fun fact, I just learned that the current phylogenetic theory is that the whole of eukarya is actually directly descended from archaea. So perhaps we are all haloarchaea in one form or another. So without any further ado, let me introduce my colleague and co-organizer, Christine Escobar, who is going to be giving our next talk about everyone's favorite space plant, duckweed. Take it away, Christine.
Well, I don't know about everybody's favorite plant, but it's certainly my favorite space plant. Thank you, Patrick. Okay, let's see, just getting my notes, getting my window in the right location. There we go. Well, I'd like to tell you all today about why we at Space Lab are so excited about duckweed as a life support component, and about the hardware that we are developing to grow this aquatic plant in microgravity. Patrick, just checking, you can see the slides?
Yep, you're good.
Okay. So I always like to begin with this question. I think we've already hit on it a few times, but it's always a good reminder. Why grow food in space? Why not just bring it with us? And the simple answer that I like to give is that living in space is a tremendous and perhaps the biggest sustainability challenge, because space habitats are extremely challenged by limited volume, limited space to work within, limited power, and the limited amount of mass you can afford to carry from Earth. So anything we can do to reuse and recycle what we consume in this uninhabitable environment can help us certainly learn to live sustainably anywhere, even on Earth. So plants, of course, are a regenerable, nutritious food source that turn our carbon dioxide into oxygen and purify our wastewater. And they also make us happy while reducing our stress. But in space, there's other complications for farming or growing any organism. Microgravity and reduced gravity really complicates water transport. It complicates air mixing and root aeration, and it can confuse a plant with gravitropic plant responses. Space, you've got high radiation, you've got reduced pressure. Oftentimes in certain habitats, you might live at a lower pressure than full atmosphere. You have high acceleration loads. You even have elevated CO2 concentrations because, believe it or not, spacecraft scrubbers, CO2 scrubbers, don't currently work as perfectly as one would hope. And all of these conditions can physiologically stress us and stress plants. So it's even harder to control infections in a small isolated container. So with all of these challenges, then we start thinking about what makes an ideal spacecraft. And things to think about is spacecrafts that grow a lot of edible, nutritious, and tasty biomass. Tasty is important, but they must grow very quickly, and they should hopefully consume a lot of CO2 with very little infrastructure, because you don't have a lot of room, very little growth volume, very little water. If they use nothing, that'd be great. Very little energy and very little labor to grow them. And also this plant that's ideal should be robust to these environmental stresses that might occur that I just mentioned, but that also can include things like pH swings, along with elevated cabin CO2 and microgravity and radiation. So some scientists are looking at ways to genetically engineer crops that grow faster, are smaller, or have higher nutritional density. But what if there was a plant out there that already has this genetic capacity to do all of these things? What if we instead change the plant's environment instead of their genes to manipulate their growth and their composition? So introduce duckweed. These guys are small, floating aquatic plants. They're in the family Limnaceae. There's 37 known species and 5 genera. Duckweed plants are commonly found in lakes, ponds, other freshwater bodies that are typically slow-flowing water or still water bodies. They're often mistaken for algae, but they're really the smallest flowering plant on Earth, and they're among the fastest growing plants in the world. So under the right conditions, these guys can double their biomass in 1 to 3 days, much like algae, but they are a higher plant that's actually a flowering plant. Even though they're a flowering plant, they primarily produce through vegetative budding. They replicate themselves simply through vegetative propagation. And interestingly, because they have permanently open stomata, they can continuously take up large amounts of carbon dioxide, and they can tolerate very high levels of CO2 without toxicity, because they have basically been adapted in this wet environment where they do not need to close their stomata. All of their surfaces absorb nutrients and gases and light. Even their roots are photosynthetic tissue. And this contributes to their fast growth because they can just absorb nutrients and light in all of their surfaces. As a floating plant, duckweed has very little structural or vascular tissue. So that means they have little fiber and they have no inedible material. They have 100% harvest index, and you can eat them. You can eat them raw. Well, it depends on what species, but we'll focus on the Wolffia. So they've adapted to really a wide variety of climates. There's duckweed plants all over the world in every kind of climate, in every corner of the globe. They're able to grow under a wide range of conditions. They're really robust, I think, for space life support because they can survive temperature extremes. They can survive pH extremes. They can survive high salinity up to 4,000 ppm. Even anaerobic shallow water. They don't necessarily have to be in oxygenated water. These plants can grow in the dark if there's sugar. They can actually have heterotrophic growth if there's sugar in their growth medium, and they can grow on very, very thin films of water. So what that means is that you require less infrastructure volume to support them. These are just fun duckweed facts, and I'll go into why this is all great for space in a moment, but they can grow under 24-hour light, so they don't necessarily require a dark period, which means you can maintain relatively high growth rates over a wide range of light intensities. They rapidly regulate their chlorophyll content and their photoprotective carotenoid pigments to dissipate heat from solar energy when they get basically too much light coming in. So they're very, very good at adapting to different light levels. And then when they're under stress, they form these dormant buds or caltorians that can sink basically to the bottom of the water and resist freezing and desiccation. I'm guessing that with the wetlands work, Mark might have heard of duckweed before, I would think. Because they are used for wastewater treatment all around the globe. They are very good at converting urea into ammonia. They have a urease enzyme, and in fact, they uptake ammonia preferentially over nitrates. And because of that, it makes them attractive for the treatment of human urine. And for that reason, they're used worldwide for wastewater treatment. And surprisingly, here's the really fun part, duckweed is really, really nutritious. Under ideal conditions, up to 45% of their dry mass is high quality protein. And I don't mean just protein, I mean with all of the essential amino acids meeting or exceeding World Health Organization standards. So high quality protein that's comparable or even better than soybeans, with everything you need in your protein. But they also have high proportions of polyunsaturated fats. They have very low omega-6 to omega-3 ratios, like flaxseed does. They've got some other good things like vitamins A and C and E. There's a lot of vitamins. They have high antioxidants. It's a nice feature for space relative to terrestrial plants, especially carotenoids. that are good to have in the diet as antioxidants to protect you from photo radiation impacts. And if you shine a lot of bright light at them, they're going to boost their antioxidant production. So you can make a basically antioxidant vitamin machine. And that's really important, especially for an astronaut who's exposed to elevated radiation in space. And those antioxidants that are protective against radiation are not produced in the human body. You have to eat them. And they have short shelf lives. So if you can produce those on board, it's a good benefit. Let's see. Basically, duckweed growth is controlled by temperature and sunlight. You throw energy and light at it and it grows, but the nutrients that are available to the plant is really what impacts its nutritional content and its chemical composition. Do they taste good? I get this all the time. I have eaten them. They don't taste like anything dramatic. People say they taste a lot like watercress. I don't know what watercress tastes like, so I can't tell you. There's a little bit of like a spice or ting to them for some species. They're eaten regularly in Asian countries. Thailand people refer to duckweed as eggs of the water, probably because of the protein. And Indonesians eat Wolfia species in salads and soups and omelets. And now there's actually a growing market for duckweed as a human dietary supplement. In the US, it's just barely starting to form. It's been flown in space. It's been in microgravity, indicating tolerance to space conditions. In fact, the first American space plant experiment in 1966 was duckweed spirodella plants, the first measurement of plant photosynthesis in space. How am I doing on time, Patrick? We're good. Okay, 5 more minutes. So if you can rapidly produce highly nutritious biomass in this small volume, this organism could provide a fundamental link in a closed habitat ecosystem because it can grow on these thin films of water. You can achieve a very high ratio of a growing surface area to volume by stacking all these shallow growth trays together. So in this example, I've got a 1 cubic meter box. You can stack 10 growth trays that are 10 centimeters deep. You can go more shallow than that. And I've got 10 meters squared of growing area. That would be enough to produce, about 112 grams of protein per day, which is enough for 2 crew members. So highly, highly prolific, able to get a lot of yield in a small space. So if that's great, they can provide a high yield per volume, how do we produce a floating plant in microgravity? So when I discovered this plant originally thinking, oh my God, this sounds like the perfect spacecraft. Oh no, it floats. What do I do for microgravity? Well, you need a stable thin film of water for the plants to be able to grow on. They can grow submerged underwater, but an air-water interface is better for more effective gas transfer, especially in microgravity. Another challenge is how do you get the plant biomass out of the water in microgravity? Because the water is going to basically be inseparable from the plant mass unless we have some way to mechanically separate them. Another challenge is lighting. We're going to have all these thin growth trays are stacked really close together and very close lighting, which quickly heats up the water. And we need a method of rapidly dissipating heat if we're going to grow them. And we need to consider cleaning mechanisms to maintain water flow in the event the biofilm grows and for pathogen control and food safety. So all these questions are going through our minds, and how do we produce this great plant in space? So we design or am developing in collaboration with the University of Colorado, a thin film hydroponic growth chamber called Microgravity Lily Pond. It supports aquatic floating plants. It also supports rooted land plants. And its goal is to have as much possible biomass production as you can and with little mass volume and power as possible. It uses capillary channels in the growth trays to deliver a stable film of water to the plants that they grow on. It also has a 3-phase separator. We call it the harvester. That basically has a rotating sieve that when you harvest the duckweed plants, it pulls the water away and returns the water to the growth beds. And then you can take the plants out and eat them. I won't go into all the details here because I'm running up on time, but we've been developing this growth chamber as part of a small business technology transfer contract through NASA phase 1, 2, and 3 now. We've built an engineering demonstration of the growth chamber, and we've even tested growing of microgreens on these beds too, not just duckweed, to support rooted plants and floating plants with a certain proprietary film that we put on top of the channels. And we've done a lot of prototyping to demonstrate a lot of the different functions of this growth chamber. But you might ask, does it work in space? So we have tested the capillary channels in drop towers, which is really, really interesting lessons learned that we had there. And also we've developed a flight experiment to test this growth bed in the water filling of the bed, the thin film stability. Can you maintain a thin film of water on a surface in microgravity, as well as the harvesting function. Now, unfortunately, this payload is a suborbital test, so it's just like a couple of minutes of microgravity. The payload has flown twice now on a suborbital rocket, but without demonstrating the water film stability, because we had other issues that occurred on the flight. Well, like the last flight, for example, was actually the rocket failed. So we've gotten a third flight attempt this year. We're going to be trying for a third attempt. And once we've demonstrated that this thin, stable film of water can be achieved with these capillary growth beds that we've developed, we're going to hopefully test it on the ISS next with actual plant growth experiments. And we're also working with the Australian Research Council. There's a Center of Excellence for Plants for Space in coordination with the University of Adelaide that are going to be working with us to test out this technology for growth of duckweed plants. So that was a ton of information. Patrick, I don't know if there's any questions for me, but that's all I have.
Thanks so much, Chris. I always love to hear about your studies of duckweed, and every time you describe all of the benefits, I just get so hyped. I just want to eat them right now. So we do have some questions, and right after this is our next like kind of coffee break.
Yeah, so we're okay.
So we can run into that a little bit, and people can leave if they'd like. We do have some questions. The first one was from AC, who wanted to know, is duckweed the first plant that was flown in space and or the ISS?
I don't know if it was the first plant ever in space. It's the first United States plant experiment. I do know that. So I think Ray Wheeler has told me there's a paper by Ward, and I don't remember the year. I want to say 1970. It's called the Ward experiment. They flew duckweed plants and algae plants, and it was the first measurement of photosynthesis in space, well before the ISS, long time before the ISS.
Wow, that's pretty cool. How about this bit of trivia? Do ducks eat duckweed?
Absolutely. That's why it gets the name. It's
Yeah, I
staple
thought
source
so.
of food for ducks, yes.
Okay, well, here's a serious question. You said that they can grow submerged if necessary. Christopher had a good question that I echoed. What if you supplement the gas concentrations in the water? Have you guys examined if like sufficient levels of oxygen and CO2 enable them to grow submerged?
So that's the trouble with microgravity. Like no matter how much you bubble the oxygen through, you're still at some point limited by diffusion, and you're slowed down by diffusion limited gas transfer. So yes, you could bubble. It would help. And I haven't actually done a cost benefit analysis on those two options yet. I really, really need to do that to, work the numbers, because it's additional hardware, right? You got a little more complexity, but then the growth bed, capillary growth bed is also, well, it's meant to be less complex, but what's the cost benefit of that? But my instinct, I will tell you, is that this is how they evolved to live on Earth, and so why not try to replicate that natural environment, and where they're used to having a gas liquid air interface to grow on. And some species do better than others submerged. Some do better or less with dissolved CO2. Some species do fine with dissolved CO2. Others would rather have it out of the air.
Right. Okay. Christina Johnson wants to know if duckweed can grow in low oxygen or perhaps saline water.
I don't I had a note in my slides that they can grow, tolerate up to like 4,000 ppm. I haven't rechecked that in a while to see, what is their real limit. But yes, they can handle quite a bit of salt. There's quite a bit of salt tolerance. What was the first part of that question?
Low oxygen water.
Oh, low, yeah. So definitely anaerobic water is fine, but not. You need some oxygen somewhere. Well, no, because they actually can. Kind of live off of their own oxygen, much like a plant root really needs to respire with oxygenated roots. But I would like to test that, Christina. I think the answer is you probably could, but I don't know. I don't know the exact. I'm not certain.
Nice. Ray just dropped the link to the Ward's duckweed study in the chat, which is really nice. I don't suppose you'll know the answer to Greg's question of is there MEC data for duckweed, the modified energy? And Greg wants to know if there's data for the modified energy cascade model for duckweed.
So. I would love to help with creating some if find out what conditions we need to grow under and what would be useful.
I guess one last one for me. I recall that there were some interesting like symbioses happening in the root zone of duckweed. Do you know what I'm alluding to? Because I
don't. Well, there's a couple of things. So definitely, especially as an aquatic plant that grows layers, mats, they're called. There's a very active microbiome typically in that aquatic environment. I think we're just beginning to understand how those symbiotic relationships are working. I think there was just recently a discovery of a bacteria that is a symbiotic Limnaceae bacteria, but I don't know a lot of details about it. One interesting fun fact is significant levels of B12 have been found in duckweed plants. Plants can't produce B12. So the theory is that there's some sort of symbiotic microbe at work there creating it. So yes, there's a lot of research there to be had in a very active microbiome, but I wouldn't suggest trying to get rid of.
Sure. Okay, one last one from Connor, who says that there's recent studies that suggest duckweed can survive 20 Gs of acceleration, and he wants to know if you think that it could go all the way to 100. I don't know where we would
I have no idea, but that is a great question. I don't know why you would do that, but okay. I'm not sure.
Sure. Okay. I guess it'd probably be hard to maintain the water-air membrane at that kind of acceleration.
As far as that, we right now are just testing to try to at least verify that it can tolerate relevant, launch loads, that it can tolerate. Well, actually, you wouldn't launch it with the water in the channels, but it can tolerate relevant vibration environments you might have on a spacecraft. But as far as how hard can you bump it, we need to find that out still, and that's very much dependent on how you design the material surfaces and the geometry of the capillary channels. So it's with some careful design, you could probably tolerate a heck of a lot of acceleration. But good question.
Cool. Yeah. All right. Thanks for that insight, Chris. So now we're on to our coffee break. We got about 15 minutes left. We're going to resume here at 2:30 Pacific time, and then just have another hour and a half of presentations, and we're wrapping it up for today. So I guess I'll see you all in 15 minutes.
Thanks, everyone.
All right. We're at 2:30. So are you about ready to kick us off, Professor?
Yes, I am.
Okay, then I will introduce you. I have the great pleasure of introducing Dr. Frida Taub, my mentor and professor emerita at the University of Washington, who also happens to be one of the pioneers of closed ecological systems. And you've definitely heard people mention her name, especially in the talks of other really famous ecologists like Mark Nelson and Ray Wheeler. So it's really a great pleasure to hear from you today. Dr. Taub, please take us from here.
Thank you. Well, we'll see whether I can convince this group that my small ecological communities can inform about life support systems, because certainly the scales are very, very different. The other thing that's very controversial about my work is that I'm working with very simple ecological communities. I'm trying to assess what ecological properties a very, very simple system will demonstrate. So I'm working with 3 different species of algae, and all of these are extremely well known. They're essentially white rats for laboratory studies. And Daphnia magna, for which there are over 20,000 published papers. So you would think that we know everything there is to know about these organisms, but that certainly is not true. Many of my experiments are done in simple bottles with a known liquid and gas phase. I have one instrument called a manta, and with it I can estimate, or it records temperature, pH, pressure, and some other properties, including dissolved oxygen. I only own one of these, so these studies are not replicated. The bottle studies, usually we're dealing with 6 replicates. Okay, so the argument that I'm going to make is that the closed material boundaries have something in common between my little bottles and life support systems. In both cases, they're going to be closed material boundaries, but of course these are open to energy exchanges. In my systems, I start with inorganic, chemically defined media. The same 3 species of algae in each experiment. Some experiments have Daphnia, not all of them have Daphnia. The microbes we are not able to define at this moment, but we save samples for future DNA analysis should the money materialize and should there be some interest in it. Over time, we find that we get behavior of algal populations and Daphnia. But eventually, I think we end up with a lot of dissolved organics and a lot of particulate detritus. Daphnia have a chitin exoskeleton, which they shed, and these exoskeletons can last for a very, very long time. We can see them in our bottles years later. What they have in common is that you're going to start out with a life support system with a big supply, and a certain amount of recycling will occur within this system. And anything that you can't use in the system essentially is going to be stored as waste. So as time goes on, you're going to deplete your supply and you're going to build up larger and larger amounts of waste storage. Now, over time, human life support systems will be expected to be largely self-sustaining. And at the present time, the kinds of money that are being potentially budgeted for returning Mars samples, for example, are threatening other projects. So there's going to be a need for as much recycling within the community as possible. So there are 3 things that I hope to be able to demonstrate to you. One is that in our systems, primary productivity tends to dominate and that recycling is inadequate. And eventually carbon dioxide becomes limiting, although I call it the pseudo-limiting factor, and I'll explain that. The other thing that I want to point out, particularly to amateurs who want to work on closed ecological systems, that you're going to have an increase in oxygen if you have oxygen production above oxygen saturation in the liquid. And the last thing, which is kind of trivial, is that animals require more trace metals. They also require more growth factors than many of the algae and potentially higher plants. So we'll see if I can convince you. Okay, so when we start with our closed ecological systems, we usually have a small number of algal cells and a fairly robust amount of nutrient available to them. So these are on 12-hour light and 12-hour dark cycles. And so at the beginning, for each light cycle, you get more oxygen production. And each 12-hour dark period, you use up somewhat less oxygen. And so over time, you are gaining biomass and you are gaining oxygen. And then you get to a part of the cycle where the system appears to be maintaining itself. And so for the amount of oxygen that is produced during the lighted period and the amount of oxygen that is used during the dark period, they seem to be in balance. And you may fool yourself into thinking that you've got a system that is in steady state and is going to continue forever, but that's not true. And for one thing, you've got a lot of oxygen gain, and this represents essentially persistent organic material. And so if you keep your system going long enough, it starts to run down. If we open the system, which means that we have released the pressure, and we put in fresh nutrients, the plants, the algae are certainly capable of much greater production. And again, given lots of nutrients, you see lots of production and relatively little use during the following night. And if you're production oriented, you think this is just wonderful. Okay, so why suddenly is my computer not going to the next slide? Oh, okay. I'm just going to, nope, now we've gone to 2 slides. Nope, now we've gone way to the end.
I think we had a lag there, so let's give it a second to catch up and then go back to your slide. Okay, so, oh, so this one did not, well, that one I think did show. Okay, that one showed. Yep, next one. There you go. Okay, one more. I think I have to be careful not to press more than once. And yeah, I don't know why these are taking so much time. Okay. I want to remind people what the equation is for photosynthesis if you're starting with bicarbonate. And that is you're going to get 1 carbon dioxide and you're going to get 1 carbonate. So if you start with a certain amount of dissolved inorganic material and you start with it as bicarbonate, as photosynthesis occurs, what happens is that half of your carbon becomes carbonate. And this carbonate is not available for photosynthesis by green algae. It may possibly be available to cyanobacteria, but that's controversial. And I don't know whether it's available to higher plants. But the problem is that you run into what I've called pseudo limitation in that you have plenty of carbon in the system, but it's not available for photosynthesis. So that is one problem that you have with carbon. The other problem is that if you use the Redfield ratio, which is what most ecologists use, which I had in small print on one of the other slides, you would expect to have 6.6 times as many carbons taken up as nitrogen. But what really happens is that you get approximately twice as much taken up. And I'll go into a little bit more detail on that. But there really is not a whole lot of literature about this carbon overconsumption or carbon nitrogen uncoupling. At the end, I'll give a bunch of references on this if people want to pursue it further. As far as the Daphnia magna are concerned, and the 2 previous ones that I showed you were algae only, but in this one, the Daphnia population, we start with 6 animals. These are asexual animals, although if conditions become really bad, they can produce sexually. So we start with 6. They don't always survive the first week, but then we'll get a big population bloom, and then it eventually decreases. And by manipulating the nutrient regime that we start with, we can actually control how long the Daphnia population will survive. And what's kind of counterintuitive is that the less nitrogen and phosphorus we put in, the better the Daphnia seem to do. And the other thing that happens is that as the algae grows, the pH increases, and I think that there's a interaction with that. I think the lessons that I've taken from these small systems that I think are relevant is that we know a lot more about the production of complex organics. We don't know as much about the breakdown of things like cellulose, lignin, and chitin. And if we don't recycle these persistent organic compounds, we essentially rob future primary productivity.
as well as building up a lot of storage that we have no use for. So unlike the Earth's ecosystem where gaseous CO2 is in excess and increasing, these systems, CO2 becomes limiting. In Biosphere 2, there was a lot of CO2, but it didn't seem to contribute adequately to oxygen. The other thing I want to point out, particularly for amateurs that are doing closed ecological system work, is that the oxygen increase and the pressure increase in a closed system will very much parallel one another. And as you build up an oxygen concentration, you're also building up pressure. This is well known in other studies. There was a very successful closed ecological equilibrated biological aquatic system that went into space, and they maintained oxygen below saturation by literally turning off the lights. A lot of studies were done at University of Hawaii where they estimated oxygen production from pressure measurements. So this is something that is unlikely to be a problem in manned systems that will be well regulated. But in amateur systems, you can have systems explode. The fact that the Daphnia require a lot of trace metals, they require vitamins that are not supplied by the algae or the algal media, I think is kind of a truism in general. I think that vitamin pills certainly are going to be necessary. So our simple closed ecological systems suggest that nutrient recycling is not going to be automatic or easy, that atmospheric pressure problems could occur. Simple food production systems will need to be supplemented. For those of you who look at the recordings, I've tried to give citations and references. I've given a number of studies that report carbon overconsumption or carbon nitrogen uncoupling. These tend to be a fairly tight research group. I've not seen a whole lot of other studies on this. I would like to know if somebody knows of them. Certainly in terms of industrial processing, if you get algal cultures nitrogen limited, you can get them to produce interesting sugars, and that's how they do most of the biofuel work. So I recognize that ecologically simple ecological systems are regarded as very stupid and dumb. Certainly the Biosphere 2 studies and studies by Goyle that you'll hear tomorrow will argue that complexity leads to stability, and these systems are relatively simple. But all I can say is we learn more from failures than success. So that's what I've got to say.
Thank you so much for that, Professor Taub. That was an excellent talk. And you have quite a few questions, so let me just jump in there. The first one's from Greg, and he wants to know if your manta was designed for drop tower experiments.
If it's designed for
drop tower experiments, you know, where you
okay, the manta was originally designed for putting in a lake or putting in the ocean. It has a limited amount of battery power. It stores the information that it gathers, and then you essentially download that information and you can manipulate the information. The Eureka company that designed or invented the Manta 2 modified mine so that I could use it on line power. I don't know if that answers the question.
Sure. I think to Greg, it's not designed for the drop tower. It was actually made specially for Frida. And I had a question for you. And it was, you had a note in one of your slides about the ratio of phosphorus to nitrogen was 1 to 12.5. And I wanted to know, is that like a generally true ratio, or is it just specifically for your systems?
My
system related to the red field?
Using a different rule book than, I mean, the other thing, I'm hearing drums in the background or some sort of noise in the background. I don't know if all of you are hearing it.
I do not hear that.
It's a mechanical clicking. Anyway, you know, my gut feeling is that if you want your animals to be healthy and you want to produce a lot of animals, you want to feed them well. And so the idea that by reducing the amount of nitrogen and phosphorus, we get healthier and longer lasting animal populations just goes against everything that I've ever been taught. But damn it, that's what my data are telling me.
Sure. We gotta believe the data, right? I have another question from
Well, let me explain one further thing. I think that the reason that those conditions that support a very large algal population kill off the Daphnia is because the algae increase the pH into the, all right, if we don't have any grazers, we can get pH as high as 11. The Daphnia can barely tolerate 10. Even with Daphnia populations, the pH can get into the high 10s. And I think that this may have some relevance on algal blooms and why grazers don't get rid of algal blooms. But that's kind of into the hypothesis range.
Cool. Yeah, that's an interesting connection. Another question we've got for you is, you were mentioning that there was some buildup of unrecycled materials in your systems. Do you think that that's due to like an incomplete metabolic representation from the microbes? Have you tried supplementing your systems?
I have, and unfortunately, the experiment was to some extent compromised. Okay, I found out what was making the noise. It was my own phone. I've tried adding Lake Washington microbiota, but I kind of compromised that experiment, unfortunately, by forgetting to put the bicarbonate in.
I remember that.
But so we're going to repeat that experiment and hopefully make different mistakes next time.
Very nice. All right. We still have a couple more questions. Really quick, Oscar wants to know, what was the photo period in your MAD systems, and how did the pH control affect that?
Most of our photo systems are 12 hours of light and 12 hours of dark, but we usually go 3 days with short day, and 3 days with long days, but always on a 24-hour cycle.
Okay. And we've got time for one or two more. Ray Wheeler wants to know, I think you alluded to this, the Jack Myers Priestley experiments. That's the one where it exploded, right? It had the mice in it. Yeah. Ray wants to know, he wants to know your opinion if the buildup of, hold on, I need to parse this really quick. He says, I think they saw the CO2 buildup of O2 as well. I think you dropped a C somewhere.
Well, I think in our system, and part of the problem is that we're supplying it with sodium bicarbonate, which, as I pointed out, only half of the carbon is photosynthetically available to the algae. We're starting with gaseous CO2. We might not have that problem. And if I'd go back and review my gas laws, I actually have CO2 tanks and I have balloons and I have thoughts about doing it, but we haven't pulled it off yet.
That's pretty interesting. Okay, cool. And with our last minute here, do we have a simple question to throw you? Well, I don't know if this one's simple, but it's a good one to end on. Andrew wants to know that if you think we'll need to create our own like endosymbiosis of sorts using genetic engineering to have sustainable closed ecological systems.
Well, certainly it would be an interesting thing. I don't know enough about communities of organisms that would be completely able to recycle all of the, and I suspect that we're going to have to go into anaerobic conditions. Certainly some of the nitrogen cycle things happen under anaerobic conditions. I've tried to play with having substrates that might have little anaerobic zones in them, but the chitin can't get into those little zones. So I've played with some of these things, but it's a big area that needs to be researched, because anything that persists as a waste product is going to be a waste of new resources for a closed ecological system.
Mhm.
I mean,
Okay.
we're it's sort of intuitive that we want to produce food, we want to produce, we want to produce, we want to produce. But what I'm saying is we better pay more attention to we got to recycle, we got to recycle, we got to recycle.
Mhm. Yeah, absolutely. Well, thank you so much for this insight, Professor. This was a fantastic talk, and I'm really glad to hear it from you. We got to go to our next speaker, though. So let me introduce Dr. Dragos, who's going to tell us about bioengineering mineral weathering. Please take it away.
Thank you so much. And while I'm sharing my screen, I would like to bring back the comment that one of the participants raised, that we should, fail and learn and fail some more, and that is where all my activity lies. I'd like to shortly introduce myself. My name is Dragos Zaharescu, and I work at the University of California, Davis, on topics related to rock-life interactions, an ecosystem spanning climate gradients from deserts of Arizona to subtropical temperate forest of Georgia, rainforests of Alaska, Hawaii. More specifically, I focus on dissociating abiotic from biological interactions. And I apply this knowledge I gained from Earth ecosystems on how Earth ecosystems work to developing ways to use mineral resources for food productions and space applications. Previously, I worked for 5 years, 6 years, if I remember correctly, at Biosphere 2 in Arizona, where also focused on experimental biological weathering. So basically live rock interactions from microbes, plants, and fungi. And before I bring in data, I would like to take a moment and reflect on our own Earth. Soil on this planet is one of the most complex systems we know, on which more than half, about 59%, according to a recent study of Earth's life, depends. This very fine layer that covers the continental crust is the evolutionary result of 4 billion years of interactions between life and rock and the transfer of nutrients from life to rock to life, and is directly responsible for the rise and fall of many, if not all, human civilizations. What I find very fascinating is that for the first time in the history of humanity, particularly in this civilization time frame, we are capable of 2 extraordinary feats. One, we're capable of engineering tools that can unravel the intricate properties of complex natural systems such as soil, all the way to nanometer and molecular scale, and if we want, even atom scale. And 2, we're capable of engineering tools that can expand the human civilization to lifeless worlds such as Moon, Mars, and what other planetary bodies in the future. So through my work here at UC Davis and at Biosphere 2, I try to expand this fundamental knowledge on soil genesis on Earth and learn from how soil builds complexity here to bioengineer extraterrestrial mineral resources for use in bioregenerative life support system. So with this, I introduce the topic of my talk, which is how we can actually bioengineer, how we can develop this knowledge to use mineral resources and support life. So I'll bring 2 examples. I'll bring examples from the natural world. Obviously, before that, I would like to introduce the team of people or teams of people I worked with, because without them, my talk would be kind of empty. Nowadays, a lot of work requires interdisciplinary and transdisciplinary collaborations, and I love that because I can fail big. And still get along with it. So yeah. So I'll bring two examples and three examples and one example. So I'm gonna talk about our work here on Earth across this ecosystem, give some examples, and then how I took this and enclosed it into small chambers and tested in a more controlled environment. So in this example, it was a continental scale field experiment. We deployed little mesh bags that we filled with granular rock. We choose like 3 rocks: basalt, granite, and quartz. Quartz, we took it as a control because it's kind of nutrient deprived. And we deployed these mesh bags in several biogeographic areas in the US that differ in climate and ecosystem type. So you see here on the left, the area where we deployed these mesh bags, maybe in Arizona, the desert landscape. You see here kind of a picture from there with the mesh bags that were deployed and collected 5 years later. So I subjected them to ecosystem weathering for 5 years. I think it was 6 in this case. But anyways, so we have Arizona lowland and we have Arizona highland, those sky islands in the middle of Arizona, which is pine forest, and we deployed there. And on this right-hand side of this particular panel, you have the subtropical rainforest, subtropical temperate rainforest of Georgia and South Carolina. Anyways, we deployed them. We collected them after a period of time, and we opened up the mesh bags. We removed the sand and looked at the transformations that those sand particles experienced, and particularly we did liquid extraction, so looked at the nutrients, and this principal component analysis here on the right, you can see that the ecosystem rock discriminated very well in terms of how nutrients get absorbed or deplete. And on the little plots on the left-hand side of this PCA, it clearly show that, for instance, aluminum and calcium. We should get this bar. Yeah, aluminum on the top and calcium on the bottom. It show how they either experience preferential leaching or preferential loss from those mineral mesh bags. And we further did, this is an inorganic analysis, and we did also extracted the organic fraction and looked at what happened in the mesh bags during this period to the organic material. And as you can see here, there's a trend, there's a control here in the red box show the organic fraction is quite low on the samples that were not deployed in the field, whereas in those that were deployed in the field, you see here with the blue little circles that in the desert highland, which is the first bar, and desert lowland, the second bar, you have an increase in material that are lipid-like, and a decrease in material that are tannin-like, where have where there's more forest, there's more tannin kind of compounds. Where the landscape is more open, you have more like microbial kind of dominated ecosystem versus like tree and fungi dominated ecosystem. So anyway, this gives a sense of the organic and inorganic fractions that get added or removed by the ecosystem from those minerals. So such knowledge of inorganic and organic weathering processes should be critical when developing bioregenerative life support system, because ultimately we would like to mimic some major processes that happen on Earth that sustain our life here, and we take those and enclose them and control them when an extra outside there. Now with this with this experience at Biosphere 2, I set up to answer another question. This is kind of large scale experiment where factors can be very confusing. So by taking it indoors and controlling some parameters, you kind of you can kind of better determine the mass flow of nutrients, from the rock to the different weathering reservoirs, like plant microbes and different solid pools. So at Biosphere 2 in Tucson, and now I do bring a photo, a night photo that Mark wanted to show. Biosphere 2. So inside there, in the desert biome, I created this what we called rockubators, which is basically a set of 6 environmental chambers where we control for. This is a close-up picture where we control for the air, the air input, and we control for the type of material of rock material. It's a super sterile environment, and we can actually dissociate abiotic from biological weathering factors. So see, and here is just an example of one of these modules. You have the aerial compartment here with the water hose that brings ultra purified air. And then you have a soil environmental compartment that sustains all these columns, which are sealed from the. We are connected to the air compartment, but they are sealed from the outside. And then we have underneath the sample collection compartment. So it's basically a column kind of highly replicated column experiment. And here on the left hand side, you see the opening of one of these columns with buffalo grass, which we use, one of the plants, growing out of pure sand. And here underneath it on C, you see the root system. You see basically how much this plant started as a seed. The only food it had was ultra pure water and just mineral rock, sand size. So you see how this rock got transformed, and the CO2 in the air got transformed into the biomass. So most of the plant energy investment happened underground, right? And following that is a little image with the arbuscular mycorrhizae. We use arbuscular mycorrhizae, and again the columns they have a water system there in such a way that prevents preferential flow and so on. There's a lot of details that I can dig in. But anyway, so this experiment allowed us to do a lot of things. But I think one of the most important was to calculate the mass balance and follow the about 55 chemical elements from their origin and the rock pool, all the way into the water. See how much proportion ends up in water, how much proportion ends up in secondary solid fractions, how much gets taken up in plants, and so on, right? So in this rockubators, we had 4 types of rock: basalt, granite, rhyolite, and schist, which kind of represent represent a great part of terrestrial crust. They're mostly igneous, and one is metamorphic. And as a biological treatment, we used either abiotic microbes, an increasing order of complexity, abiotic microbes plant mycorrhiza, and you use 2 types of plant, 2 types of mycorrhiza. So it's 3 times we sacrificed the experiment every 4 times, so it was highly replicated experiment, and we analyzed a bunch of chemical elements from carbon, nitrogen, all the way to rare earth elements, which is kind of most of the chemical elements in the periodic table. So it's just an example of basalt. You get this kind of graph where you basically can follow the distribution, the compartmentalization of each chemical elements from rock into life. And you see here the example of phosphorus and iron. You see how with increasing ecosystem complexity, there's significant effects on chemical weathering and element loss and uptaken by plant. And some elements have more, some have less, some have different patterns, but still it's kind of small. This blue is water, orange is root, and green is shoot. So this is kind of the plant, water, and these are kind of very small slice of the overall weathering, which is on the grays, with the green, no, the gray, black being different solid fractions there. So what weathers and ends up on life is kind of very, very, very small, right? And you can easily see it even in the rare earth elements. So you found something extraordinary. You found biosignatures embedded in the rare earth elements patterns, but they are kind of we don't know much how they interact with life, but we can see here that there is clearly an ecosystem effect. And I have a paper that shows there is more just than that. They're kind of preferentially uptaken when phosphorus is low, and they're a pretty interesting group of elements which are important for the civilization in different ways now, but they're kind of important for life outside our planet. So I think it's a kind of group of elements we should keep an eye on. Probably it's going to be the ones that are going to fund over a lot of our mission out there. Again, you see an increasing trend in rare earth elements weathering, immobilization, and uptake and the plant tissue. Now, obviously, this raises the question. Okay, he brought an answer to the question whether plants can actually survive on just bare rock and water, and the cleanest possible water. Obviously, to this water you can add all kinds of stuff, but I wanted to see a very clean system, in a basic way how it operates. So it is survivable. Plants survive. It does a lot in growing root biomass, but then they can grow only so much, only so fast, and we're probably not going to be able to rely on them as the only food source. But they will be an important component of a bioregenerative life support system in the sense that we can now extract resources using different life forms from the regolith itself, either on Moon, which is our nearest body, or out there Mars. The next question I had was, how can we accelerate this weathering process? And I had a nice discussion with different colleagues, including with Ray, and we applied for a NASA submit a NASA proposal to plant sciences, space biology, plant sciences. We got funded for 1 year. So we kind of designed a system that can replicate some of the high energy conditions that you would find on Mars, and subject the rock material to those conditions and follow the weathering process. So this is a little sketch, and then I designed a 3D model, and we ran some tests in the lab. And here is a bean growing on basalt, and analyze the basalt to see there's some preliminary analysis to see how we can handle the post experimental processing of the material. And we went to Iceland for a different purpose, a different expedition out there to look at the soil formation in Iceland, and visit a number of places and brought back different types of basalt, which differ in their physical properties. And this is kind of the locations that we visited. So we have very fresh basalt. We visited in 2021. So you see number one here was a fresh eruption. And then we visited basalt that were 2 million years old, and basalt that was highly vesicular versus basalt that was more like glassy or more iron, less iron. And with these samples, we have them in storage, and we are now in the phase of starting to process them, to break down these rocks into granular material that have similar grain sizes. So we control for that and so on. And you see here the lava flows, number one from 2021 eruption, and the number four. And number four is a very, very vesicular, highly vesicular, high silica content basalt that erupted in 2016, which you can basically break it up in your hand. So I think the physical properties of the rock are going to influence the leaching behavior, the release of chemical elements, and ultimately the plant growth. And that is on the side. We have the material. And
apologies for interrupting you. We're coming up on the end of your time. Is there a way that you could summarize so we could get to the next speaker?
Yeah.
Thanks.
1 minute. Thanks. We ran preliminary analysis and see here just comparatively two rocks. two rock grains. And we looked at the chemical analysis, and we saw that chemical properties of basalt that we collected, which are in this colored balls, are within the Mars range. So kind of we can use it as a Mars simulant. And we started the build-up phases of our chambers, and we went, collected all the materials, brought them, cut them, broke them, cut them again, glue them, break them, cut them, until they all fit together into these two chambers, which are behind me, and they have a white, radiation-rich light that illuminate them. They have an aerial compartment, a experimental platform on which we're going to run the experiments, and access ports. They're all sealed. This is the terrestrial, and then we have the Mars environment, which has to be a highly closed environment. We're going to add high intensity UVC radiation to add an energetic factor and CO2 based atmosphere that replicates the Mars conditions. So we're kind of in this stage where we're setting up this new experiment that I can, during our questions, I can show you around. This is just right. Thank you.
Yeah, thank you, Jagos. That was awesome. That was really, really cool. I'm interested in how your weathering could be applied to like regolith simulants, for example, or actual regolith. And it's cool that you actually have the technology right behind you too. I'm sorry that we don't have time for questions and that I had to interrupt you, but there are definitely some questions in the chat, and if you could answer those at your leisure, that would be awesome. Yeah, thanks so much for presenting. Super cool. Up next on this agenda, we've only got 2 more talks, guys, so hang in there. A surprise, we're doing Christine again, but this time Christine is going to tell us about microcosms, mesocosms, and macrocosms, and the issue of scale in facilities for ecological life support. So take it away, Chris.
Okay. Thanks again, Patrick. I seem to have gone backwards on my presentation. There we go. You should be on the first slide now. Okay, so what I was hoping to do in the few minutes that I have is introduce you to the concept of scaling issues in experimental ecosystem test facilities. This presentation is going to be extremely high level. It's kind of like kindergarten version of ecosystem theory. It's a research area, though, that I've become very interested in and I know very little about. But it's not a topic that's discussed very often, I believe, and I think will be really important to the design of operational full-scale space habitat ecosystems. So I'm going to present to you a problem to think about without necessarily having an actual current solution that maybe we can discuss as a group. So just first, this is a reminder of the purpose of an ecosystem for human life support, which I always want to bring people back to the fact that we are trying to support humans. So it's trying to maintain an optimal habitat that compensates for disturbances that are created by human metabolic activity. So this ecosystem provides this metabolic counterbalance or reciprocal to the humans living in it. It consumes human excretion, it restores what the humans consume. And an artificial life support ecosystem, as we all know, now exchanges energy with the outside, and it can be either open or closed to matter exchange. Closed ecological systems, or, well, ecological systems in general can contain stores of needed substances, store them, or it can regenerate them. That's the closed part. If your material cycling is well coordinated, we can hopefully continue this indefinitely. And you can get that closure with biological components or physical components. I'm not one to say that necessarily everything has to be biological all the time. If there's a robust physical chemical component that can serve a purpose to support the biology. And ideally, we want full closure, but it can also be partial, where sometimes you might have to store some substances. And if we're going to design one of these, we're going to design an artificial ecosystem to support humans, we have to apply principles of ecology, right? Of systems ecology and ecosystem theory to study the material and the energy exchange processes between these biotic and abiotic components in a spacecraft. So systems ecology, as the name says, which Jane Shetzoff tomorrow can tell us probably a little bit more, uses a systems approach to explain these characteristic processes and reactions of ecosystems. And just to let you all know, because a couple of years ago this was new to me, there is such a term as ecosystem theory. Ecosystem theory is a set of principles and properties that are common to all ecosystems, forming the basis, are formed by founding systems ecologists like Eugene Odom, like Howard Odom, Claire Folsom, that Mark Nelson mentioned earlier, Joe Hansen, other systems ecologists. And I won't go into all of this here, but this is kind of the basic high level. Hey, there is this field of science called, and there is a such thing as ecosystem theory that says there's these common principles and properties that guide and define the behavior of an ecosystem that is more than the sum of its parts. That includes things like conservation of matter, producing entropy, basic biochemistry of the living organisms. They need free energy. There's diversity that defines the system, its hierarchical organization, how much information content or complexity it has, how much buffering capacity, and there's other emergent system level properties. So why do we care about all that? If I'm going to design an ecological life support system, we need to understand these properties, right? And the effect of our spacecraft constraints on those properties, like we talked about mass, volume, pressure, power limitations. And we use models to simulate, to predict, and to verify how the system will perform so that we can try to find a good or the best design that we can before we spend a lot of time and money building it and testing it. So now we're going to model our ecosystem, and typically how this is done is by using these network diagrams with bins that represent different components or stores or functions. In this case, you just got your basic autotrophs, heterotrophs, consumers, and decomposers in a bin for inorganic nutrients. And there's connections of the flows of matter between them. Could be flows of energy as well. And these compartments, they're going to grow in size, they're going to shrink, they're not all going to stay the same size, but hopefully you'll have some sort of a dynamic equilibrium in a closed system where your total mass should stay constant overall. And so this mass balance technique is often used for modeling. And this is a very simple example of a network model. But these models can get really complex very quickly. In a mechanistic ecosystem model, especially as the number of bins, organisms, trophic structure starts increasing, and the number of elements that you're tracking, and then there's feedback loops between these material cycles. Eventually, our models get pretty darn complex, and we're going to have to validate them with live experimental facilities to not only build them, but to test them. So how do we do that? How do we validate our models? To test them, we can do some benchtop experiments, right? In a lab, we can measure component processes. We can have a plant growth chamber to monitor photosynthetic rates, for example. But ecosystems really are very complex. They're greater than the sum of their parts. There's feedback loops between different components and different elements or feedback mechanisms. So these component level tests, they're not going to tell you a whole lot about how the links and the components are interacting with each other. So what we need is integrated ecosystem level tests, right, to answer a lot of questions. Really important is to answer things like reliability and robustness, and how well can the system repair itself over time or recover from a failure. And empirically measuring reliability and robustness, you can imagine, requires a lot of replication and a lot of test conditions across a wide state space. And it takes long duration experiments if you really want to capture your system's performance and behavior over time and capture failure rates. So the reason why only, at least I think the reason why only a handful of facilities have been built worldwide to do these kind of integrated full-scale life support system tests with humans in the loop and with mass closure is that they're big, they're expensive, they take a lot of time and manpower to operate. And so therefore it is hard and expensive and time consuming to get replication. Granted, we need a lot more of these facilities. I won't knock them, but I'm saying there's difficulties and constraints and why there haven't been that many of them and why it's so challenging to create. So is there another way we can test other life support design configurations and on a budget? And one way be with small scale physical models that are comparable in function to the real thing, to the real system. I'll go right back to a comment from Professor Taub, who said, people think microcosms are dumb. I don't think they're dumb at all. In fact, I think microcosms are extremely smart and incredibly useful if they're designed well. So that's what I'm primarily trying to discuss here today. So you have these small prototypes. It enables you to have faster cycling times so that you can reduce the size and the cost of conducting a lot of experiments. They're small, they're controllable, they're replicable, they're low cost. You can make them scalable in order to make inferences from one size system to a larger size system. They can be open or closed to material. They can have a few or many species, and typically you have some way of measuring metabolic rates or other parameters inside. Their use dates back to 1851, and I don't have a reference on my slide right now for what that was, but some microcosms built in the 1970s are actually still alive today. That is the one of the Folsom microcosm experiments that, again, I think Mark Nelson alluded to previously. But if we're going to verify models, so we're talking about how do we test with a real live system to be able to see how well our models can predict what it's going to do. If we're going to do that with small scale microcosms, they have to be properly scaled to represent the dynamics of the larger system that you're actually going to operate. And you need to be able to extrapolate from the small system prototype to the big one. The bottom left picture here actually is the one someone correct me because it's been a long day and my memory is waning. I can't remember the name of the gentleman who who has this microcosm that has been going since I think 1970 something for decades. It's still alive today. But we need to know whether our downscaling from large down to small is affecting our system dynamics, and dynamic distortions might occur because of changes in your time, your process time, how big the system is, but also in like things like geometric relationships. And we'll talk about a couple of examples of that. So if we're going to design an experiment, we need to preserve functional similarity and the ecological relationships on any scale so that your test system is representative of what would happen operationally. That sounds hard. So how do we do that? This is a very little studied area, I think, of closed ecosystem research, and I think it's critical to our ability to be able to prove out and control bioregenerative life support. There's a book, Peterson, Enclosed Experimental Ecosystems and Scale, that provides a really detailed summary of different quantitative approaches to extrapolate your findings from different microcosm studies to different size systems. He discusses a lot of different spatial scaling factors as well as other types of scaling factors that might affect your ecological dynamics and processes that you are seeing. So things like geometric relationships, just simply the size of your container, right? If my depth has changed, my depth might affect my light transmission. The volume of my container might affect my mobility of the organisms inside of it. Even the shape of my container could affect things like heat transfer that needs to be extrapolated from one scale system to the next. Temporal scaling, if you're shortening time scales, you got to ask, are you able to see all of the process cycles that you want to be able to observe on that chart and scale? Is the frequency matching? Or observable? Is the frequency of those cycles observable? Are the element residence times throughout the network, throughout the bins, preserved in this microcosm? Physical scaling factors like your mixing of your fluid flow, which can affect your gas exchange and settling rates and all kinds of other properties. How's your light being transmitted? Is there scattering effects that you brought in because you now have a small little box? Are the nutrient ratios the same from one size system to the next? And then how about ecological complexity? So how do we represent diversity of a large system in a small one, or the right trophic depth to be representative of a full-scale system? Again, this presentation is all about more questions than I have answers for. But there's a concept called similitude. It's used for designing and testing engineering models. The engineers might be familiar with it, scientists maybe, but it's that concept that's used for like a model of an airplane in a wind tunnel. Models have similitude for the real application if they share geometric similarity, kinematic similarity, dynamic similarity. And I won't get into what those mean, but its main application is in fluid mechanics, right? I think we've all heard of Reynolds numbers, which is a great example of a dimensionless number that involved in similitude for aerospace engineering and hydraulic engineering to test fluid flow conditions with scaled models. So this concept of similitude is strongly tied to dimensional analysis. For those of you who haven't heard of dimensional analysis, there might be properties of a scale invariant system that are dimensionless, that can describe and predict your ecosystem behavior no matter what its size is. This would be really helpful if we want to design a scaled up system for more crew. We want to now have more people without having to build a larger test facility or a mock-up. And then also if we want to do a bunch of cheap, small prototypes to run a lot of experiments under a variety of conditions. So Peterson and other authors have suggested dimensional analysis could be a tool for scaling our experimental systems while conserving ecological relationships, regardless of their dimensions. In dimensional analysis, basically you combine model terms such that the units cancel out, and it results in things like percentages and unitless parameters like ratios. For example, a metabolism might be represented by a ratio of photosynthetic to respiration rates. So I have some other examples too, like maybe, I'm just spitballing, thinking off the top of my head because there's not been a lot of research or public literature on this. Ratio of buffer capacity to total mass could be an example. A similatory ratio is a commonly used one, so the amount of oxygen produced per CO2 consumed by a primary producer. Maybe it's the ratio of atmospheric carbon to organic carbon. That's one that Mark Nelson mentioned earlier, or organism lifetime to a material residence time. So you can go on with these different ideas of how we might represent an ecosystem's properties in a scale invariant way. So just wrapping up, I propose to this group, if I may, perhaps a new area of research called ecological similitude. It's an ecosystem science of scale that defines non-dimensional ecological parameters to quantify the similarity between life support ecosystems that are different temporal and spatial scales. And I think it's a critical area of research in order for us to be able to predict mass and energy exchange in many different spacecraft configurations and operating environments. Again, I have more questions than answers at this point, but I wanted to at least introduce you all to this concept as we're thinking about test facility development. So that's all I have, Patrick.
All right, thanks so much, Chris. That was yeah, that was super intense. I was barely keeping up, to be honest.
Oh, sorry,
I have a lot to learn. So I don't know, everyone in the chat was definitely invigorated by your talk. I don't know that anyone had a specific question. I guess if I were to ask you one, like, is there a specific, I've already lost the terms, but you were saying like unitless comparisons, like unitless measurements. Is there one that you think is a particularly pressing one that should be investigated?
No, all I know is I wish I had about like 1 month of my life to study that question, to see if we can come up with some suggestions about what would be dimensionless parameters to describe a life support ecosystem to allow us to say this one is representative of this larger one. And also what variables do we want to be careful about that are extremely scale sensitive.
Sure.
So no, I think automatically what comes to mind is things like I was watching Mark Nelson's talk, and things like the ratios of elements, buffering capacity, how the rate cycling rates is going to be pretty important. But how do you turn that into a dimensionless number? So, like for example, the lifetime of an organism versus the material residence time could be one. But again, I'm just throwing stuff out there. And no, I don't have one in particular.
Yeah, I mean, I think you reached your goal. Everyone here has clearly thought it was thought-provoking. So great work. Thank you,
Christine. Got to make small, dumb microcosms smart.
Yeah. Okay, so on to the final talk for today. We've got Dr. Kristen Peach from NASA here, who's going to tell us about space ecology and the Open Science Data Repository. So I don't want to take any more of your time. Please go ahead, Kristen.
All right, thank you. And I promise everyone I will be really concise because I know it's a Friday afternoon for me and maybe Friday night for other folks. So I will keep it quick. Confusingly, I also go by Chris. So I have just been like jarred every time you said it, but my name is Kristen Peach. I've been at NASA's Gene Lab, which is now part of the Open Science Data Repository, for about 2 years. But my master's and my PhD were both in the ecology and evolutionary biology of wild plants in California. So I started my career as a field biologist. Before that, I was at USDA doing some work on weevils and invasive aquatic plants. So I was very much an earth ecologist and plant biologist until the last few years. I did a postdoc with the National Center for Ecological Analysis and Synthesis. So ecology has been a part of my professional life for a long time. But I'm here today because in the Open Science Data Repository, we historically have focused on what would, by a purist, be considered more biological types of studies, but we're really interested in expanding our scope to include especially ground analog studies that are applicable for spaceflight that maybe have fallen into the more ecology category. So I was really glad to see this workshop and really happy to be here. Let's see, sorry. Okay. So I've taken the little cartoons from the Space Ecology website as a presentation roadmap. So I'm just going to go quickly through them and review some of OSDR, which is how I will refer to it now. I know it's very hard to stop calling it Gene Lab, but we're trying to be really inclusive of ALSDA, who's our new partner. So we're calling it OSDR now. Identify the gaps in our repository, and then hopefully get you all really excited about submitting your data to us. So we're really focused on open science, and the way that we define that is listed here. I won't read it to you. I know you can all read just fine on your own, but we're really focused on making all space flight relevant data publicly available. And so we facilitate synthesis science, which I think is really a theme of this workshop, is like we should all be working together, and the collaboration makes this work move faster and better. And that's really the foundation of what we're trying to do at OSDR. So again, I think this is the perfect workshop for us. So now we provide access to the raw and processed data from space relevant and space flight experiments, not just NASA funded, although probably the majority of our studies do have some NASA funding, but that's not a requirement. And so we combine Gene Lab, which you've heard a little bit about already today, and the Ames Life Science Data Archive, ALSDA. You know how NASA loves an acronym. And so now we are a new acronym, OSDR. And so we'll have both omics data, which again, you've heard about being associated with Gene Lab, and phenotypic data. So things like plant leaf area and biomass and photosynthesis assays, etc. And those are our logos. We don't have a united logo yet, which I think is a huge problem, but we're working on it. And we have more than 60 plant studies, which I'm especially focused on. I know that ecology includes many things that are not plants, but I am plant focused because I'm biased in our repository, but we're hoping to really expand that to include, again, more studies that are interactions between plants and their environment. We have, of course, more robust statistics on our omics assays, because GeneLab has been around longer than ALSDA, or it has been a more organized repository in this sense for longer. But we have, in addition to the assays you see here, these new ALSDA assays, which include morphometric analysis, flow cytometry, et cetera. So a lot of the type of work that I've seen presented today would be a really great addition to our repository if folks are willing to share it. And so I'm just going to show two quick case studies of the types of data sets we have in our repository to give you a sense of how this can be a powerful tool for you as PIs and ecologists and researchers, and how it can be powerful for your students when they don't have time to collect data and just need to analyze data that already exists or things like that. And again, if you're looking to identify patterns across spaceflight research, we're a really good resource. We're looking for all publications that examine the effects of microgravity on a specific ecotype of Arabidopsis or something like that. And the first one is around lunar regolith, and I saw in the chat, I too will die on the hill that the word soil means that there's life in it. So I hear that. But we have, in this study, it was one of our first ones in which we included both genomics raw data and images of plants from which you could extract, plant growth data and things like that. And we have, all of the protocols for how the data was collected. We have a sample table and then assay tables that are specific to each assay. And this is the type of synthesis science we hope to continue to host in the repository. So we can really do that important work of connecting phenotype and genotype, which is at the root of so many of our investigations. Another example includes RNA-seq data and images of seedlings exposed to different light treatments in space. And that's OSD 120. I have the DOIs listed for both of these, but they're also quite easy to find if you search via that link that Christina, my coworker, has posted in the chat. And with many of these data sets, our internal team has processed the raw data. And so you can also use these really fun data visualization tools within the repository. This feels like a safe space, so I will admit that I have a lot of trouble with 3D PCA plots. I can't learn anything from them, so I'm going to change this and look at a 2D one. But we have lots of different types of data visualizations based on the raw and processed data in our repository. And we're really hoping, in addition to these omics tools like this heat map, that we can add non-omics data visualizations to those. And in the next 2 months or so, we're really hoping to showcase our multi-study visualization tool where you can compare patterns of gene expression across studies instead of just looking at one individually. So the thing that we need to do better at is more ecology data. So I'm sure sadly some of you are aware of the National Academy's Decadal Survey, which prioritized these 11 key scientific questions that we as biological and physical sciences at NASA are supposed to focus on in the coming decade. And a lot of these are ecological in nature. So how does the space environment influence biological mechanisms? And basically, how do we get organisms to survive in space while figuring out all the different interactions that require their survival and reproduction? And happily, many of these were the types of questions that ecologists and biologists are already interested in, but it did highlight the need for us at OSDR to think a little bit outside our traditional box of the types of studies that we had specifically focused on in the past. And especially I'm grateful for this because there's only 2 of us plant folks at OSDR right now, so we're feeling very validated. So all of this work, the work required to answer these questions in the Decadal Survey will be really improved if we can work with ecologists who are doing the types of experiments needed to baseline these efforts, and we can get those and support those people. And so we can start to think about what the questions are moving forward and what we're actually capable of already answering right now with the data that already exists. And some of the examples, again, lunar regolith has been a really hot topic the last few the last months. It was especially popular in the decadal survey. We only have 3 studies right now in our repository that examine that, but one of the ways we're trying to encourage folks to submit their data to us is by creating specific submitter templates, metadata templates, and working with them really closely so that it's really easy for someone to give us their data and feel good about the way that we present it to the world. And I should say it's a given that we don't make data public without a data submitter's express permission, unless it's already public somewhere else. So there should be no concerns about getting scooped because you decided to work with us. So making things like these lunar regolith templates where we think about how best we can describe the substrate in which an organism grows are one of the ways we're thinking about improving our whole infrastructure to do a better job of incorporating these types of studies into our repository so that we can enable the type of synthesis science that we have with projects like the rodent research missions, but for plants or ecology topics. And so what I really like from you all, if you're not already part of the OSDR analysis working group for plants, it's a really wonderful group. I have the QR code here, but we can also provide links. The working groups are really great opportunity to start collaborations or work on collaborations, to ask questions. There's students, there's PIs, there's every career level possible in these AWG meetings. They're only twice a month and you don't have to come to every one. So there's a really low bar for entry, and we would love to have you all there if you don't already come. And so I encourage you to at least consider that. Additionally, if any of you will be at ASGSR, we're doing an analysis working group workshop, which Christina and I will be involved in leading. I won't physically be there, but this will be right before ASGSR main session starts. And I really encourage you all to come and check it out. And I'll end with, we also have, if you are someone who works with omics data quite a bit, we have some public data processing pipelines that are available on our GitHub that are becoming more and more popular with our users, and we really encourage you to check those out. And if you have suggestions for improvements, we're always happy to take pull requests. So with that, I will end and open it up to questions.
Thanks so much, Chris. That was fantastic. I've got a couple of questions for you, although Christina has been very adroit in answering them as they've come up in the chat. So I guess some of the ones that haven't been answered yet, like from Greg, he wants to know, does your repository have any data about plant photosynthesis in the MEC models? Modified energy
I
cascade?
don't think so. I don't think, would that be entirely modeled data? Because right now I don't think we have any data sets that are entirely modeled data. So
okay.
Not yet, but we could.
Sure.
Well, I think the question might be whether there's a way to have data that could be used to create MEC models from actual growth experiments.
Oh, yes.
That's what was being asked.
Okay.
But the question
Yes,
is,
then
what
that
information is needed
that we
for the
have.
MEC? Sorry, Krista, go ahead.
No, that's okay. I'm trying to read the chat while listening, which is a terrible idea. So if I understand the question correctly, we might need a little bit more time before we produce something that would be ready for that type of effort, just because it has traditionally only been a raw omics data repository. And so the number of studies where we've added things like photosynthesis data are relatively minimal, but that's the goal. And we already have a lot of the data. It's just a matter of getting it organized and curated and then out to the public, which is no small feat. And I see the question of, are you meshing with NCBI databases? We ingest data from NCBI. So any spaceflight relevant study that's in NCBI that is public already, we have ingested, and we stay pretty on top of that. There is a project to make that a programmatic process that has not been approved, and I don't know if it ever will be, but we have pretty good overlap with the type of data they have in their repository right now. I think we do a slightly better job, but I'm biased.
Sure. Okay, we've got a question from Richard Barker, who says there are tools for environmental metadata visualization currently under development. So if people submit environmental data from their regolith ecology experiments, for example, could it be compared with the data for the spaceflight environment or other space biology related environments?
That's a great question. It certainly could be. You know, the goal is that we can, in a few months, or at least in 2024, that we can compare data across studies. I should say Richard Barker also works at the Open Science Data Repository, so maybe he was
sounds like a loaded question.
pitching me an easy one to help me out, which I appreciate. But yes, hopefully that's the goal. We would especially be interested in, I'm interested right now in ingesting a lot of studies on things like just nutrient poor soil or high basalt soil or substrate or medium or things, so that we can really understand these kind of, I call them regolith adjacent studies, and hopefully learn a lot from those, and that could move the work on actual lunar or Martian regolith forward faster.
Gotcha. I was not expecting one of the takeaways from this workshop to be that regolith becomes a taboo word to use, but here we are. I'm also on the soil is alive hill. Okay, I think these are all of the questions. Yeah, I think that's all of the questions so far. We still have a few minutes left in your presentation. Kristen, is there anything you wanted to add on, or oh, Jane wants to know how to join the working group.
Oh, yes. I can add a link to the chat if y'all missed the QR code. I know QR codes are kind of goofy, and something like this, nobody wants to pull their phone out, but a long link didn't seem easier. So I'll add the link to the chat, and certainly get all of that information out to everybody.
Great. Yeah, fantastic. And thanks for doing this work too. Open science is so important, especially, I mean, that's one of the themes of the workshop, right? We're trying to collaborate, and that is a critical aspect. So we are here at the end of the program for the first day. I mean, this says closing remarks. I don't have anything to say, unless Chris, do you?
I had one actually quick comment for Kristen and the group that I missed the opportunity there, but I was thinking maybe we might just spend a few minutes and let folks put in feedback into the chat or the mural or wherever of their own closing comments, and then we'll wrap up.
Sure, yeah, that sounds good. Yeah, okay, well, in that case, I think we're... Oh,
yeah, I did have a question, Kristen. Back when you had a slide talking about needs or gaps or something to that effect. And of course, Arabidopsis comes up as like the model space plant. It's perhaps a loaded question, but I was wondering if we as a community might start identifying model space crops, model plants that are potential food sources that we might actually eat and have nutritional value.
That doesn't feel loaded.
I think duckweed should be one, but there's others.
No, we'd love to have your duckweed data. We do have you know, maybe 6 or 7 other plant species other than Arabidopsis thaliana.
I think just like identifying what is a model space crop that you can start building a lot of flight heritage with, that similar to the amount of heritage that we have with something like Arabidopsis. And there's a few different candidates one might use, things that are easy to grow. Microgreens, for example, could be Brassica rapa is a big famous one that has some flight heritage. Anyway, I'm just throwing the idea out there if we could start using this term of a model space crop.
Yeah, I mean, it's something we think about a lot in the plant EWG, and I know that there is a cost to being brave enough to pick kind of a new non-Arabidopsis species for your very expensive spaceflight study, and so we totally understand that. But there are definitely like I said, 6 or 7 other plant species in our repository that we have data for in our repository. So it's not as limited as just Arabidopsis thaliana, but I agree that kind of as a community or as a field, it would be great if there was a consensus. It might make people more confident in writing a proposal to do something that's not on
right, without having to justify it as strongly. Why am I using this plant? There's a question, Patrick, from Priya, whether there's any data on ancient plants like Haloarchaea. I'm gonna mispronounce.
Unfortunately, no. I keep hoping or thinking maybe even some ginkgo data would be interesting, just because it's so radiation resilient or something and so ancient. I think ancient plants could be a really good genetic reservoir of resilience to the type of extreme conditions that plants are expected to experience. But again, I think it's unfortunately been a NASA funding limitation more than a limitation of imagination.
Well, here's hoping that the new decadal will maybe provide some funding avenues.
Definitely. But if anybody knows of or has done research themselves on either radiation resilience or kind of just stress resilience in ancient plants that they have the raw data for, I would love to put it in the repository. So please let me know. I'll put my email in the chat.
Dragos has his hand up.
Okay, I could make a comment. Okay, it's not going to come into focus. You introduced the enclosed.
That looks familiar.
Yeah, the enclosed experimental ecosystems and scale. That was the second book, Scaling Relations in Experimental Ecology. And I'm sorry, this isn't going to come into focus again. But this was a 10-year effort, largely from University of Maryland, on the whole question of how do you extrapolate from small experimental systems to real ecosystems. Because they were having serious pollution problems, and your small systems, usually your light gets all the way to the bottom of your container. But if you're talking about a real estuary, you have areas that are below the photic zone. Anyway, 10 years of enormously powerful effort went into that question. And so
with a lot of empirical data, right? They built many mesocosms.
Oh, yeah.
Yeah. Dragos, what's up? You have your hand up.
Yeah, I had a question for you actually. I was asking myself how much of a duckweed, how much duckweed can you eat a day? For how long?
Oh.
In terms of biomass.
Well, like any plant, I mean, you're going to need other things in your diet. It doesn't provide you everything you need. How much can you safely eat with Wolffia? I don't think there's any limit. There's no toxin, no toxic elements. If you're going to eat lemna, you have a problem with oxalic acid, that you can reduce its production, but you're going to want to either cook it or give it a limit how much you eat. But that's why we stick with Wolffia, because it does not produce oxalic acid. So yeah, as far as I know, isn't really any limit except for your desire to eat that much duckweed in one day.
Does it form symbiosis with cyanobacteria or other nitrogen fixers?
Oh, sorry, about cyanobacteria?
Cyanobacteria or other nitrogen fixers, if it forms symbiosis with microbes, then it will.
That's a good question. I don't know a lot about that area yet. I would like to look into that a little bit more to see if there is some research on cyanobacteria and nitrogen fixation, because really they're so efficient at nitrogen metabolism, preferring ammonium nitrate, for example. They can use nitrate, but I don't know if there's a lot of need for fixation. But I'm that's just a guess, actually. It's not something I've researched.
While we're calling on raised hands, I see now that Joya, your hand has been up for, I think, a while. I don't know if that was intentional or not. But if you had a question, you're welcome to give it now. And nice of you to join us, Joya. Okay, the hand went down. I guess not. No worries. All right. Anyone have any comments before we drop off here? This has been really quite dense and interesting day. I'm looking forward to decompressing and thinking about it, and then doing it all again tomorrow. Okay, there's no further comments, so I guess we can just wrap this up. Oh, and we did get some feedback in the chat, but it was all really positive. I guess anyone who wasn't having a good time already left, so that's great confirmation bias.
Yeah, we did lose some folks over the course of the day. I think they got worn out, but
yeah, I can't blame them. All right, well, thanks so much everybody for coming. This has been super fun, and I'm learning a lot personally. I hope you guys are. So I will see you all again bright and early tomorrow, or perhaps dark and late tomorrow, depending where you are. Until then, see you guys.
bye-bye. Thanks, everyone.